Following is a conversation with Chris Rabbi.
Oh, what the fuck is that shit? No wonder.
As I've said many times before, he's one of the most brilliant engineers in modern computing, having created LLM compiler infrastructure project, the Clang compiler, the programming language, a lot of key contributions to TensorFlow and TPUs for Google. He served as vice president of Autopilot software at Tesla, was a software innovator, a leader at Apple, and now he co-created a new full-stack AI infrastructure for distributed training, inference, and deployment on all kinds of hardware called modular, and a new programming language called Mojo that is a superset of Python, giving you all the usability of Python with the performance of C, C++. In many cases, Mojo code is demonstrated over 30,000x speed up of Python. If you love machine learning, if you love Python, you should definitely give Mojo a try. This programming language, this new AI framework, and this conversation with Chris
I've got
is
Mojo.
mind-blowing.
What is Mojo?
I love it.
Sex appeal?
It gets pretty technical at times, so
I gotta take a whiz.
The ride.
What kind of whiz,
This
Rabbi?
is the Let's Do This podcast supported. Please check out our sponsors in the description. Acknowledge your friends. It's Chris.
What kind of,
It's been,
I don't know,
5'5"?
5'5"?
Since we last talked, and in that time, you somehow went and co-created
An average piss lady.
Mojo.
I know pisses. I don't ask you what your piss
for
looks
AI,
like.
it's a superset of Python.
This one time,
Let's look at the
Oprah
big picture. What is the
had
vision
this thing.
for Mojo?
She like made me start thinking about piss colors and like how
working on a lot of
dehydrated you
technologies
can
for
be.
many years.
So what's super
A
hydrated?
lot of things in mobile like servers and things like this.
Like
But the
zero?
world's changed.
Zero should be you don't have to do it.
New GPUs and new machine learning accelerators.
Oh wait,
and
it can be
like that,
how badly you have to pee in the color.
At Google, work on GPUs, one of the biggest large scale
Alright.
systems
We're gonna-
exist for AI.
We're gonna have all this shit.
Really what you see
Standardized.
is if you look across all of the things that are happening in the industry, there's this new compute platform. And it's not just about
Some ladies gonna
CPUs or
I just
GPUs
had a
or
5.5.
PPUs or NPUs or IPUs or whatever, all the PUs. Right? It's about how we program this. Right? And so for software folks like us, right, it doesn't do us any good if there's this amazing hardware that we can't use. And one of the things you find out really quick is that having the theoretical capability of programming something and then having the world's power and the innovation of all the smart people in the world get unleashed on something can be quite different. And so really where Mojo came from was starting from a problem of you need to be able to take machine learning, take the infrastructure underneath it, make it way more accessible, way more usable, way more understandable by normal people and researchers and other folks that are not themselves like experts in GPUs and things like this. And then through that journey, we realized, hey, we need syntax for this. We need to do it.
So one of the main features of the language, I say so fully in jest, is that it allows you to have the file extension to be
I think it's 5.5.
file emoji, which is one of the first emojis used as a file extension I've ever seen in my life. And you ask yourself the question, why in the 21st century are we not using Unicode for file extensions? Because I mean, it's an epic decision. I think clearly the most important decision in was, but you could also just use emoji or file extension.
Well, so, okay, so take a step back. I mean, Lex, you think that the world's ready for this? This is a big moment in the world, right?
We'll release this onto the world.
This is innovation.
I mean, it really is kind of brilliant. Emojis are such a big part of our daily lives. Why is it not important?
Well, and like you take a step back and look at what file extensions are. Right? They're basically metadata, right? And so why are we spending all the screen space on them, all the stuff? Also, you have them stacked with text files and PDF files and whatever else. Like, if you're gonna do something cool, you want to stand out, right? Emojis are colorful. They're visual. They're beautiful.
What's been the response so far? Is there support on like Windows on operating system in displaying like files for?
Yeah. The one problem I've seen is that Git doesn't escape it right, and so it thinks that the fire emoji is unprintable, and so it like prints out weird hex things. Use command line Git tool, but everything else, as far as I'm aware, I have faith that Git can be improved. So
GitHub is fine.
GitHub is fine. Yeah, GitHub is fine. Visual Studio Code, Windows, like all this stuff, totally ready. because people have internationalization in their normal part of their path. So this is just the next step, right? Somewhere between, oh wow, that makes sense. Cool. I like new things. To, oh my god, you're killing my baby. Like, what are you talking about? This can never, like, I can never handle this. How am I going to type this? Like, all these things. And so this is something where I think that the world will get there. You don't have to bet the whole farm on this. I think we can provide both paths. But I think this is great.
When can we have emojis as part of
Yeah, so I mean, let's just provide that. So I think that we have partial support for that. It's probably not fully done yet, but yeah, you can do that. For example, in Swift, you can do that for sure. So an example we give Apple was the dog cow. Yeah. So it's a classical Mac heritage thing. So it's the dog and the cow merged together, and that's a variable. Of course, the internet went and made pilot poop for everything. So if you want to name your function pilot poop, then you can totally go to town and see how it gets put review.
Okay, so let me just ask a bunch of random questions. So is Mojo primarily designed for AIs, or what is it a general purpose?
Good question. So it's AI first, and so AI is driving a lot of the requirements, and so Modular is building and designing and driving moving forward. And it's not because it's an interesting project theoretically to build, it's because we need it. And so at Modular, we're really tackling the AI infrastructure landscape and the big problems in AI, and the reasons that it is so difficult to use and scale and adopt and deploy and all these big problems in AI. And so we're coming at it from that perspective. Now, when you do that, when you start tackling these problems, you realize that the solution to these problems isn't actually an AI-specific solution. And so what we're doing is we're building what would be a fully general program language. That means that you can obviously tackle GPUs and CPUs and like these AI things, but it's also a really great way to build NumPy and other things like that. Or just if you look at what many Python libraries are today, often they're a layer of Python for the API, and they end up being C and C++ underneath them. That's very true in AI. That's true in lots of other domains as well. So anytime you see this pattern, that's an opportunity for Mojo to help simplify the world and help people have one thing.
Optimize through simplification by having one thing. You mentioned Modular. Mojo is the programming language. Modular is the whole software stack.
So just over a year ago, we started something called Modular. Yeah, what Modular is about is about taking AI and up-leveling it into the next generation. So if you take a step back, what's gone on in the last 5, 6, 7, 8 years is that we've had things like TensorFlow, PyTorch, these other systems come in. We've used them, we know this. And what's happened is these things have grown like crazy. They get tons of users in production deployment scenarios, being used to power so many systems. AI is all around us now. It used to be controversial years ago, but now it's a thing. But the challenge with these systems is that they haven't always been thought out with current demands in mind. So you think about it, where were LLMs 8 years ago? It didn't exist. Right? AI has changed so much, and a lot of what people are doing today are very different than when these systems were built. And meanwhile, the hardware side of this has gone into a huge mess. There's tons of new chips and accelerators, and every big company is announcing a new chip every day. And so between that, you have like moving system on one side, moving system on the other side, and it just turns into this gigantic mess, which makes it very difficult for people to actually use AI, particularly in production deployments. That's what Modular's doing for helping build out that software stack, solve some of those problems, so then people can be more productive and get more AI research into production. Now, what Mojo does is it's a really, really, really important piece of that. And so that is part of that engine, part of the technology that allows us to solve problems.
So Mojo is the programming language that allows you to do high-level programming, the low-level programming, to do all kinds of programming in that spectrum that gets you closer and closer to the hardware.
So take a step back to the left. What do you love about
Oh boy, where do I begin? What is love? What do I love about Python?
You're a guy who knows about it.
Yes. How intuitive it is. How it feels like I'm writing an actual language. English. How when I can not just write but read other people's code, somehow I can understand it faster. It's more condensed than other languages, like the ones I'm really familiar with, like C++. and C. Uh, there's a bunch of sexy little features. Uh, we'll probably talk about some of them, but list comprehensions and stuff like this.
So, and don't forget the entire ecosystem of all packages.
Oh yes, it's probably huge.
There's always something. If you want to do anything, there's always a package.
Yeah, so it's not just the ecosystem of the packages and the ecosystem of the humans that do it. That's an interesting dynamic, because I think something about the usability and the ecosystem makes this thing viral and it grows, and it's a virtuous cycle.
Well, and there's many things that went into that. Like, so I think that ML was very good for Python, and so I think that kind of growing PyTorch systems, embracing Python really took and helped make that grow. But I think that the major thing underlying it is that Python's like the universal connector. And it really helps bring together lots of different systems. You can compose them and build out larger systems without having to understand how it works. But then, what is the problem with Python?
Well, I guess you could say several things, but probably that it's slow.
I think that's usually what people complain about, right? And so I mean, other people complain about tabs and spaces versus curly braces or whatever, but I mean, those people are just wrong. It is actually just better to use indentation.
Wow, strong words. So actually, it's a small tangent. Let's actually take that. Let's take all kinds of tangents.
Oh, come on, Lex, you can push me. I can take it.
Design. Listen, I recently left Emacs for VS Code.
Okay.
The kind of hate mail I had to receive, because on the way to doing that, I also said I've considered Vim,
Yep.
and chose not to with VS Code. And just,
Touching on deep religions, right?
anyway, tabs is an interesting design decision, and so you've really written a new programming language here. Yes, it is a superset of Python, but you can make a bunch of different interesting decisions here. And you chose actually to stick with Python as in terms of some of the syntax.
So let me finish. So, I mean, you can explain this in many rational ways. I think that the indentation is beautiful, but that's not a rational explanation. Right? So, but I can defend it rationally. First of all, Python 1 has millions of programmers.
Yeah.
It is huge. It's everywhere. It owns machine learning. So, actually, it is the thing. Second of all, if you look at it, C code, C++ code, Java, whatever stuff, curly brace languages also run through formatting tools and get indented. And so if they're not indented correctly, first of all, we push your brain around. It can lead to bugs. There's notorious bugs that happen across time, but the indentation was wrong and misleading, and it wasn't formatted right, and so it turned into an issue, right? And so what ends up happening in modern large-scale code bases, people run automatic format. So now what you end up with is indentation and curly braces. You're going to have the notion of grouping. Why not have one thing? Right? Get rid of all the clutter and have a more beautiful thing. Also, you look at any of these languages, it's like, okay, well, you can have curly braces, or you can omit them with one statement, or you just like enter this entire world of complicated design space that objectively you don't need.
Yeah, I would love to actually see statistics on errors made because of indentation. Like how many errors are made in Python versus in C++ that have to do with basic formatting. I'd love to see.
I think it's probably pretty minor, because once you get like you use VS Code, I do too. So if you get VS Code set up, it does the indentation for you. Right? So you don't, it's actually really nice to not have to fight it. And then what you can see is the editor is telling you how your code will work by indenting, which I think is pretty cool.
I honestly don't think I don't remember having an error in Python because I didn't stuff.
So I mean, I think that they're again. So I can joke about it, and I love to kind of, I realize this is such a polarizing thing, and everyone wants to argue about it. So I like poking at the bear a little bit, right? But frankly, right? Come back to the first point. Like it's huge. It's an AI. It's the right thing for us. Like we see Mojo as being an incredible part of the Python ecosystem. We're not looking to break Python or change it or quote unquote fix it. We love Python for what it is. Our view is that Python is just not done yet. If you look at, you mentioned Python being slow. Well, there's a couple of different things that go into that we should talk about. But one of them is it just doesn't have those features that you would use to do C-like programming. And so if you say, okay, well, I'm forced out of Python into C for certain use cases, well, then what we're doing is we're saying, okay, well, why is that? Can we just add those features that are missing from Python back up to Mojo? And then you can have everything that's great about Python, all the things you're talking about as well. Plus, not be forced out of it when you do something a little bit more computational intense or weird or hardware-y or whatever it is.
Well, a million questions I want to ask, but at high level again, is it compiled or is it an interpreted language? So Python is just in time compilation. What's Mojo?
So Mojo, the complicated answer, does all the things. So it's interpreted, it's chip compiled, and it's statically compiled. And so this is for a variety of reasons. One of the things that makes Python beautiful is that it's very dynamic. And because it's dynamic, one of the things they added is that it has this powerful metaprogramming feature. And so if you look at something like PyTorch or TensorFlow or even a simple use case, like you find a class that has the plus method. And you can overload the dunder methods like dunder add, for example, and then the plus method works on your class. And so it has very nice and very expressive dynamic metaprogramming features. In Mojo, we want all those features to come in. If we don't want to break Python, we want it all to work. The problem is you can't run those super dynamic features on an embedded processor or on a GPU. Right? Or if you could, you probably don't want to just because of the performance. So we entered this question of saying, okay, how do you get the power of this dynamic metaprogramming into a language that has to be super efficient in specific cases? And so what we did was we said, okay, we'll take that interpreter. Python has an interpreter in it, right? Take that interpreter and allow it to run at compile time. And so now what you get is you get compile time method. And so this is super interesting, super powerful, because one of the big advantages you get is you get Python-style expressive APIs. You get the ability to overload operators. And if you look at what happens inside of PyTorch, for example, with automatic differentiation, computer mode, like all these things, they're using these really dynamic features at runtime. But we can take those features and list them so that they don't compile.
So the C++ has metaprogramming with templates, but it's really messy.
It's super messy. It's always, it was accidentally, different people have different interpretations. My interpretation is that it was made accidentally powerful. It was not designed to be Turing complete, for example, but that was discovered kind of along the way, accidentally. And so there have been a number of languages in the space. So they usually have templates, code instantiation, and copying features of various sorts. Some more modern languages, or some more newer languages, let's say, like, they're fairly unknown, like Zig, for example, says, okay, well, let's take all of those types you can run it, all those things you can do at runtime, and allow them to happen at runtime. And so one of the problems with C++, which is one of the problems with C++, is it's okay. I mean, everybody hates me for a variety of reasons, anyways, I'm sure. Right? I've written enough the way they show love. I've written enough C++ code to earn a little bit of grumpiness with C++. But one of the problems with it is that the metaprogramming system templates, it's just a completely different universe from the normal runtime programming. So if you do metaprogramming and programming, it's just like a different universe, different syntax, different concepts, different stuff going on. So again, one of our goals with Mojo is to make things really easy to use, easy to learn, and so there's a natural stepping stone. And so as you do this, you say, okay, well, I have to do programming at runtime. I have to do programming at compile time. Why are these different things?
How hard is that to pull up? Because that sounds, to me as a fan of metaprogramming in C++, how hard is it to pull that off? That sounds really, really exciting, because you can do the same style programming at compile time and runtime. That's really
Yep. And so, I mean, in terms of the compiler implementation details, it's hard. I won't be shy about that. It's super hard. It requires, what Mojo has underneath the covers is a completely new approach to the design of the compiler itself. And so it's built on these technologies like MLIR that you mentioned, but it also includes other caching and other interpreters and JIT compilers and other stuff like that.
You have like an interpreter inside
within the compiler. Yes. And so it really takes the standard model of programming languages and kind of twists it and unifies it with the runtime, which I think is really cool. And to me, the value of that is that, again, many of these languages have metaprogramming. Like they grow macros or something. Like you can list, right? I know your roots, right? and this is a powerful thing, right? And so, if you go back to the list, one of the most powerful things about it is that it said that the data for programming are the same, right? And so that made it way simpler, way more consistent, way easier to understand, reason about, and it made it more composable. So if you go to the library, you can use it both at runtime, which is pretty cool.
Yeah. And then for machine learning and programming, I think you could generally say is extremely useful. And so you get features, I'll jump around, but there's the feature of auto-tuning and adaptive compilation just blows my mind.
Yeah. Well, so let's go back to that. So,
all right.
So what is machine learning? Like, what is a machine learning model? It's really interesting to me because what PyTorch and what TensorFlow and all these frameworks are kind of pushing compute into is they're pushing into like this abstract specification of a compute problem. We're saying it's mapped to a whole bunch of different things. And so this is why it became a map programming problem. So you want to be able to say, cool, I have this neural net, I run it with batch size 1,000. Do a mapping across batch. Or okay, I want to take this problem, now run it across 1,000 CPUs or GPUs. And so like this problem, like just describe the compute, then map it and do things and transform it are like actually it's very profound, and that's one of the things that makes machine learning systems really special.
Maybe can you describe auto-tuning and how do you pull off? I mean, I guess adaptive compilation is what we're talking about. Yeah, how do you pull off auto-tune? I mean, is that as profound as I think it is? It seems like a really like we mentioned list comprehensions. To me, from a quick glance at Mojo, which by the way I have to absolutely like dive in. As I realize how amazing this is, like they absolutely must have. That looks like just an incredible feature for machine learning.
Yeah. Well, so what is auto tuning? So take a step back. Auto tuning is a feature in Mojo. It's not so very very little of what we're doing is actually research. Many of these ideas have existed in other systems and other places, and so what we're doing is we're pulling together good ideas, remixing them, and making them into hopefully a beautiful system. Right? So auto tuning, the observation is that turns out hardware systems, algorithms are really complicated. Turns out maybe you don't actually want to know how the hardware works, right? A lot of people don't. Right? So there are lots of really smart hardware people, I know a lot of them, where they know everything about, okay, the cache size is this, and the number of registers is that. If you use this length of vector, it's going to be super efficient. It's mapped directly onto what we can do, like all this kind of stuff. Or the GPU has SMs and has a warp size of whatever, right? All the stuff that goes into these things, or the tau size of a TPU is 128, like these factoids. My belief is that most normal people, I love hardware people, so I'm not trying to offend literally everybody on the internet, but most programmers actually don't want to know this stuff, right? So if you come at it from the perspective of how do we allow people to build both more abstracted but also more portable code, because it could be that the vector length changes, or the cache size changes, or it could be that the tau size of your matrix changes, or the number, an A100 versus an A200 versus a Volta versus a whatever GPU have different characteristics, right? A lot of the algorithms that you run are actually the same, but the parameters, these magic numbers you have to fill in, end up being really fiddly numbers that an expert has to go figure out. And so what auto-tuning does is says, okay, well, guess what? There's a lot of compute out there. Right? So instead of having humans go randomly try all the things, or do a grid search, or go search some complicated multi-dimensional space, how do we have computers do that? Right? And so what auto-tuning does is you can say, hey, here's my algorithm. If it's a matrix operation or something like that, you can say, okay, I want to carve it up into blocks. I want to do those blocks in parallel, and I want this with 128 things I'm running on. I want to cut it this way or that way or whatever. And you can say, hey, go see which one's actually empirically better on the system.
And then the result of that, you cache for that system.
Yep.
You save it.
And so come back to twisting your compiler brain, right? So not only does the compiler have an interpreter that's used to do that programming, that compiler, that interpreter, programming now has to actually take your code and go run it on a target machine. see which one it likes the best, and then stitch it in and then keep going.
So part of the compilation is machine specific.
Yeah. So I mean, this is an optional feature, right? So you don't have to use it for everything. But yeah, if you're so one of the things that we're in the quest of is ultimate performance. Right, ultimate performance is important for a couple of reasons. Right, so if you're an enterprise, you're looking to save costs and compute, things like this. Ultimate performance translates to fewer servers. you care about the environment, hey, better performance leads to more efficiency. I mean, you could joke and say like, Python's bad for the environment, right? And so if you move to Mojo, it's like it's 10x better just out of the box and keep going, right? But performance is also interesting because it leads to better products. And so in the space of machine learning, right, if you reduce the latency of a model, so every time you query the server running the model, it takes less time, but then the product team can go and make the model bigger. Well, that actually makes it so you have a better experience as a customer. And so a lot of people care about that.
So for auto tuning, for like tile size and 128 for TPU, you would specify like a bunch of options to try just in the code, simple statement, and then you can just set and forget and know, depending on wherever it compiles, it will actually be the fastest.
And yeah, exactly. And the beauty of this is that it helps you in a whole bunch of different ways, right? So if you're building, so often what will happen is that you're building stuff for yourself, right? You wake up one day, you say, I have an idea, I'm going to go put up some code, I get to work, I forget about it, I move on with life, I come back 6 months or a year or 2 years or 3 years later, you dust it off and you go use it again in a new environment. And maybe your GPU is different. Maybe you're running on a server instead of a laptop, maybe whatever, right? And so the problem now is you say, okay, well, I mean, not everybody cares about performance, but if you do, you say, okay, well, I want to take advantage of all these new features. I don't want to break the old thing, though. And so the typical way of handling this kind of stuff before is let's say this is templates, or you're talking about C with macros, you end up with if-defs, you get like all these weird things get layered in, make the code super complicated, and then how do you test it? Right? It becomes this crazy complexity, multi-dimensional space you have to worry about. And that just doesn't scale very well.
Actually, let me just jump around before I go to specific features. Like the increase in performance here that we're talking about can be just insane. You're right that Mojo can provide a 35,000x speed up over Python. How does it do that?
Yeah, so I can even get more, but we'll get to that. So first of all, when we say that, we're talking about what's called CPython. It's the default Python that everybody uses. When you type Python 3, that's like typically the one you use, right? CPython is an interpreter. And so interpreters, they have an extra layer of like byte codes and things like this that they have to go read, parse, interpret, and make some kind of slow from that perspective. And so one of the first things we do is we move to a compiler. And so just moving to a compiler, getting the interpreter out of the loop is 2 to 5 to 10x speed up depending on the code. So just out of the gate, just using more modern techniques. Now, if you do that, one of the things you can do is you can start to look at how CPython started to lay out data. And so one of the things that CPython did, and this isn't part of the Python spec necessarily, but this is just a set of decisions, is that if you take an integer, for example, it'll put it in an object. In Python, everything's an object. And so they do the very logical thing, keeping the memory representation of all objects the same. So all objects have a header, they have like payload data. What this means is that every time you pass around an object, you're passing around a pointer to the data. Well, this has overhead. It turns out that modern computers don't like using pointers very much and things like this. It means you have to allocate the data, and you have to reference count it, which is another way that Python uses to keep track of memory. And so this has a lot of overhead. And so if you say, okay, let's try to get that out of the heap, out of a box, out of the direction, and into the registers. That's another 10x.
So it adds up if you're reference counting every single thing you create, that adds up.
Yep. And if you look at, people complain about the Python GIL, this is one of the things that hurts parallelism. That's because of the reference count. So the GIL and reference counting are very tightly intertwined in Python. It's not the only thing, but it's very tightly intertwined. And so then you lean into this and say, okay, cool. Well, modern computers, they can do more than one operation at a time. So they have vectors. Use a vector. Well, a vector allows you to take one, instead of taking one piece of data, doing an add or multiply, and then pick up the next one, you can now do 4 or 8 or 16 or 32 at a time. Well, Python doesn't expose that because of reasons. And so now you can say, okay, well, you can adopt that. Now you have threads. You have like additional things where you can control memory hierarchy. And so what Mojo allows you to do is it allows you to start taking advantage of all these powerful things that have been built into the hardware over time. And the library gives very nice features. So you can say, just parallelize this, do some parallel. Right? So it's very very powerful weapons against slowness, which is why people have that. And I think having fun, like just taking code and making it go fast, because it's an adrenaline rush to see like how fast you can get things.
Before I talk about some of the interesting stuff with parallelization and all that, let's first talk about the basics. We talked to indentation, right? So this thing looks like Python. It's sexy and beautiful like Python, as we mentioned.
Yep.
Is it a language? So what's the role of types?
Yeah, good question. So Python has types. It has strings, it has integers, it has dictionaries, and all that stuff. But they all live at runtime. Right? And so because all those types live at runtime in Python, you don't have to spell them. Python also has like this whole typing thing going on now. A lot of people use it. Yeah. I'm not talking about that. That's kind of a different thing. We can go back to that. But typically the you just say I have a def, and my def takes two parameters. I'm going to call them A and B. So that is great, but what that does is that forces what's called a consistent representation. So these things have to be a pointer to an object with the object header, and they all have to look the same. And then when you dispatch a method, you go through all the same different paths, no matter what the receiver, whatever that type is. So what Mojo does is it allows you to have more than one kind of type. And so what it does is allows you to say, okay, cool, I have an object, and objects behave like Python does. It's fully dynamic, that's all great. For many things, classes, like that's all very powerful and very important. But if you want to say, hey, it's an integer, it's 32 bits, or 64 bits, or whatever, it's a floating point value, it's 64 bits, well, then the compiler can take that and it can use that to do way better optimization. And so again, the directions is huge, and you can get better code completion because you have this compiler knows what the type is, so it knows what operations work on it. And so that's actually pretty huge. And so what Mojo does, it allows you to progressively adopt types to your program. So you can start, it's compatible with Python, so then you can add however many types you want, wherever you want them. And if you don't want to deal with it, you don't have to deal with it. And so one of our opinions on this is that it's not that types are the right thing or the wrong thing. It's that they're a useful thing.
Which is kind of optional. It's not strict typing. You don't have to specify type.
Exactly.
Okay, so it's starting from the thing that Python's kind of reaching towards right now with trying to inject types into it.
With a very different approach, but yes. Yeah.
What's the different approach? I'm actually one of the people that have not been using type very much in Python.
That's okay. Why did you say?
It's just, because I know the importance. Like adults use strict typing. And so I refuse to grow up in that sense. It's a kind of rebellion. But I just know that it probably reduces the amount of errors. Even forget about performance improvements. It probably reduces errors if you reduce strict typing.
Yeah, so I mean, I think it's interesting to look at that, right? And the reason I'm giving you a hard time is that there's this cultural norm, this pressure, this like there has to be a right way to do things. Like only grown-ups only do it one way. If you don't do that, you should feel bad.
Yes.
Right? Like some people feel like Python's a guilty pleasure or something, and it's like when it gets serious, I need to go rewrite it. Right?
Yeah.
Well, I mean, cool. I understand history and I understand kind of where this comes from, but I don't think it has to be a guilty pleasure.
Yeah.
Right?
Yeah.
So if you look at that, you say, why do you have to rewrite it? Well, you have to rewrite to deploy. Well, why do you want to deploy? Well, you care about performance, you care about ability, or you want anything on the server that has no dependencies. You have objectives you're trying to attain. So what if Python can achieve those objectives? So if you want types, well, maybe you want types because you want to make sure you're passing the right thing. Sure, you can add a type. If you don't care, you're prototyping some stuff, you're hacking some things out, you're like pulling some random code off the internet, it should just work. Right? And you shouldn't be like pressured, you shouldn't feel bad about doing the right thing or the thing that feels good. Now, if you're in a team, right, you're working at some massive internet company, you have 400 million lines of Python code, well, they may have a house rule that you use types, right? It makes it easier for different humans to talk to each other and understand what's going on and folks at scale, right? And so there are lots of good reasons why you might want to use types, but that doesn't mean that everybody should use them all the time. So what Mojo does is it says, cool, well, allow people to use types, and if you use types, you get nice things out of it. You get performance, things like this, right? But Mojo is a full compatible superset of Python. And so that means it has to work without types. It has to support all the dynamic things. It has to support all the types. It has to support for comprehension, miscomprehensions, and things like this, right? And so that starting point, I think, is really important. And I think, again, you can look at why I care so much about this. And there's many different aspects of that. One of which is the world went through a very challenging migration from Python 2 to Python 3. Right? This migration took many years, and it was very painful for many teams. Right? And there's a lot of things that went on in that. I'm not an expert in all the details. I honestly don't want to be. I don't want the world to have to go through that, right? And people can ignore Mojo, and if it's not their thing, that's cool. But if they want to use Mojo, I don't want them to rewrite code.
I mean, the superstep part it's just so much brilliant stuff here. That definitely is incredible. We'll talk about that.
Yeah.
First of all, how's the typing implemented differently in Python versus Mojo? So this heterogeneous flexibility, you said, is differently implemented.
Yeah. So I'm not a full expert in the whole backstory on types in Python. So I'll give you that. I can give you my understanding. My understanding is basically, like many dynamic languages, the ecosystem went through a phase where people went from writing scripts to writing large-scale, huge code bases in Python, and at scale, kind of helps have types. People want to be able to reason about interfaces, what you expect string and int, like what are these basic things. And so what the Python community started doing is it started saying, okay, let's have tools on the side, checker tools, like to go and like enforce invariance, check for bugs, try to identify things. These are called static analysis tools generally. And so these tools run over your code and try to look for bugs. What ended up happening is there's so many of these things, so many different weird patterns and different approaches on specifying types and different things going on that the Python community realized and recognized, hey, there's a thing here. And so what they started to do is they started to standardize the syntax for adding types to Python. Now, one of the challenges they had is they're coming from kind of this fragmented world where there's lots of different tools, they have different trade-offs and interpretations and types of different things. And so if you look at types in Python, according to the Python spec, the types are ignored. So according to the Python spec, you can write pretty much anything in a type position. Okay? And you can write any expression. Okay? Now, that's beautiful because you can extend, you can do cool things, you can build your own tools, you can build your own house linter or something like that, right? But it's also a problem because any existing Python program may be using different tools and they have different interpretations. So if you adopt somebody's package into your ecosystem, try to run the tool you prefer, it may throw out tons of weird errors and warnings and problems just because it's incompatible with how these things work. Also because they were added late, not checked by interpreter, it's always kind of more of a hint than it is a requirement. And so the C Python implementation can't use them for performance. And so it's really
that's the big one, right? So you can't utilize for the compilation, for the different kind of compilation.
Yeah, exactly. And this all comes back to the design principle. They're kind of hints. They're kind of, the definition's a little bit murky. It's unclear exactly the interpretation in a bunch of cases. And so because of that, you can't actually, even if you want to, it's really difficult to use them to say, like, it is going to be an int. If it's not, it's a problem. Right? A lot of code would break. So in Mojo, right, so you can still use those kind of type annotations, it's fine. But in Mojo, if you declare a type and you use it, then it means it is going to be that type. And the compiler helps you check that, enforce it, and it's safe. And it's not a like best effort hint kind of thing.
So if you try to shove a string type thing into an integer,
you get an error
from the compiler compile time. Nice. Okay, what kind of basic types are there?
Yeah, so Mojo is pretty hardcore in terms of what it tries to do in the language, which is the philosophy there is that we, if you look at Python, right, Python's a beautiful language because it's so extensive. Right? And so all of the different things in Python, like for loops and plus, and like all these things can be accessed through these underbar methods. Okay? So you have to say, okay, if I make something that is super fast, I can go all the way down to the metal. Why do I need to have integers built into the language? And so what Mojo does is it says, okay, well, we can have this notion of structs. So we have classes in Python, now you can have structs. Classes are dynamic, structs are static. Cool, we can have performance, we can write C++ kind of code with structs if you want. These things mix and work beautifully together. But what that means is that you can go and implement strings and ints and floats and arrays and all that kind of stuff in the language, right? And so that's really cool because me as a idealizing compiler language type of person, what I want to do is I want to get magic out of the compiler and put it in the libraries. Because if somebody can, if we can build an integer that's beautiful and has an amazing API and does all the things you'd expect an integer to do, if you don't like it, maybe you want a big integer, maybe you want a sideways integer. I don't know, what all the integers are. Then you can do that, and it's not a second class system. And so if you look at certain other languages like C++, one I also love and use a lot, int is hard-coded language, but complex is not. And so isn't it kind of weird that you have this std complex class, but you have int, and complex tries to look like a natural numeric type and things like this, but integers and floating point have these special promotion rules and other things like that that are magic and are hacked in with the pilot. Because of that, you can't actually make something that works like the book of text.
Is there something provided as a standard? Because because it's AI first, numerical types are so important here. So is there something like a nice standard implementation of digital things?
Yeah, so we're still building all that stuff out. So we provide integers and floats and all that kind of stuff. We also provide buffers and tensors and things like that you'd expect in an ML context. Honestly, we need to keep designing, redesigning, and working with the community to build that out, make that better. That's not our strength right now. Give us 6 months or a year, and I think we'll be way better. But the power of putting it in the library means we can have teams of experts that aren't compiler engineers that can help us design and refine and drive this forward.
So one of the exciting things we should mention here is that this is new and fresh. This cake is unbaked. It's almost baked. You can tell it's delicious, but it's not fully ready to be consumed.
Yep, that's very fair. It is very useful, but it's very useful if you're a super low-level programmer right now. And what we're doing is we're working our way up the stack. And so the way I would look at Mojo today in May 2023 is that it's like a 0.1. So I think that a year from now, it'll be way more interesting to a variety of people. But what we're doing is we decided to release it early so that people can get access to anything. We can build with the community. We have a big roadmap that we publish, being transparent about this, and a lot of people are involved in this stuff. And so what we're doing is we're really optimizing for building this thing the right way. And building it the right way is kind of interesting working with the community because everybody wants it yesterday. And so sometimes it's kind of, there's some dynamics there. But
Yeah,
I think it's the right thing.
So there's a Discord also, so the dynamics is pretty interesting. Sometimes the community probably can be very chaotic and introduce a lot of stress. Guido have famously quit over the stress of the walrus operator. I mean, it broke. Maybe that was broke the camel's back. Exactly. And so it could be very stressful to develop. You can just tangent upon a tangent. Is it stressful to work through the design of various features here, given that the community is so richly involved?
Also, so I've been doing open development and community stuff for decades now. Somehow this has happened to me. So I've learned some tricks. But the thing that always gets me is I want to make people happy, right? And so this is maybe not all people all happy all the time, but generally I want people to be happy, right? So the challenge is that, again, we're tapping into some deep-seated long tensions and pressures, both in the Python world, but also the AI world, the hardware world, and things like this. So people just want to be faster. And so, again, our decision was, let's release this early. Let's get people used to it or access to it and play with it. And let's build it in the open, which we could have had the language monk sitting in the cloister up on the hilltop, beavering away trying to build something. But in my experience, you get something that's way better if you work with it. And so, yes, it can be frustrating. It can be challenging for lots of people involved. And if you mention our Discord, we have over 10,000 people on the Discord, 11,000 people or something. Keep in mind, we released Mojo 2 weeks ago. So it's very cool. But what that means is that 10, 11,000 people all will want something different, right? And so what we've done is we've tried to say, okay, cool, here's our roadmap. Here, and the roadmap isn't completely arbitrary. It's based on here's the logical order in which to build these features or add these capabilities and things like that. And what we've done is we spun really fast on like bug fixes. So we actually have very few bugs, which is cool. I mean, actually for projects in the state, but then what we're doing is we're dropping features very deliberately.
I mean, it's just fun to watch because you got the two gigantic communities of like hardware, like systems engineers, and then you have the machine learning Python people that are like higher level.
Yeah.
And it's just two like army
they've been at war. Yeah, they've been at war. Right, and so here's
a Tolkien novel or something.
Okay, so here's the test. Again, like it's super funny for something that's only been out for 2 weeks, right? People are so impatient, right? But okay, cool. Let's fast forward a year. Like in a year's time, Mojo will be actually quite amazing and self-control, be very good. People still have these problems, right? And so you look at this, you say, and the way I look at this at least is to say, okay, well, we're solving big, long-standing problems. To me, looking at it, I want to make sure we do it right. Right? There's like a responsibility you feel because if you mess it up, right? There's very few opportunities to do projects like this and have them really have an impact on the world. If we do it right, then maybe we can take those feuding armies and actually heal some of those wounds.
Yeah,
right?
Like this feels like a speech by George Washington, right? Or something.
And you look at this, it's like, okay, well, how different are we?
Yeah.
We all want beautiful things. We all want something that's nice. We all want to be able to work together. We all want our stuff to be used. Right? So if we can help heal that, now I'm not optimistic that all people will use Mojo and stuff using C++. Like that's not my goal, right? But if we can heal some of that, I think that'd be pretty cool.
Yeah. And we can start by putting the people who like races into the group.
So there are proposals for adding braces to Mojo. We tell them no.
Okay. Politely. Yeah. Anyway, so there's a lot of amazing features on the roadmap, and these are implemented. It'd be awesome. I could just ask you a few things.
Yeah,
so the other performance improvement comes from immutability. So what's this var and this let thing that we got going on? Well, what's immutability?
Yeah, so one of the things that is useful, and it's not always required, but it's useful, is knowing whether something can change out from underneath it. So in Python, you have a pointer to an array. Right? So you pass that pointer to an array around to things. You pass into a function. Maybe take that and scroll it away into some other data structure. So you get your array back, and you go to use it. Now somebody else is like putting stuff in your array. How do you reason about that? It's to be very complicated and be selective about. And so one of the things that, again, this is not something Mojo forces on you, but something Mojo enables is a thing called value semantics. And what value semantics do is they take collections like arrays, dictionaries, so tensors, and strings, and things like this at a much higher level and make them behave like proper values. So it makes it look like you pass these things around, you get a logical copy of all the data. If I pass you an array, it's your array. You can go do what you want to it. You're not going to hurt my array. Now, that is an interesting and very powerful design principle. It defines away a ton of bugs. You have to be careful to implement it in an efficient way.
Is there a performance hit that's significant?
Generally not, if you implement it the right way, but it requires a lot of very low level getting the language right hits.
I assume that'd be a huge performance hit because it's the benefit is really nice. You don't get
absolutely. Well, the trick is you can't do copies, so you have to provide the behavior of copying without doing the copy.
Yeah. How do you do that?
It's not magic. It's just it's actually pretty cool. Well, so first, before we talk about how that works, let's talk about how it works in Python. Right? So in Python, you define a person class, or maybe person class is a bad idea. You define a database class, right? And the database class has an array of records, something like that, right? And so the problem is that if you pass in a record or a class instance into a database, it'll take hold of that object, and then it assumes it has it. And if you're passing an object in, you have to know that that database is going to take it, and therefore you shouldn't change it after you put it in the database. Right? This is
just kind of have to know that.
You just have to kind of know that, right? And so you roll out version 1 of the database, you just kind of have to know that. Of course, Lex uses its own database, right?
Yeah.
Right? Because you built it. You understand it first, right? Somebody else joins the team. They don't know this, right? And so now they suddenly get bugs. You're having to maintain a database. You shake your fist. You argue. The 10th time this happens, you're like, okay, we have to do something different, right? So what you do is you go change your Python code, when you change your database class, to copy the record every time you add it. And so what ends up happening is you say, okay, I will do what's called a defensive copy inside the database. And then that way, if somebody passes something in, I will have my own copy of it. And they can go do whatever, and they're not going to break my thing. Okay, this is usually the two design factors. If you look at PyTorch, for example, this is cloning a tensor. There's a specific thing, and you have to know where to call it, and you have to call it right place, you get bugs, and this is state of the art. So a different approach, so it's used in many languages, so I work with it in Swift, is you say, okay, well, let's provide value standards. So we want to provide the view that you get a logically independent copy, but we want to do that lazily. And so what we do is we say, okay, if you pass something into a function, it doesn't actually make a copy. What it actually does is it just increments a reference to it. And if you pass it around, you stick it in the database, you go in the database, you own it, and then you come back out of the stack, nobody's copied anything. You come back out of the stack, and the caller lets go of it. Well, then you've just handed it off to the database, you've transferred it, and there's no copies made. Now, on the other hand, if your coworker goes and hands you a record and you pass it in, you stick it in the database, and then you go to town and you start modifying it, what happens is you get a copy lazily on demand. And so what this does is gives you copies only when you need them, and it also, so it depends on the bugs, but also generally reduces the number of copies in practice. So
But the implementation details are tricky here.
yeah, so this is, yes.
Something with reference counting, but to make it performant across a number of different kinds of objects.
Yeah, well, so you need a couple of things. So there's many, so this concept has existed in many different worlds, and so it's not novel research at all, right? The magic is getting the design right so that you can do this in a reasonable way, right? So there's a number of components that go into this. One is when you're passing around, so we're talking about Python and reference counting and the expense of doing that. When you're passing values around, you don't want to do extra reference counting for no good reason. And so you have to make sure that you're efficient and you transfer ownership instead of duplicating references and things like that, which is a very low-level problem. You also have to adopt this. You have to build these data structures. And so you say, most be compatible with Python. So of course, the default list is a reference semantic list. It works the way you'd expect in Python, but then you have to design a value semantic list. So you just implement that, and then you implement the logic thing. And so the role of the language here is to provide all the low-level hooks that allow the author of the type to be able to get to express this behavior without forcing it into all cases or hard coding the system.
But there's ownership, so you're constantly transferring, tracking who owns it.
Yes. So there's a whole system called ownership, and so this is related to work done in the Rust community. So the Swift community has done a bunch of work, and there's a bunch of different other languages involved. Kind of C++ actually has copy constructors and destructors and things like that, and so and C++ has everything. So it has move constructors and has like this whole world of things. And so this is a body of work that's kind of been developing for many, many years now. So Mojo takes some of the best ideas out of all of these systems and releases them in a nice way so that you get the power of something like the Rust programming language, but you don't have to deal with it when you don't want to, which is a major thing in terms of teaching and learning and being able to use and scale these systems.
How does that play with argument conventions? What are they? Why are they important? How does the value semantics? How does the transfer ownership work with the arguments when they're passing?
Yeah. So if you go deep into systems programming, this isn't, again, it's not something for everybody. But if you go deep into systems programming, what you encounter is these types that get weird. So if you're used to Python, you think about everything, just copy it around. I can go change it and mutate it and do these things, and it's all cool. If you get into systems programming, where you get into these things like I have an atomic number, or I have a mutex, or I have a uniquely owned database handler, things like this. Right? So these types you can't necessarily copy. Sometimes you can't necessarily even move them to a different address. And so what Mojo allows you to do is it allows you to express, hey, I don't want to get a copy of this thing. I want to actually just get a reference to it. And by doing that, what you can say, okay, if I'm defining something weird, like a atomic number or something, it's like it has to be, so an atomic number is an area in memory that multiple threads can access at a time without locks. Right? And so like the definition of atomic numbers, multiple different things have to be people can't. Therefore, they have to agree on where it is. Right? So you can't just like move it up underneath one because it kind of breaks what it means. And so that's an example of tech that you can't copy, you can't move. It, like once you create it, it has to be where it was. Now, if you look at many other examples of the database handle, right? So, okay, well, what happens? How do you copy a database handle? Do you copy the whole database? That's not something you necessarily want to do. There's a lot of types like that where you want to be able to say that they are uniquely owned. So there's always one of this thing, and or if I create a thing, I don't copy it. And so what Mojo allows you to do is it allows you to say, hey, I want to pass around and reference this thing without copying it. And so it has borrowed conventions. So you can say you can use it, but you don't get to change it. You can pass it by mutable reference. And so if you do that, then you get a reference to it, you can change it, and so it manages all that kind of stuff.
So it's just a really nice implementation of like the C++ has, the reference types of pointers.
Yeah,
Smart, different kinds of implementations of smart pointers that you can explicitly define this allows. But you're saying that's more like the weird case versus the common case.
well, it depends on what I mean. I don't think I'm a normal person, so
Yes.
I'm not going to call other people weird.
Yeah.
But if you talk to a typical Python programmer, you're definitely not thinking about this, right? This is a lower level of abstraction. If you talk to a C++ programmer, certainly if you talk to a Rust programmer, again, they're not weird, they're delightful. Like these are all good people, right? Those folks I think about all the time, right? And so I look at this as there's a spectrum between very deep, low-level systems. I'm going to go poke the bits and care about how they're laid out in memory, all the way up to application and scripting and other things like this. So it's not that anybody's right or wrong. It's about how do we build one system that scales.
By the way, the idea of an atomic number has been something that always brought me deep happiness, because the flip side of that, the idea that threads can just modify stuff asynchronously. So the whole idea of concurrent programming is a source of infinite stress.
Well, so this is where you jump into, again, you zoom out and get out of programming languages and just look what the industry has done. My mind is constantly blown by this, right? And you look at what, Moore's Law. Moore's Law is this idea that computers, for a long time, single thread performance just got faster and faster and faster and faster for free. But then physics and other things intervened, and power consumption, like other things started to matter. And so what ended up happening is we went from single core computers to multi-core, and we went to accelerators. And this trend towards specialization of hardware is only going to continue. And so for years, us programming language nerds and other people have been saying, well, how do we tackle multi-core? Right? For a while, it was like, multi-core is the future. We have to get on top of this thing. Then it was multi-core is the default. What are we doing with this thing? And then it's like, there's chips with hundreds of cores in them. what happened, right?
Yeah.
And so I'm super inspired by the fact that, in the face of this, those machine learning people invented this idea of a tensor. Right? And what is a tensor? A tensor isn't like an arithmetic and algebraic concept. It's like an abstraction around a gigantic parallelizable data set, right? And because of that, and because of things like PyTorch, we're able to say, okay, we'll express the math of the system. This enables you to do automatic differentiation. This enables you to do like all these cool things, and it's an abstract representation. Because you have that abstract representation, you can map it onto these parallel machines without having to control. Okay, put that by here, put that by there, and this has enabled an explosion in terms of AI, compute, accelerators, like all this stuff. So that's super, super exciting.
What about the deployment and the execution across multiple machines?
Yeah.
So you write that the modular compute platform dynamically partitions models with billions of parameters and distributes their execution across multiple machines, enabling unparalleled efficiency. Whether they use unparalleled in that sentence anyway, enabling unparalleled efficiency, scale, and reliability for the largest workloads. So how do you do this abstraction of distributed deployment?
Yeah, so one of the really interesting tensions, so there's a whole bunch of stuff that goes into that. I'll pick a random walkthrough. if you go back and replay the history of machine learning, the brief most recent history of machine learning, very deep. I knew Lex with the AI podcast. Yes. Right. Yeah. So if you look at TensorFlow PyTorch, which is pretty recent history in the big picture, right? But TensorFlow is all about graphs. PyTorch, I think, pretty unarguably ended up winning. And why did it win? Mostly because of usability. Right. And the usability of PyTorch is, I think, huge. And I think, again, that's a huge testament to the power of taking abstract, theoretical, technical concepts and bringing it to the masses. Right. Now, the challenge with what the TensorFlow versus the PyTorch design points was that TensorFlow is kind of difficult to use for researchers, but it was actually pretty good for deployment. PyTorch is really good for researchers, and kind of not super great for deployment, right? And so I think we as an industry have been struggling. If you look at what deploying a machine learning model today means, it's that you'll have researchers who are, wicked smart, of course, but they're wicked smart at model architecture and data and calculus, and they're wicked smart in various domains. They don't want to know anything about the hardware deployment or C++ or things like that. Right? And so what's happened is you people who train the model, they throw it over the fence, and then you have people that try to deploy the model. Well, every time you have a team A does X, they throw it over the fence, and team Y does something. Team B does Y, like you have a problem, because of course it never works the first time. And so you throw it over the fence, they figure out, okay, it's too slow, it won't fit, doesn't use the right operator, the tool crashes, whatever the problem is, then they have to throw it back over the fence. And every time you throw a thing over a fence, it takes 3 weeks of project managers, meetings, and things like this. And so what we've seen today is that getting models in production can take weeks or months. It's not atypical, right? I talk to lots of people, and you talk about like VP of software at some internet company trying to deploy a model. They're like, why do I need a team of 45 people? It's so easy to train a model. Why can't I deploy it? Right? And if you dig into this, every layer is crawled down. So if you look at the language piece, this is tip of the iceberg. It's a very exciting tip of the iceberg for folks, but you've got Python on one side and C++ on the other side. Python doesn't really deploy. It can theoretically, technically in some cases, but often a lot of production teams will want to get things out of Python because they get their performance and control and whatever else. So Mojo can help with that. If you look at serving, we talk about gigantic models. Well, a gigantic model won't fit on one machine. Right? And so now you have this model, it's Python, it has to be written in C++. Now it also has to be carved up so that half of it runs on one machine, half of it runs on another machine. Or maybe it runs on 10 machines. And so now suddenly the complexity is exploding, right? And the reason for this is that if you look into PyTorch, these systems, they weren't really designed for this world. They were designed for back in the day when we were starting and doing things where it was a different, much simpler world. You went on Resonant 50 or some ancient model architecture like this. And it was a completely different world.
Trained on one GPU,
exactly.
doing
AlexNet,
GPU.
AlexNet, right? The major breakthrough, and the world has changed, right? And so now the challenge is that TensorFlow, PyTorch, these systems, they weren't actually designed for LLMs. Like that was not a thing. And so where TensorFlow actually has amazing power in terms of scale and deployment, things like that. And I think Google is, maybe not unmatched, but they're like incredible in terms of their capabilities and gigantic scale. Many researchers use PyTorch, right? And so PyTorch doesn't have those same capabilities. It's what Modular is. Now, if you take a step back and say, like, what is Modular doing? Right? So Modular has like a bitter enemy that we're fighting against in the industry. And it's one of these things where everybody knows it, but nobody is usually willing to talk about it.
The bitter enemy.
The bitter thing that we have to destroy, that we're all struggling with, and it's like fish can't see water, is complexity.
Yes, complexity.
Right.
That was very close off.
Yeah. And so if you look at it, yes, it is on the hardware side.
Yes.
All these accelerators, all these software stacks that go with the accelerator, all these, like, there's massive complexity. You look at what's happening on the modeling side. Massive amount of complexity. Like, things are changing all the time. People are inventing. Turns out the research is not done. Right? And so people want to be able to move fast. Transformers are amazing, but there's a diversity even within transformers. And what's the next transformer, right? And you look into serving, also huge amounts of complexity. It turns out that all the cloud providers, right, have all their very weird but very cool hardware for networking, all this kind of stuff, and it's all very complicated. People aren't using it. If you look at classical serving, right, there's this whole world of people who know how to write high-performance servers with zero-copy networking, like all this fancy asynchronous I/O, and like all these fancy things in the serving community. Very little that has pervaded into the machine learning world. Right, and why is that? Well, it's because, again, the systems have been built up over many years. They haven't been rethought. There hasn't been a first principles approach to this. And so what Modular is doing is we're saying, okay, we've built many of these things, right? So I've worked on TensorFlow and TPUs and things like that. Other folks on our team like work on PyTorch Core. We've worked on Onyx Runtime. We've worked on many of these other systems. And so built systems like the Apple accelerators and all that kind of stuff. Like our team is quite amazing. And so one of the things that roughly everybody at Modular is grumpy about is that when you're working on one of these projects, you have a first order goal. Get the hardware to work. Get the system to enable one more model. Get this product out the door. Enable the specific workload or make it solve this problem for this product team. Right? And nobody's been given a chance to actually do that step back. And so we as an industry, we didn't take 2 steps forward. We took like 18 steps forward in terms of all this really cool technology across compilers and systems and runtimes and heterogeneous computing, like all this kind of stuff. And like all this technology has been, I wouldn't say beautifully designed, but it's been proven in different quadrants. When you look at Google with GPUs, massive, huge exaflops of compute strapped together into machines that researchers are programming in Python in a notebook. That's huge. That's amazing. Right? It's incredible. And so you look at the technology that goes into that, and the algorithms are actually quite general. And so lots of other hardware out there and lots of other teams out there don't have the sophistication or maybe the years working on it or the budget or whatever that Google does, right? And so they should be getting access to the same algorithms, but they just don't have it. So what Modular's doing is we're saying, cool, this is not researching. Like we've built auto tuning in many systems. We've built programming languages, right? And so like have implemented C++, have implemented Swift, we've implemented many of these things. And so, it's hard, but it's not research. And you look at accelerators, and we know there's a bunch of different weird kinds of accelerators, but they actually cluster together. Right? And you look at GPUs, well, there's a couple of major vendors of GPUs, and they maybe don't always get along, but their architectures are very similar. You look at CPUs. CPUs are still super important for the deployment side of things. We've seen new architectures coming out from all the cloud providers and things like this, and they're all super important to the world, right? But they don't have the 30 years of development that the entrenched people do, right? And so what Modular can do is we're saying, okay, all this complexity, like it's not bad complexity, it's actually innovation, right? And so it's innovation that's happening, and it's for good reasons. But I have sympathy for the core software people, right? I mean, again, I'm a generally a software person too. I love hardware, but software people want to build applications and products and solutions that scale over many years. They don't want to build a solution for one generation of hardware with one vendor's tools. And because of this, they need something that scales with them. They need something that works on cloud and mobile, right? Because their product manager said, "Hey, I want it to have lower latency and better for personalization," or whatever they decide, right? Products evolve, and so the challenge with the machine learning technology and the infrastructure we have today in the industry is that it's all these point solutions. And because there are all these point solutions, it means that as your product evolves, you have to switch technology stacks or switch to a different vendor. And what that does is that slows down progress.
So basically, a lot of the things we've developed in those little silos for machine learning tasks, you want to make that the first-class citizen of a general-purpose programming language that can then be compiled across all these kinds of hardware.
Well, so it's not really about a programming language. I mean, the programming language is a component of the mission. The mission is, our not literal, but our joking mission is to save the world from terrible AI software.
Excellent.
Okay. So if you look at this mission, you need a syntax. So yes, you need programming. And like we wouldn't have to build the programming language when it existed. Right? So if Python was already good enough, then cool, we just used it. We're not just doing very large scale, expensive engineering projects for the sake of it. Like it's to solve the problem, right? It's also about accelerators. It's also about exotic numerics and E16 and matrix multiplications and convolutions and like this kind of stuff. Within the stack, there are things like kernel fusion. It's a esoteric but really important thing that leads to much better performance and much more general research hackability together.
And that's enabled by the ASICs. That's enabled by certain hardware. So it's like, where's the dance between? There's several questions here. Like, how do you add a piece of hardware to this stack?
Yeah.
If a new piece of, like, if I have this genius invention of a specialized accelerator, how do I add that to the modular framework? And also, how does modular as a standard start to define the kind of hardware that should be developed?
Yeah. So let me take a step back and talk about status quo. Okay. And so if you go back to TensorFlow 1, PyTorch 1, this kind of time frame, and these all evolved and got way more complicated. So let's go back to the glorious simple days. Right? These things basically were CPUs and CUDA. And so what you do is you say, go do a dense layer. The dense layer has a matrix multiplication now. Right? And so when you say that, say, go do this big operation, matrix multiplication, and if it's on a GPU, kick off the CUDA kernel. If it's on a CPU, go do like an Intel algorithm or something like that, the Intel MKO. Okay? Now, that's really cool if you're either NVIDIA or Intel, right? But then more hardware comes in. Right? And on one axis, you have more hardware coming in. On the other hand, you have an explosion of innovation in AI. And so what happened with both TensorFlow and PyTorch is that the explosion of innovation in AI has led to, it's not just about matrix multiplication and convolution. These things have now like 2,000 different operators. But on the other hand, you have, I don't know how many pieces of hardware there are out there. It's a lot. Okay, it's not even hundreds. It's probably thousands. Okay, and across all of Edge and across like all the different things
that are used at scale.
Yeah, exactly. I mean,
so it's not just like
AI is everywhere. Yeah,
it's not a handful of GPU alternatives.
Correct.
It's
every phone, often with many different chips inside of it from different vendors. Right. Like it's AI is everywhere. It's a thing, right?
Why are they all making their own chips? Like, why is everybody making their own thing?
Well, so because
is that a good thing?
So Chris's philosophy on hardware, right? So my philosophy is that there isn't one right solution, right? And so I think that again, with the Moore's law, specialization happens.
Mm.
If you're training GPT-5, you want some crazy supercomputer data center thingy. If you're making a smart camera that runs on batteries, you want something that looks very different. If you're building a phone, you want something that looks very different. If you have something like a laptop, you want something that looks maybe similar but a different scale, right? And so AI ends up touching all of our lives, robotics, right? And like lots of different things. And so as you look into this, these have different power envelopes. There's different trade-offs in terms of the algorithms. There's new innovations in sparsity and other data formats and things like that. And so hardware innovation, I think, is a really good thing. And what I'm interested in is unlocking that innovation. There's also like analog and quantum, and like all the really weird stuff, right? And so if somebody can come up with a chip that uses analog computing and it's 100x more power efficient, think what that would mean in terms of the daily impact on the products we use. That'd be huge. Now, if you're building an analog computer, you may not be a compiler specialist. Right? These are different skill sets, right? And so you can hire some compiler people if you're running a company maybe. But it turns out these are really like exotic new generation of compilers. Like this is a different thing, right? So if you take a step back out and come back to what's the status quo, status quo is that if you're Intel or you're NVIDIA, you continue to keep up with the industry and you chase and okay, there's 1900 now, there's 2000 now, there's 2100, and you have a huge team of people that are like trying to keep up and tune and optimize. And even when one of the big guys comes out with a new generation of their chip, they have to go back and rewrite all these things, right? So really, it's only powered by having hundreds of people that are all like frantically trying to keep up. And what that does is that keeps out the little guys. Sometimes the not so little guys. The big guys are also just not in those positions. And so what has been happening, so a lot of, you talk about the rise of new exotic crazy accelerators, people have been trying to turn this from a let's go write lots of special kernels problem into a compiler problem. And so we and I contributed to this as well. we as an industry went into it like, let's go make this compiler problem phase, let's call it. Much of the industry is still in this phase, by the way, so I wouldn't say this phase is over. And so the idea is to say, look, okay, what a compiler does is it provides a much more general, extensible, hackable interface for dealing with the general case, right? And so within machine learning algorithms, for example, people figured out that, hey, if I do a matrix multiplication and I do a ReLU, right, the classic activation function, it is way faster to do one pass over data and then do the ReLU on the output while I'm writing out the data. Because ReLU is just the maximum operation, max 0. And so it's an amazing optimization to matmul, ReLU, squish together in one operation. Now I have matmul ReLU. Well, wait a second. If I do that, now I just went from having 2 operators to 3. But now I figure out, okay, well, there's a lot of activation functions. Leaky ReLU, like a million things that are out there, right? And so as I start fusing these in, now I get permutations of all these algorithms, right? So what the compiler people said, they said, hey, cool, well, I will go enumerate all the algorithms, I will enumerate all the pairs, and I will actually generate a kernel for you. And I think that this has been very, very useful for the industry. This is one of the things that powers Google GPUs, PyTorch 2's like rolling out really cool compiler stuff, with Triton, other technology, things like this. And so the compiler people are kind of coming into their fore and saying, like, awesome, this is a compiler problem, we'll compiler it. Here's the problem. Not everybody's a compiler person. I love compiler people, trust me, right? But not everybody can or should be a compiler person. It turns out that there are people that know analog computers really well, or they know some GPU internal architecture thing really well, or they know some crazy, sparse, numeric, interesting algorithm that is the cusp of research, but they're not compiler people. And so one of the challenges with this new wave of technology trying to turn out a compiler is, again, it's excluded a ton of people. And so you look at what does Mojo do? What does the modular stack do? It brings programmability back into this world. Like it enables, I wouldn't say normal people, but like a different kind of delightful nerd that cares about numerics or cares about hardware or cares about things like this to be able to express that in the stack and extend the stack without having to actually go hack the compiler itself.
To extend the stack on the algorithm side,
yeah,
and then on the hardware side.
Yeah. So again, go back to like the simplest example of int. Right? And so what both Swift and Mojo and other things like this did is we said, okay, pull magic out of the compiler and put it in standard library. Right? So what Modular's doing, the engine that we're providing, and like this very deep technology stack, right, which goes into heterogeneous runtimes and like a whole bunch of really cool things. This whole stack allows that stack to be extended and hacked and changed by researchers, by hardware innovators, by people who know things that we don't know. Because Modular has some smart people, but we don't have all the smart people. It turns out.
What are heterogeneous runtimes?
Yeah. So what is heterogeneous, right? So heterogeneous just means many different kinds of things together. Mm-hmm. So the simplest example you might come up with is a CPU and a GPU. Mm-hmm. And so it's a simple heterogeneous computer to say, I will run my data loading and preprocessing and other algorithms on the CPU. And then once I get it into the right shape, I shove it into the GPU. I do a lot of matrix multiplications and convolutions and things like this. And then I get it back out and I do some reductions and summaries and I shove it across the wire across the network to another machine. And so you've got now what are effectively 2 computers, a CPU and a GPU, talking to each other, working together in a heterogeneous system. But that was okay. You look at a modern cell phone. Modern cell phone, you've got CPUs. And they're not just CPUs. There's like big dot little CPUs, and so there's multiple different kinds of CPUs that are working together. They're multi-core. You've got GPUs. You've got neural network accelerators. You've got dedicated hardware blocks for media, so for video decode and JPEG decode, things like this. So you've got this massively complicated system. This isn't just cell phones. Every laptop these days is doing the same thing. And all of these blocks can run at the same time and need to be choreographed. Right? And so, again, one of the cool things about machine learning is it's moving things like data flow graphs and higher-level abstractions and tensors and these things that it doesn't specify, here's how to do the algorithm. It gives the system a lot more flexibility in terms of how to translate or map or compile it onto the system you have. And so what you need, bottomest part of the layer there is a way for all these devices to talk to each other. And so this is one thing that I'm very passionate about. I think I'm a nerd, but all these machines and all these systems are effectively parallel computers running at the same time, sending messages to each other. And so they're all fully asynchronous. Well, this is actually a small version of the same problem you have in a data center. And in a data center, you now have with different machines, sometimes very specialized, sometimes with GPUs or TPUs in one node, sometimes with disks in another node. And so you get a much larger scale heterogeneous computer. And so what ends up happening is you have this like multi-layer abstraction of hierarchical parallelism and hierarchical asynchronous communication. And making that, again, my enemy is complexity. By getting that away from being different specialized systems at every different part of the stack and having more consistency and uniformity, I think we can help lift the world and make it much simpler and actually get used.
But how do you leverage like the strengths of the different specialized systems? So we're looking inside the smartphone.
Yeah.
Like you're using what, like, I don't know, 5-6 computers essentially inside the smartphone. How do you, without trying to minimize the explicit, making it explicit which computers supposed to be used for which operation?
Yeah, so there's a pretty well-known algorithm, and what you're doing is you're looking at two factors. You're looking at the factor of sending data from one thing to another. So it takes time to get it from that side of the chip to that side of the chip, and things like this. And then you're looking at what is the time it takes to do an operation on a particular block. So take CPUs. CPUs are fully general. They can do anything, right? But then you have a neural net accelerator that's really good at matrix multiplications. And so you say, okay, well, if my workload is all matrix multiplications, I start up, I send the data over to the neural net thing, it goes and does matrix multiplications. When it's done, it sends me back the result. All is good, right? And so the simplest thing is just saying, do matrix operations over there. But then you realize you get a little bit more complicated because you can do matrix multiplications on GPU, you can do it on neural net accelerator, you can do it on CPU, and they'll have different trade-offs and costs. And it's not just matrix multiplication. And so what you actually look at is you look at, I have generally a graph of compute. I want to do a partitioning. I want to look at the communication, the bisection bandwidth, and like the overhead and the sending of all these different things, and build a model for this, and then decide, okay, it's an optimization problem. What do I place?
It's the old school theoretical computer science problem, scheduling. And then how does, presumably it's possible to somehow magically include auto-tune into this?
Absolutely. So, I mean, in my opinion, this is an opinion. This is not everybody would agree with this, but in my opinion, the world benefits from simple and predictable systems at the bottom that you can control. But then once you have a predictable execution layer, you can build lots of different policies on top of it. Right? And so one policy can be that the human programmer says, do that here, do that here, do that here, do that here, and like fully manually controls everything, and the system can just do it. Right? Then you quickly get into the mode of like, I don't want to have to tell it to do it.
Yeah.
And so the next logical step that people typically take is they write some code in heuristic. Oh, if it's a matrix multiplication, do it over there. If it's floating point, do it on the GPU. If it's integer, do it on the CPU. Like something like this. And then you then get into this mode of like people care more and more, and you say, okay, well, let's actually like make the heuristic better. Let's get into auto-tune. Let's actually do search of the space to decide, well, what is actually better. Right? Well, then you get into this problem where you realize it's not a small space. It's a many-dimensional, hyperdimensional space that you cannot exhaustively search. So, do you know of any algorithms that are good at searching very complicated spaces for?
Don't tell me you're going to turn this into a machine learning problem.
But then you turn it into a machine learning problem, and then you have a space of algorithms, ortho learning, like all these.
Can you include that into the stack, into the module stack?
Yeah.
Where does it sit? Where does it live? Is it a separate thing, or is it a part of the compilation?
So you start from simple empirical models, and so you can have full control, and you can have coarse-grained knobs that like nudge systems. You don't have to do this. But if you really care about getting best, the last ounce out of a problem, then you can use additional tools. And there, the cool thing is you don't want to do this every time you run a model. You want to figure out the right answer and then catch it. And once you do that, you can say, okay, cool. Well, I can get up and running very quickly. I can get good execution out of my system. I can decide if something's important. If it's important, I can go through a bunch of machines at it, do a big expensive search over the space using whatever technique I feel like it's related to the problem. And then when I get the right answer, cool, I can just start using it. And so you can get out of this this trade-off between, okay, am I going to like spend forever doing a thing, or do I get it right quickly and quality result? Like these are actually not in contention with each other if the system's designed to scale.
You started and did a little bit of a whirlwind overview of how you get 35,000x speed up or more over Python. Jeremy Howard did a really great presentation about sort of the basic. Look at the code. Here's how you get the speed up. Like you said, that's something we could probably developers can do for their own code to see how you can get this gigantic speed up. But can you maybe speak to the machine learning task in general? How do you make some of this code fast and specifics? And what would you say is the main bottleneck for machine learning tasks? So are we talking about matmul, matrix multiplication? How do you make that fast?
So, I mean, if you just look at the Python problem, right, you can say, how do I make Python faster? There's been a lot of people who have been working on the, okay, how do I make Python 2x faster, 10x faster, or something like that, right? And there's been a ton of projects in that vein. Right? Mojo started from the, what can the hardware do? Like, what is the limit of physics? What is the speed of light? What is the, like, how fast can this thing go? And then, how do I express that? Right? And so it wasn't anchored relatively on make Python a little bit faster. It's saying, cool, I know what the hardware can do, let's unlock it. Right? Now, when you
just say how gutsy that is to be in the meeting and opposed to trying to see how do we get the improvement. It's like, what can the physics do?
And maybe on a special kind of work, you look at that, what is the limit of physics? How fast can these things go? Right? When you start looking at that, typically it ends up being a memory problem. Right? So today, particularly with these specialized accelerators, the problem is that you could do a lot of math within them, but yet you get bottleneck sending data back and forth to memory, whether it be local memory or distant memory or disk or whatever it is. And that bottleneck, particularly as the training sizes get large, as you start doing tons of inferences all over the place, like that becomes a huge problem. Right? So again, what happened is we went through a phase of many years where people took the special case and hand-tuned it, tweaked it, tricked it out, and they knew exactly how the hardware worked, and they did the model, and they made it fast. Didn't generalize. And so you can make 50 or some, or something, and like you can do that. Right? It's very small. Right? But as the models get bigger, more complicated, as the machines get more complicated, it stops working. And so this is where things like kernel fusion come in. So what is kernel fusion? This is this idea of saying, let's avoid going to memory. And let's do that by building a new hybrid kernel, a numerical algorithm that actually keeps things in the accelerator instead of having to write all the way up to memory. What's happened with these accelerators now is you get the levels of memory. In a GPU, for example, you'll have global memory, local memory, and like all these things. If you zoom way into how hardware works, the register file is actually memory. So the registers are like a L0 cache. And so a lot of taking advantage of the hardware ends up being fully utilizing full power in all this capability. And this has a number of problems, right? One of which is, again, complexity disaster, right? There's too much hardware. Even if you just say, let's look at the chips from one line of like Apple or Intel or whatever it is, each version of the chip comes out with new features. They change things so that it takes more time or less time to do different things. You can't rewrite all the software whenever they change. Right. So this is where you need a much more scalable approach. This is what Mojo and what the modular stack provides this infrastructure, this system for factoring all this complexity and allowing people to express algorithms, auto-tuning, for example, express algorithms in a more portable way so that when a new chip comes out, you don't have to rewrite it all. So to me, like, I kind of joke, like, what is a compiler? There's many ways to explain that. Convert thing A and thing B, and convert source code to machine code. Like, you can talk about many things that compilers do. But to me, it's about a bag of tricks. It's about a system, a framework you can hang complexity. It's a system that can then generalize and can work on problems that are bigger than fit in one human's head, right? And so what that means, what a good stack, modular stack provides, is the ability to walk up to it with a new problem, and it'll generally work quite well. And that's something a lot of machine learning infrastructure tools and technologies don't have. Typical state of the art today is you walk up, particularly if you're deploying, if you walk up with a new model, you try to push it through the converter crashes. That's crazy. The state of ML tooling today is not anything that a C programmer would ever accept. Right? And it's always been this kind of flaky set of tooling that's never been integrated well, and it's been never worked together, and because it's not designed together. It's built by different teams, it's built by different hardware vendors, it's built by different systems, it's built by different internet companies that try to solve their problems. And so that means that we get this fragmented, terrible mess of complexity.
So in the specifics of, and Jeremy showed this, there's the vectorized function, which I guess is built into the into Mojo.
Vectorized, as it shows, what's in the library.
Into the library, standard library. Vectorized, parallelized. Vectorized is more low level, parallelized is higher level. There's the tiling thing, which is hard to demonstrate the auto-tune thing.
So think about this in like levels, hierarchical levels of abstraction. So at the very, if you zoom all the way into compute problem, you have one floating point. Right. So then you say, okay, I can do things one at a time in an interpreter. It's pretty slow. Right? So I can get to doing one at a time in a compiler. See, then I can get to doing 4 or 8 or 16 at a time with vectors. That's called vectorization. And you can say, hey, I have a whole bunch of different, what a multi-core computer is. It's basically a bunch of computers. Right? So they're all independent computers that can talk to each other and they share memory. And so now what parallelized does is says, okay, run multiple instances of this on different computers. And now they can all work together. Right? So what you're doing is you're saying, keep going out to the next level out. And as you do that, you're highlighting the advantages. So tiling is a memory optimization. Right? It says, okay, let's make sure that we're keeping the data close to the compute part of the problem instead of sending it all back and forth through memory every time I load a block.
And the size of the block size is all. That's how you get through the auto-tune to make sure it's optimized.
Yeah. Well, so all of the details matter so much. This is another funny thing about machine learning and high-performance computing that is very different than C compilers we all grew up with, where if you get a new version of GCC or a new version of Clang or something like that, maybe something will go 1% faster, right? And so compiler engineers are really, really, really hard to get 0.5% out of your C code, something like that. But when you're talking about an accelerator or an AI application where you're talking about these kinds of algorithms, and these are things people used to write Fortran, for example, right? If you get it wrong, it's not 5% or 1%. It can be 2x or 10x, right? If you think about it, you really want to make use of the full memory you have, the cache, for example. If you use too much space, it doesn't fit in the cache, and now you're going to be thrashing all the way back out to main memory. And these can be 2x, 10x, major performance. So this is where getting these magic numbers and these things right is really actually important.
So you mentioned that Mojo is a superset of Python. Can you run Python code as if it's Mojo code?
Yes. Yes. And this has two sides to it. So Mojo's not done yet. So I'll give you this thing. Mojo's not done yet. But already we see people that take small pieces of Python code, move it over, they don't change it, and you can get 12x speedups. Somebody was just tweeting about that yesterday, which is pretty cool, right? And again, interpreters, compilers, right? So without changing any code, also this is not JIT compiling or doing anything fancy. It's just basic stuff. Mojo will continue to grow out. As it grows out, it will have more and more and more features. And our North Star is to be a full superset of Python, and so you can bring over basically arbitrary Python code and have it just work. And it may not always be 12x faster, but it should be at least as fast and way faster. Now it'll take time to do that. Python is a complicated language. There's not just the obvious things, but there's also non-obvious things that are complicated. Like we have to be able to talk to C Python packages, that talk to the C API. There's a bunch of pieces.
But you have to, I mean, to make explicit the obvious and not be so obvious until you think about it. So, to run Python code, that means you have to run all the Python packages and libraries.
Yeah.
So that means what? What's the relationship between Mojo and C Python, the interpreter that's presumably would be tasked with getting those packages to work?
Yep. So in the fullness of time, Mojo will solve for all the problems and you'll be able to remove Python packages over and run them in Mojo
Without the C Python.
without C Python someday.
Yeah.
It's not today, but someday. And that'll be a beautiful day because then you'll get a whole bunch of advantages and you'll get massive speed ups.
So you can do that one at a time, right? You can move packages one.
Exactly. But we're not willing to wait for that. Python is too important. The ecosystem is too broad. We want to be able to build Mojo out. We also want to do it the right way without time, without intense time pressure. We're obviously moving fast, but and so what we do is we say, okay, well, let's make a C import an arbitrary existing package. Arbitrary, including like you write your own manual of this, whatever. It's not like standard like an arbitrary package, and import that using C Python. C Python already runs all the packages, right? And so what we do is we built an integration layer where we can actually use C Python, again, practical, to actually just load and use all these packages as they are. The downside of that is you don't get benefits of Mojo. So they run as fast as they do in the traditional C Python way. But what that does is that gives you incremental migration. So if you say, hey, cool, there's the Python ecosystem is fast, so all of it should just work. But there's certain things that are really important. So if I'm doing weather forecasting or something, well, I'm going to be able to load up data, I'm going to work with it, and then I have my own crazy algorithm inside of it. Normally I write that in C++. If I can write in Mojo and have one system that scales, well, that's way easier to work with.
Is it hard to do that, to have that layer that's running C Python? Because is there some communication back and forth?
Yes, it's complicated. I mean, this is what we do. So, I mean, we make it look easy, but it is complicated. But what we do is we use the C Python existing interpreter. So it's running its own bytecodes, and that's how it provides the compatibility. And then it gives us C Python objects, and we use those objects as is. And so that way, we're fully compatible with all the C Python objects and all the it's not just the Python part, it's also the C packages, the C libraries underneath them, because they're often hybrid. And so we can fully run and fully compatible all that. And the way we do that is that we have to play by the rules, right? So we keep objects in that representation when they're coming from that rule.
What's the representation that's being used?
In memory. We have to know a lot about how the C Python interpreter works. It has, for example, reference counting, but also different rules on how to pass pointers around and things like this. Super low level fiddly, and it's not like Python, it's like how the interpreter works. Okay? And so that gets all exposed out, and then you have to define wrappers around the low level C code. And so what this means is you have to know not only C, which is different from Python, obviously, not only Python, the wrappers, but the interpreter and the wrappers, and the implementation details, and conventions, and it's just this really complicated mess. And when you do that, now suddenly you have the bugger that bugs Python, you can't step into C code. So you have this two-world problem. Right? And so by pulling this all into Mojo, what you get is you get one world. You get the ability to say, cool, I have untyped, very dynamic, beautiful, simple code. Okay, I care about performance for whatever reason, right? There's lots of reasons you might care. And so then you add types, parallelize things, vectorize things, you can use these techniques, which are general techniques to solve a problem, and then you can do that by staying in the system. And if you're you have that one Python package is really important to you, you can move to Mojo to get massive performance benefits on that, and other advantages. If you like stack types, it's nice if they're enforced. Some people like that, right? Rather than being hints, so there's other advantages too. And then you can do that incrementally as you go.
So one different perspective on this would be why Mojo instead of making CPython faster or redesigning CPython?
Yeah, well, I mean, you could argue Mojo is redesigning CPython, but why not make CPython faster, better, and things like that? There's less people working. So actually, there's a team at Microsoft that is really improving. I think CPython 3.11 came out in October or something like that, and it was 15% faster, 20% faster across the board, which is pretty huge given how mature Python is and things like this. And so that's awesome. I love it. Doesn't run on GPU. It doesn't do AI stuff, like doesn't do vectors, doesn't do things. 20% is good, 35,000 times better, right? So like they're definitely. I'm a huge fan of that work, by the way, and it composes well with what we're doing. And so it's not like we're fighting or anything like that. It's actually just general. It's goodness for people, but it's just a different path. Right? And again, we're not working forwards from making Python a little bit better. We're working backwards from what is the limit of physics.
What's the process of porting Python code to Mojo? Is there what's involved in that process? Is there tooling for that?
Not yet. So we're missing some basic features right now, and so we're continuing to drop out new features like on a weekly basis. But at the fullness of time,
is it an automatable process?
So when we're ready, it will be very automated. Yes.
Is it automatable? Like, is it possible to automate in the general case, the Python to Mojo conversion?
Yeah. Well,
you're saying it's possible.
Well, so, and this is why, I mean, one of the reasons why we use tenants.
Yes.
Right. So, first of all, by being a superset,
yeah,
it's like C versus C++. Can you move C code to C++?
Yes.
Yeah. Right. And you can move C code to C++, and then you can adopt classes, you can adopt templates, you can adopt other references or whatever C++ features you want after you move C code to C++. Like you can't use templates in C, right? And so if you leave it as C, fine, you can't use the features, but it still works, right? And C and C++ could work together. And so that's the analogy, right? Now, here, right, there's not a Python is bad and then Mojo is good. Right? Mojo just gives you superpowers. And so if you want to stay with Python, that's cool. But the tooling should be actually very beautiful and simple because we're doing the hard work of defining a superset.
Right, so you're right. So there's several things to say there, but also the conversion tooling should probably give you hints as to like how you can do the code.
And then exactly. Once you're in the new world, then you can build all kinds of cool tools to say like, hey, you should adopt this feature. And we haven't built those tools yet, but I fully expect those tools will exist, and you can quote unquote, modernize your code or however you can. Right? So, I mean, one of the things that I think is really interesting about Mojo is that there have been a lot of projects to improve Python over the years. Everything from getting Python to run on the Java virtual machine, PyPy, which is a JIT compiler. There's tons of these projects out there that have been working on improving Python in various ways. They fall into one or two camps. So PyPy is a great example of a camp that is trying to be compatible with Python. Even there, not really. It doesn't work with all the C packages and stuff like that. But they're trying to be compatible with Python. There's also another category of these things where they're saying, well, Python is too complicated. And I'm going to cheat on the edges, and it's like integers in Python can be an arbitrary size integer. If you care about fitting in going fast on a register on a computer, that's really annoying, right? So you can choose two paths. Right? Say, well, people don't really use big integers that often, therefore I'm going to just not do it, and it'll be fine. Not a Python superset. Or you can do the hard thing and say, okay, this is Python. You can't be a superset of Python without being a superset of Python. And that's a really hard technical problem, but it's, in my opinion, worth it. Right? And it's worth it because it's not about any one package, it's about this ecosystem. It's about what Python means for the world. And it also means we don't want to repeat the Python 2 to Python 3 transition. Like we want people to be able to adopt this stuff quickly. And so by doing that work, we can help with people.
Yeah, the challenge, it's really interesting technical philosophical challenge of really making a language a superset of another language. Breaking my brain a little bit.
Well, it paints you into corners. So again, I'm very happy with Python. Right? So joking, joking aside, I think that the indentation thing is not the actual important part of the problem, right? But the fact that Python has amazing dynamic metaprogramming features and they translate to beautiful static metaprogramming features, I think is profound. I think that's huge, right? So Python, I've talked with Guido about this. It's like it was not designed to do what we're doing. That was not the reason they built it this way, but because they really cared and they were very thoughtful about how they designed the language, it scales very elegantly in space. But if you look at other languages, for example, C and C++, right, if you're building a superset, you get stuck with the design decisions of the subset, right? And so, C++ is way more complicated because of C and legacy than it would have been if they would have theoretically designed a from scratch thing. And there's lots of people right now that are trying to make C++ better and resyntax C++. It's going to be great. We'll just change all the syntax. If you do that, now suddenly you have zero packages. You don't have to do that.
So what are the, if you could just linger on that, what are the biggest challenges of keeping that superset status? What are the things you're struggling with? Is it all boiled down to having a big integer?
No, I mean, it's
what are the other things?
Usually it's the long tail of weird things. So let me give you a war story. War story in this space is you go way back in time. Project I worked on is called Clang.
Mm-hmm.
Clang, what it is C++ parser, right? And when I started working on Clang, it's been like 2006 or something, 2007, 2006, when I first started working, right? It's funny how time flies. I started that project, and I'm like, okay, well, I want to build a C parser, C++ parser for LLVM. It's going to be the world. GCC is yucky. This is me earlier times. It's yucky. It's unprincipled. It has all these weird features, like all these bugs. Like it's yucky. So I'm going to build a standard compliant C and C parser. It's going to be beautiful, amazing, well engineered, all the cool things that engineers has to do. And so I started implementing, building it out, and then I got to include standard IO.h. And all of the headers in the world use all GCC stuff. And so again, come back away from theory back to reality, right? I was at a fork in the road. I could have built an amazingly beautiful academic thing that nobody would ever use. Or I could say, well, it's yucky in various ways. All these design mistakes, accents of history, the legacy. At that point, GCC was like over 20 years old. Yeah. Now LLVM's over 20 years old, right? So it's funny how time catches up to you, right? And so you say, okay, well, what is easier, right? I mean, as an engineer, it's actually much easier for me to go implement long tail compatibility weird features, even if they're distasteful, and just do the hard work and like figure it out, reverse engineer, understand what it is, write a bunch of test cases, like try to understand behavior. It's way easier to do all that work as an engineer than it is to go talk to all C programmers and argue with them and try to get them to rewrite their code. Right? And
so that brings a lot more things.
Yeah. And you have realities like nobody actually even understands how the code works. This was written by the person who quit 10 years ago. Right? And so this software is kind of frustrating that way, but that's how the world works.
Right? Yeah, unfortunately, it can never be this perfect, beautiful.
Well, there are occasions in which you can build, you invent a new data structure or something like that. Or there's this beautiful algorithm that just like makes you super happy. Right? I love that moment. But when you're working with people, you're working with code and dusty code bases and things like this, right? It's not about what's theoretically beautiful. It's about what's practical, what's real, what people actually use. And I don't meet a lot of people that say, I want to rewrite all my code just for the sake of it.
Mm-hmm. By the way, there could be interesting possibilities, and we'll probably talk about it, where AI can help rewrite some code. That might be farther out in the future, but it's a really interesting one, how that could create more, be a tool in the battle against this monster of complexity that you mentioned. What? You mentioned Guido, the benevolent dictator for life of Python. What does he think about Mojo? Have you talked to him much about it?
I have talked with him about it. He found it very interesting. We actually talked with Guido before it launched, so he was aware of it before have a ton of respect for Guido for a bunch of different reasons. You talk about Walrus Operator, and like Guido is pretty amazing in terms of steering such a huge and diverse community and like driving it forward. And I think Python is what it is thanks to him. So to me, it was really important starting for Mojo to get his feedback and get his input and get his eyes on this. Right? Now, a lot of what Guido was and is, I think, concerned about is how do we not fragment the community? We don't want a Python 2 to Python 3 thing. Like that was really painful for everybody involved. And so we spent quite a bit of time talking about that and some of the tricks I learned from Swift, for example. So in the migration from Swift, we managed to like not just convert Objective-C into a slightly prettier Objective-C, which we did. We've then converted, not entirely, but almost an entire community to a completely different language. Right? And so there's a bunch of tricks you learn along the way that are directly relevant to what we do. So this is where, for example, you leverage CPython while bringing up the new thing. That approach is proven and comes from experience. And so Guido was very interested in, like, okay, cool. Like, I think that Python is really his legacy. It's his baby. I have tons of respect for that. Incidentally, I see Mojo as a member of the Python family. We're not trying to take Python away from Guido and from the Python family. And so, to me, it's really important that we're a good member of that community. And so, yeah, I think that, again, you would have to ask Guido this, but I think that he's very interested in this notion of, like, cool, Python gets beaten up for being slow. Maybe there's a path out of that. Right? And that, the future is Python, right? I mean, look at the far outside case on this, right? And I'm not saying this is Guido's perspective, but there's this path of saying, like, okay, well, suddenly Python can suddenly go all the places it's never been able to go before, right? And that means that Python can go even further, even more impact on the world.
So in some sense, Mojo could be seen as Python 3.0.
I would not say that. I think that would drive a lot of people really crazy.
Because of the PTSD of the 3.0 2.0.
I'm willing to annoy people about Max versus Vim,
Not that
versus Spaces.
That's that one.
I don't know. That might be a little bit far even for me. Like, my skin may not be that bad.
But the point is stuck to being superset and allowing all of these capabilities, I think, is the evolution of the language. It feels like an evolution of the language. So he's interested by the ideas that you're playing with, but also concerned about the fragmentation. So what are the ideas you've learned? What are you thinking about? How do you avoid fragmenting the community? Or the Pythonistas and the I don't know what to call the Mojo people. Magicians, I like it. Can coexist happily and share code, and basically just have these big code bases that are using CPython and more moving towards Mojo.
Well, so again, these are lessons I learned from Swift, and here we face very similar problems, right? In Swift, you have Objective-C, super dynamic. They're very different syntax, right? But you're talking to people who have large-scale code bases. I mean, Apple's got the largest scale code base for Objective-C code, right? And so, none of the companies, none of the iOS developers, none of the other developers want to rewrite everything all at once, and so you want to be able to adopt things piece at a time. And so a thing that I found that worked very well in the Swift community was saying, okay, cool. And this is when Swift was very young. You say, okay, you have 1 million line of code Objective-C app. Don't rewrite it all. But when you implement a new feature, go implement that new class using Swift. Right? So now this turns out is a very wonderful thing for an app developer, but it's a huge challenge for the compiler team and the system people that are implementing it. Right? This comes back to what is this trade-off between doing the hard thing that enables scale versus doing the theoretically pure and ideal thing. Right? And so Swift had adopted and built a lot of different machinery to deeply integrate with Objective-C. And we're doing the same thing with Python. Right? Now, what happened in the case of Swift is that Swift as a language got more and more mature over time, right? And incidentally, Mojo is a much simpler language than Swift in many ways, and so I think that Mojo will develop way faster than Swift for a variety of reasons. But as the language gets more mature, in parallel with that, you have new people starting new projects, right? So when the language is mature and somebody's starting a new project, that's when they say, okay, cool, I'm not dealing with on the lines of code. I'll just start and use the new thing for my whole stack. Now the problem is, again, you come back to more communities and more people that work together. You build a new subsystem or a new feature, a new thing in Swift, or you build a new thing in Mojo. Then you want to end up being used on the other side, right? And so then you need to work on integration back the other way. So it's not just when we're talking Python, it's also Python and Mojo. Right? And so what I would love to see, I don't want to see this next month, right? But what I want to see over the course of time is I would love to see people that are building these packages, like NumPy or TensorFlow, or these packages that are half Python, half C++. And if you say, okay, cool, I want to get out of this Python C++ world into a unified world, and so I can look at Mojo, but I can't give up all my Python clients. There's like these levers get used by everybody. They're not all going to switch all once, and maybe never, right? So the way we should do that is we should bend Python interfaces to the Mojo types. And that's what we did in Swift. It worked great. I mean, it's a huge implementation challenge for the compiler people, right? But there's only a dozen of those compiler people, and there are millions of users. And so it's a very expensive, capital-intensive, skill set intensive problem, but once you solve that problem, it really helps adoption. It really helps the community progressively adopt. And so I think that this approach will work quite well with the Python and the Mojo world.
So for a package, port it to Mojo and then create a Python interface.
Yep.
So how do to learn on these packages, NumPy, PyTorch, TensorFlow?
Yeah.
How do they play nicely together? So is Mojo supposed to be, let's talk about the machine learning one. Is Mojo kind of vision to replace PyTorch and TensorFlow, to incorporate it? What's the relationship in this?
All right, so take a step back. So I wear many hats. So you're angling it on the Mojo side. Mojo is a programming language, and so it can help solve the C++, Python view set.
The fire emoji got me. I'm sorry. We should be talking modular. Yes.
Okay. So the fire emoji is amazing. I love it. It's a big deal. The other side of this is the fire emoji is in service of solving some big AI problems, right? And so the big AI problems are again this fragmentation, this hardware nightmare, this explosion of new potential, but it's not getting felt by the industry, right? And so when you look at how does the modular engine help TensorFlow and PyTorch, right? It's not replacing them, right? In fact, when I talk to people, again, they don't like to rewrite all their code. You have people that are using a bunch of PyTorch, a bunch of TensorFlow. They have models that they've been building over the course of many years, right? And when I talk to them, there's a few exceptions, but generally they don't want to rewrite all their code, right? And so what we're doing is we're saying, okay, well, you don't have to rewrite all your code. What happens is the modular engine goes in there and goes underneath TensorFlow and PyTorch. It's fully compatible. It just provides better performance, better predictability, better tooling. It's a better experience that helps lift TensorFlow and PyTorch and make them even better. I love Python, I love TensorFlow, I love PyTorch. Right? This is about making the world better because we need AI to improve.
But if I have a process that trains a model and I have a process that performs inference on that model and I have the model itself, what should I do with that in the long arc of history? In terms of if I use PyTorch to train it, should I rewrite stuff in Mojo with that if I care about performance?
Well, so I mean, again, it depends. So if you care about performance, then writing it in Mojo is going to be way better than writing it in Python. But if you look at LLM companies, for example, if you look at OpenAI, rumored, and you look at many of the other folks that are working on many of these LLMs and other like innovative machine learning models. On the one hand, they're innovating in the data collection, model billions of parameters, and the model architecture, and the RLE, HF, and the like all the cool things that people were talking about. But on the other hand, they're spending a lot of time writing CUDA kernels, right? And so you say, wait a second, how much faster could all this progress go if they were not having to handwrite all these CUDA kernels? Right? And so there are a few technologies that are out there, and people have been working on this problem for a while. And they're trying to solve subsets of the problem, again, kind of fragmented space. And so what Mojo provides for these kinds of companies is the ability to say, cool, I can have a unifying theory. And again, the better together the unifying theory, the 2-world problem or the 3-world problem, the n-world problem. Like this is the thing that is slowing people down. And so as we help solve this problem, I think it would be very helpful for making this whole cycle go faster.
So obviously we talked about the transition from Objective-C to Swift and design this programming language. And we've also talked quite a bit about the use of Swift for machine learning context. Why have you decided to move away from maybe an intense focus on Swift in machine learning context versus sort of deciding a new programming language that happens to be a super
You're saying this isn't a rational set of life choices I made?
Did you go to the desert? Did you meditate? Okay. Right. No, it was bold. It was bold and needed, and I think I mean it's just bold. And sometimes to take those leaps is a difficult leap to take.
Yeah. Well, so okay. I mean, I think there's a couple of different things. So actually, I left Apple back in 2017, January 2017. So it's been a number of years that I left Apple. And the reason I left Apple was to do AI. Okay, so and again, I won't come on Apple and AI, but the at the time, right, I wanted to get into and understand the technology, understand the applications, the workloads, and so I was, okay, I'm going to go dive deep into applied and AI, and then the technology underneath it, right? I found myself at Google.
And that was like when TPUs were working.
Exactly. So I found myself at Google, and Jeff Dean, who's a rock star, as you know, right? And in 2017, TensorFlow was like really taking off and doing incredible things. And I was attracted to Google to help with TPUs, right? TPUs are an innovative hardware accelerator platform. Have now, I mean, proven massive scale and like done incredible things, right? And so one of the things that this led into is a bunch of different projects, which I'll skip over, right? One of which was this Swift for TensorFlow project, right? And so that project was a research project. And so the idea of that is say, okay, well, let's look at innovative new programming models where we can get a fast programming language, we can get automatic differentiation into language, let's push the boundaries of these things in a research setting. Right? Now, that project, I think, lasted 2-3 years. There's some really cool outcomes of that. So one of the things that's really interesting is I published a talk at an LLVM conference in 2018. It seems like so long ago. About graph program abstraction, which is basically the thing that's in PyTorch 2. And so PyTorch 2, with all this DynamoRio thing, is all about this graph program abstraction thing from bytecode. So a lot of the research that was done ended up pursuing and going out through the industry and influencing things. And I think it's super exciting and awesome to see that. But the Swift for TensorFlow project itself did not work out so good. And so there's a couple of different problems with that. One of which is that you may have noticed Swift is in Python. There's a few people that write Python code.
Yes.
And so it turns out that all of ML is pretty happy with Python.
It's actually a problem that other programming languages have as well, that they're not Python. We'll probably maybe briefly talk about Julia, which is a very interesting, beautiful programming language, but it's not Python.
Exactly. Well, and so like if you're saying I'm going to solve a machine learning problem where all the programmers are Python programmers, and you say the first thing you have to do is switch to a different language. Well, your new thing may be good or bad or whatever, but if it's a new thing, the adoption barrier is massive.
It's still possible.
Still possible? Yeah, absolutely. The world changes and evolves, and there's definitely room for new and good ideas, but it just makes it so much harder. And so, lesson learned, Swift is not Python, and people are not always in search of like learning a new thing for the sake of learning a new thing. And if you want to be compatible with all of this code, turns out, meet the world where it is. Second thing is that, a lesson learned is that Swift, as a very fast and efficient language, kind of like Mojo, but a different take on it still, really worked well with eager mode. And so eager mode is something that PyTorch does, and proved out really well, and it enables really expressive and dynamic, easy to debug programming. TensorFlow at the time was not set up for that. Let's say that was not.
Timing is also important.
Yeah, TensorFlow is a good thing. It has many strengths, but you could say Swift for TensorFlow is a good idea, except for the Swift and except for the TensorFlow part. So
because it's not Python and TensorFlow because it's not.
it wasn't set up for AI at the time. Yeah,
It was 1.0.
exactly. And so one of the things about that is that in the context of being a research project, I'm very happy with the fact that we built a lot of really cool technology. We learned a lot of things. I think the ideas went on to have influence on systems like PyTorch. A few people use that, I hear, right? And so I think that's super cool. And for me personally, I learned so much from it. Right? And I think a lot of the engineers on it also learned a tremendous amount. So, I think that that's just really exciting to see. And I'm sorry that the project didn't work out. I wish it did, of course, right? But it's a research project, and so you're there to learn from it.
It's interesting to think about the evolution of programming as we come up with these whole new set of algorithms in machine learning and artificial intelligence and what's going to win out. Because it could be a new programming language.
Yeah.
It could be, I just mentioned Julia. I think there's a lot of ideas behind Julia that Mojo shares. What are your thoughts about Julia in general?
So I will have to say that when we launched Mojo, one of the biggest things I didn't predict was the response from the Julia community, and so I was not. I mean, let me take a step back. I've known the Julia folks for a really long time. They were an adopter of LLVM a long time ago. They've been pushing state of the art in a bunch of different ways. Julia is a really cool system. I had always thought of Julia as being mostly a computing focused environment, and I thought that was its focus. I neglected to understand that one of their missions is to help make Python work end to end. And so I think that was my error for not understanding that, and so I could have been maybe more sensitive to that. But there's major differences between what Mojo is doing and what Julia is doing. So as you say, Julia is not Python. Right? And so one of the things that a lot of the Julia people came out and said is okay, well, if we put a ton of more energy and a ton more money or engineering or whatever to Julia, maybe that would be better than starting Mojo. Maybe that's true, but it still wouldn't make Julia Python. So if you work backwards from the goal of let's build something for Python programmers without requiring them to relearn syntax, then Julia just is there. Right? I mean, that's a different thing. Right? And so if you anchor on I love Julia and I want Julia to go further, then you can look at it from a different lens. But the lens we were coming at was, hey, everybody's using Python. Python syntax isn't broken. Let's take what's great about Python and make it even better. And so it's just a different starting point. So I think Julia is a great language. The community is a lovely community. They're doing really cool stuff, but it's just it's slightly different angle.
But it does seem that Python is quite sticky. Is there some philosophical almost thing you could say about why Python, by many measures, seems to be the most popular programming language?
Well, I can tell you things I love about it. Maybe that's one way to answer the question, right? So, huge package ecosystem, super lightweight and easy to integrate. It has very low startup time.
So what startup time? You mean
You
learning curve or what?
Yeah, so if you look at certain other languages, you say Go, it just takes Java, for example, takes a long time to compile all the things, and then the VM starts up and the garbage collector kicks in, and then it revs its engines, and then it can plow through a lot of internet stuff or whatever, right? Python is scripting. It just goes, right? Python has very low compile time. So you're not sitting there waiting. Python integrates in notebooks in a very elegant way that makes exploration super interactive and so awesome, right? Python is also, it's almost the glue of computing. Because it has such a simple object representation, a lot of things plug into it. That dynamic metaprogramming thing we were talking about also enables really expressive APIs. And so there's lots of reasons that you can look at technical things that Python has done and say okay, wow, this is actually a pretty amazing thing. And any one of those you can neglect. People will all just talk about notation and ignore the fundamental things. But then you also look at the community side, right? So Python owns machine learning. Machine learning is pretty big.
Yeah, and it's growing.
And it's growing, right? And it's growing in importance, right?
And there's a reputation and prestige to machine learning, to where if you're a new programmer, you're thinking about which programmer do I use. Well, I should probably care about machine learning. Therefore, let me try Python. And it kind of builds and builds and builds.
And you can go back before that. my kids learn Python. Right? Not because I'm telling them to learn Python, but because
they would
well, no, right? Well, they also learn Scratch, right, and things like this too. But it's because Python is taught everywhere, right? Because it's easy to learn, right, and because it's pervasive. Right? And
back in my day, we learned Java and C++. Uphill both the directions. But yes, I guess Python is the main language of teaching software engineering in schools now.
Yeah, well, if you look at this, there's these growth cycles. If you look at what causes things to become popular and then gain in popularity, there's reinforcing feedback loops and things like this. And I think Python has done, again, the whole community has done a really good job of building those growth loops and help propel the ecosystem. And I think when you look at what you can get done with just a few lines of code, it's amazing.
So this kind of self-building loop is interesting to understand because when you look at Mojo, what it stands for, some of the features, it seems sort of clear that this is a good direction for programming languages to evolve in the machine learning community. But it's still not obvious that we will because of this, whatever the engine of popularity, of virality. Is there something you can speak to, like how do you get people to switch?
Yeah, well, I mean, I think that the viral growth is to switch people to Unicode.
Yeah,
I think the Unicode file extensions are one of that. That's going to be,
yeah. Tell the kids they can use the fire emoji.
Exactly. Well, in all seriousness, like I mean, I think there's really, I'll give you two opposite answers. One is, I hope if it's useful, if it solves problems, and people care about those problems being solved, they'll adopt the tech. Right? That's kind of the simple answer. And when you're looking to get tech adopted, the question is it solving a problem people need solved? And is the adoption cost low enough that they're willing to make the switch and cut over and do the pain up front so that they can actually do it, right? And so hopefully Mojo will be that for a bunch of people. And people building these hybrid packages are suffering. And it's really painful. And so I think that we have a good shot of helping people. But the other side is like, it's okay if people don't use Mojo. Like, it's not my job to say like everybody should do this. Like, I'm not saying Python is bad. Like, Python, CPython, like all these implementations, because Python ecosystem is not just CPython, it's also a bunch of different implementations with different trade-offs. And this ecosystem is really powerful and exciting, as are other programming languages. It's not like TypeScript or something is going to go away, right? And so there's not a winner-take-all thing. And so I hope that Mojo is exciting and useful to people, but if it's not, that's also fine.
But I also wonder what the use case for why you should try Mojo would be. So practically speaking, it seems like so there's entertainment, there's the dopamine hit of saying, holy shit, this is 10 times faster. This little piece of code is 10 times faster in Mojo.
Out of the box before you get to 35 times.
Exactly. I mean, just even that, I mean, that's the dopamine hit that every programmer sort of dreams of. The optimization. It's also the drug that can pull you in and have you waste way too much of your life optimizing and over optimizing, right? But so what do you see that would be like common? It's very hard to predict, of course, but if you look 10 years from now, Mojo is super successful. What do you think would be the thing where people like try it and then use it regularly and it kind of grows and grows and grows?
Well, so you talk about dopamine. And so, again, humans are not one thing. And some people love rewriting their code and learning things and throwing themselves in the deep end and trying out new things. In my experience, most people don't. Like, they're too busy. They have other things going on. By number, most people don't like this. I want to rewrite all my code. But even those people, the too busy people, the people that don't actually care about the language, they just care about getting stuff done, those people do like learning new things, right? And so you talk about the dopamine rush 10x faster. Wow, that's cool. I want to do that again. It's also like, here's the thing I've heard about in a different domain, and now I don't have to rewrite all my code. I can learn a new trick. Right? Well, that's called growth, And so one thing that I think is cool about Mojo, and again, those will take a little bit of time for example, the blog posts and the books and like all that kind of stuff develop and the languages get further along. So what we're doing, we talk about type, you can say, look, you can start with the world you already know you can progressively learn new things and adopt them where it makes sense. If you never do that, if you get really excited about it and want to go all the way in the deep end and want to rewrite everything and really whatever, that's cool, right? But I think the middle path is actually the more likely one, where it's you come up with a new idea and you discover, wow, that makes my code way simpler, way more beautiful, way faster, way whatever. And I think that's what people like. Now, if you fast forward and you said like 10 years out, right? I can give you a very different answer on that, which is, I mean, if you go back and look at what computers looked like 20 years ago, every 18 months they got faster for free. Right? 2x faster every 18 months. It was like clockwork. It was free, right? You go back 10 years ago, and we entered in this world where suddenly we had multi-core CPUs and we had GPUs. And if you squint and turn your head, what a GPU is, it's just a many-core, very simple CPU thing, kind of, right? And so, and 10 years ago, it was CPUs and GPUs and graphics. Today, we have CPUs, GPUs, graphics, and AI, because it's so important, because the compute is so demanding, because of smart cameras and the watches and all the different places that AI needs to work in our lives. It's caused this explosion of hardware. And so part of my thesis, or my belief of where computing goes, if you look out 10 years from now, it's not going to get simpler. Physics isn't going back where we came from. It's only going to get weirder from here on out. Right. And so to me, the exciting part of what we're building is it's about building that universal platform, which will continue to get weird. Again, I don't think it's avoidable, it's physics. But we can help lift people, scale, do things with it. You don't have to rewrite their code every time a new device comes out. And I think that's pretty cool. And so if Mojo can help with that problem, then I think that it will be hopefully quite interesting and quite useful to a wide range of people, because there's so much potential. Like there's so much, maybe analog computers will become a thing or something, right? And we need to be able to get into a mode where we can move this programming forward, but do so in a way where we're lifting people and growing them instead of forcing them to rewrite all their code and exploding them.
Do you think there'll be a few major libraries that go Mojo first?
Well, so I mean, modular engines like that. So again, come back to, like, we're not building Mojo because it's fun. We're building Mojo because we had to solve these accelerators.
That's the origin story. But I mean ones that are currently in Python.
Yeah, so I think that a number of these projects will. So one of the things, again, it's just my best guess, like each of the package maintainers also has, I'm sure, plenty of other things going on. People like really don't like rewriting code just for the sake of rewriting code. But sometimes, like, people are excited about like adopting a new idea. It turns out that while rewriting code is generally not people's first thing, it turns out that redesigning something while you rewrite it, using a rewrite as an excuse to redesign, can lead to the 2.0 of your thing that's way better than the 1.0. Right? And so I have no idea. I can't predict that. But there's a lot of these places where, again, if you have a package that is half C, half Python, right, you just solve the pain, make it easier to move things faster, make it easier to bug and evolve your tech. Adopting Mojo kind of makes sense to start with, and then it gives you this opportunity to rethink these things.
So the two big games are that there's a performance game, and then there's the portability to all kinds of different devices.
And there's safety. Right? So you talk about real types. I mean, I'm not saying this is for everybody, but that's actually a pretty big thing. Right?
Yeah, types are.
And so there's a bunch of different aspects of what value provides. And so I mean, it's funny for me. Like, I've been working on these kinds of technologies and tools for too many years now. But you look at Swift, right? And we talked about Swift TensorFlow, but Swift as a programming language. Swift's now 13 years old from when I started it.
Yeah.
So, because I started in 2010, I remember. And so that project, and I was involved with it for 12 years or something, right? That project has gone through its own really interesting story, right? And it's a mature, successful, used by millions of people system, right? Certainly not dead yet, right? But also, going through that story arc, I learned a tremendous amount about building languages, about compilers, about working with the community, and things like this. And so that experience, like, I'm helping channel and bring directly to other systems, same thing. Like, apparently I like building and iterating and evolving things. And so you look at this LLVM thing I worked on 20 years ago, you look at MLIR, right? And so a lot of the lessons learned in LLVM got fed into MLIR. And I think that MLIR is a way better system than LLVM was. And, Swift is a really good system, and it's amazing. But I hope that Mojo will take the next step forward in terms of design.
In terms of running Mojo, people can play with it. What's the Mojo Playground?
Yeah.
And from the interface perspective and from the hardware perspective, what's this incredible thing running on?
Yeah, so right now, here we are 2 weeks after launch.
Yes.
We decided that, okay, we have this incredible set of technology that we think might be good, but we have not given it to lots of people yet. And so we were very conservative and said, let's put it in a workbook so that if it crashes, we can do something about it. We can monitor and track that, right? And so, again, things are still super early, but we're having like one person a minute sign up with over 70,000 people 2 weeks in. It's kind of crazy.
So you can set up with the playground and you can use it in the cloud.
Yeah.
In your browser.
And so what that's running on, right? Yeah, what that's running on is that's running on cloud VMs. And so you share a machine with a bunch of other people, but it turns out there's a bunch of them now because there's a lot of people. And so what you're doing is you're getting free compute, you're getting to play with this thing in kind of a limited, controlled way so that we can make sure that it doesn't totally crash and be embarrassing. Right?
Yeah.
So now a lot of the feedback we've gotten is people want to download it locally, so we're working on that right now. And so that's
the goal, to be able to download it locally.
Yeah, that's what everybody expects. And so we're working on that right now. And so we just want to make sure that we do it right. I think this is one of the lessons I learned from Swift also, by the way, is that when we launched Swift, it feels like forever ago. It was 2014. And it was super exciting. The team, had worked on Swift for a number of years in secrecy. Okay. And we, 4 years into this development, roughly, of working on this thing, at that point, about 250 people at Apple knew about it. Okay, so it was secret. Apple's good at secrecy, and it was a secret project. And so we launched this at WWDC, a bunch of hoopla and excitement, and said, developers are going to be able to develop and submit apps to the App Store in 3 months. Yeah. Well, several interesting things happened, right? So first of all, we learned that, A, it had a lot of bugs. It was not actually production quality, and it was extremely stressful in terms of trying to get it working for a bunch of people. And so what happened is we went from 0 to, I don't know how many developers Apple had at the time, but a lot of developers overnight, and they ran into a lot of bugs, and it was really embarrassing, and it was very stressful for everybody. It was also very exciting. The other thing I learned is that when it happened, roughly every software engineer who did not know about the project at Apple, their head exploded when it was launched. Because they didn't know it was coming. And so they're like, wait, what is this? I signed up for Apple because I love C. Why is there a new thing? Right? And so now what that meant practically is that the push from launch to, first of all, to fall, but then to 2.0, 3.0, and all the way forward was super painful for the engineering team, like myself. It was very stressful. The developer community was very grumpy about it because they're like, okay, well, wait, so I'm changing and breaking my code, and I have to fix the bugs, and it was just a lot of tension and friction on all sides. There's a lot of technical debt in the compiler because you have to run really fast. You have to really take the thing, unblock the use case, and do the thing, and it's not right, but you never have time to go back and do it right. I'm very proud of the Swift team because they've come but they came so far and made so much progress over this time since launch. It's pretty incredible. So it's a very, very good thing. But I still want to do that again, right? And so
iterate more through the development process.
And so what we're doing is we're not launching it when it's hopefully 0.9 with no testers. We're launching it and saying it's 0.1, right? And so we're setting expectations of saying okay, well, don't use this for production. Right? If you're interested in what we're doing, we'll do it in a way, and we can do it together. But don't use it in production yet. We'll get there, but let's do it the right way. And I'm also saying we're not in a race. The thing that I want to do is build the world's best thing.
Yeah.
Right? Because if you do it right in this industry, it doesn't matter if it takes an extra 2 months. 2 months is worth waiting. And so doing it right and not being overwhelmed with that, this is again, war wounds, lessons learned, whatever you want to say, I think is absolutely the right thing to do. Even though right now people are very frustrated that it can't download it or it doesn't have feature X or something like this. And so,
What have you learned in a little bit of time since it's been released into the wild, and that people have been complaining about feature X or Y or Z? What have they been complaining about? What they have been excited about? Like almost like detailed things versus like big. I think everyone would be very excited about the big vision.
yeah. Well, so I mean, I've been very pleased. I mean, in fact, I mean, we've been massively overwhelmed with response, which is a good problem to have. It's kind of like a success disaster, in a sense, right? And so, what, I mean, if you go back in time when we started Modular, it was just a year and a half ago. So it's still a pretty new company, new team, small but very good team of people. Like we started with extreme conviction that there's a set of problems we need to solve, and if we solve it, then people will be interested in what we're doing. But again, you're building in basically secrets, right? You're trying to figure it out. The creation's a messy process. You're having to go through different paths and understand what you want to do and how to explain it. Often when you're doing disruptive and new kinds of things, just knowing how to explain it is super difficult, right? And so when we launched, we hope people would be excited, but I'm an optimist, but I'm also like don't want to get ahead of myself. And so when people found out about Mojo, I think their heads exploded, right? And here's I think a pretty credible team. They've taught some languages and some tools before, and so they have some lessons learned and are tackling some of the deep problems of the Python ecosystem and giving it the love and attention that it should be getting. And I think people got very excited about that. And so if you look at that, I mean, I think people are excited about ownership and taking a step beyond Rust. Right? There's people that are very excited about that. There's people that are excited about, just like I made Game of Life go 400 times faster, right? And things like that. And that's really cool. There are people that are really excited about I really hate stuff.
Like systems engineers, they're like stepping up. Like
So that's me, by the way. Also, but
I get third person excitement when people tweet, "Yeah, I made this at the end of life or whatever faster." You're like,
and also like I would also say that let me cast blame out to people who deserve it. These terrible people who convinced me to do some of this. Jeremy Howard, that guy.
So he's been pushing for this kind of thing.
He's wanted this for years.
Yeah, he's wanted this for a long
He's
time.
wanted this for years.
For people who don't know Jeremy Howard, he's like one of the most legit people in the machine learning community. He's a grassroots. He really teaches. He's an incredible educator. He's an incredible teacher, but also legit in terms of a machine learning engineer himself.
Yeah, so
he's been running the fast.ai and looking, I think, for exactly.
And so I mean, the first time, so I met Jeremy pretty early on. But the first time I sat up and I'm like, this guy is ridiculous, is when I was at Google and we were bringing up GPUs and we had a whole team of people and there was this competition called Dawn Bench of who can train ImageNet fastest. Right? Yes. And Jeremy and one of his researchers crushed Google by not through sheer force of the amazing amount of compute and the number of GPUs and stuff like that he just decided that progressive imagery sizing was the right way to train the model and fewer epoch faster and make the whole thing go vroom, right? Yep. And I'm like, this guy is incredible. So you can say, anyways, come back to, where's Mojo coming from? Chris finally it's all his fault.
But there's a kind of very refreshing, pragmatic view that he has of machine learning that I don't know if it's this mix of desire for efficiency, but ultimately grounded in the desire to make machine learning more accessible for a lot of people. I don't know what that is. I guess that's coupled with efficiency and performance, but it's not just obsessed about performance.
So a lot of AI and AI research ends up being that it has to go fast enough to get scaled. So a lot of people don't actually care about performance, particularly on the research side, until it allows them to have a bigger data set, right? And so suddenly now you care about distributed compute, like all these exotic HPC. Like you don't actually want to know about that. You just want to be able to do more experiments faster and do some bigger data sets, right? And so Jeremy has been really pushing the limits. And one of the things I'll say about Jeremy, and there's many things I can say about Jeremy because I'm a fan of his, but it fits in his head. And Jeremy actually takes the time, where many people don't, to really dive deep into why is the beta parameter of the atom optimizer equal to this, right? And he'll go survey it and understand what are all the activation functions and trade-offs and why is it there. Everybody that does, this model, pick that thing.
So the why, not just trying to provide, like really what is going on.
Right. And so as a consequence of that, like he makes time, so he spends time to understand things in depth that a lot of people don't. And as you say, he then brings it and teaches people. And his mission is to help lift. His website says making AI uncool again. Like it's about forget about the hype. It's actually practical and useful. Let's teach people how to do this. Now the problem Jeremy struggled with is that he's pushing the envelope. Right? Research isn't about doing the thing that is staying on the happy path or the well-paved road, right? And so a lot of the systems today have been these really fragile, fragmented things. They're special cases, it's happy path. And if you fall off the happy path, you get eaten by an alligator.
So what about so Python has this giant ecosystem of packages and it's a package repository. Do you have ideas of how to do that well in Mojo?
Yeah.
How to do a repository of packages?
Well, so that's another really interesting problem that I knew about, but I didn't understand how big the problem it was. Python packaging. A lot of people have very big pain points and a lot of scars with Python packaging.
Oh, you mean so there's some of the things
building and distributing and managing dependencies and versioning and all this stuff.
So from the perspective of if you want to create your own package,
and then or you want to build on top of a bunch of other people's packages and then they get updated and stuff like this. Now, I'm not an expert in this, so I don't know the answer. I think this is one of the reasons why it's great that we there's others involved. But one of the things I've heard from smart people who've done for this is that the packaging becomes a huge disaster when you get the Python and C together. And so if you have this problem where you have code split between Python and C, now not only do you have to package the C code, you have to build the C code. C doesn't have a package manager, right? C doesn't have a dependency versioning management system, right? And so I'm not experienced in the state of the art and all the different Python package managers, but my understanding is that's a massive part of the problem. And I think Mojo solves that part of the problem directly heads up. One of the things I think we'll do with the community, this isn't, again, we're not solving all the world's problems at once, we have to be kind of focused to start with, is that I think that we will have an opportunity to reevaluate packaging. Right? And so I think that we can come back and say, okay, well, given the new tools and technologies and the cool things we have that we built up, because we have not just syntax, we have an entirely new compiler stack that works in a new way. Maybe there's other innovations we can bring together and maybe we can help solve that problem.
So almost a tangent to that question from the user perspective with packages. It was always surprising to me that it was not easier to sort of explore and find packages. With pip install, and it feels it's an incredible ecosystem. It's just interesting that it wasn't made. It's still, I think, not made easier to discover packages to do like search and discovery.
Yeah, if you call it. Well, I mean, it's kind of funny because this is one of the challenges of these like intentionally decentralized communities. And so I don't know what the right answer is for Python. There are many people that, I don't even know the right answer for Mojo. There are many people that would have much more understanding behind it. But it's interesting if you look at this, right? Open source communities. There's Git. Git is a fully decentralized, and anybody can do it any way they want. But then there's GitHub, right? And GitHub, centralized, commercial in that case, right? Things really help pull together and help solve some discovery problems and help build a more consistent community. And so maybe there's opportunities for
something like a GitHub.
Yeah.
Although even GitHub, I might be wrong on this, but the search and discovery for GitHub is not that great. I guess they'll use Google search.
Yeah. Well, I mean,
Get,
maybe that's because GitHub doesn't want to replace Google search. Right? And I think there is room for specialized solutions to specific goals. So.
sure.
I don't know the right answer for GitHub even. They can go figure that out.
But the point is to have an interface that's usable, that's accessible to people of all different skill levels.
Well, and again, like what are the benefits of standards? Right? Standards allow you to build these next level of ecosystem, next level of infrastructure, and next level of things. And so, again, come back to I hate complexity. C plus Python is complicated. It makes everything more difficult to deal with. It makes it difficult to port, get around, work with. All these things get more complicated. So, I mean, I'm not an expert, but maybe Mojo can help a little bit by helping reduce the amount of C in this ecosystem and make it better scalable.
So any kind of packages that are hybrid in nature would be a natural fit for you to know that.
Which is a lot of them.
So, a lot of them, especially when they're doing some interesting stuff. Let me ask you about some features.
Yeah.
So we talked about, obviously, indentation as a type language or optionally typed. Whatever it is that.
It's either optionally or progressively. I think so people have very strong opinions on the right word to use.
Yeah.
I don't know.
I look forward to your letters. So there's the var versus let, but let is for constants. Var is an optional.
Yeah, var makes it readable, so you can raise up.
Then there's function flexibility.
Oh, okay. Oh.
I mean, there's a lot of sorts of happiness for me, but function overloading is, I guess, is that for performance, or is that why does Python not have function?
So I can speculate. So Python is a dynamic language. The way it works is that Python and Objective-C are actually very similar worlds if you ignore syntax. And so Objective-C is straight line derived from Smalltalk, a really venerable, interesting language that much of the world has forgotten about, but people that remember it love it generally. And the way that Smalltalk works is that every object has a dictionary. And the dictionary maps from the name of the function, the name of the value within an object, to its implementation. And so the way you call a method in Objective-C is you say, go look up, the way I call foo is I go look up foo, I get a pointer to the function back, and then I call it. Okay? That's how Python works. Right? And so now the problem with that is that the dictionary within a Python object, all the keys are strings, and it's a dictionary, so you can only have one entry per name.
You think it's as simple as that?
I think it's as simple as that. And so now, why do they never fix this? Like, why do they not change it to not be a dictionary? Why do they not change it? Like, the other things. Well, you don't really have to in Python because it's dynamic. And so you can say, I get into the function, now if I got past an integer, do some dynamic tests for it, string, thing. There's another additional challenge, which is even if you did support overloading, you're saying, okay, well, here's a version of the function for integers and a function for strings. Well, you'd have, even if you could put it in that dictionary, you'd have to have the caller to dispatch. And so every time you call a function, you'd have to say, like, is it an integer or string? And so you'd have to figure out where to do that test. And so in a dynamic language, overloading is something you don't have to have. So, but now you get into a type language, and in Python, if you subscript with an integer, then you get typically one element out of a collection. If you subscript with a range, you get a different thing out, right? And so often in type languages, you want to be able to express the fact that, cool, I have different behavior depending on what I actually pass into this thing. If you can model that, it can make it safer, more predictable, more faster, and all these things.
It somewhat feels safer, yes, but also feels empowering. Like in terms of clarity, that you don't have to design whole different functions.
Yeah, well, this is also one of the challenges with the existing Python typing systems, is that in practice, if you take subscript, like in practice, a lot of these functions, they don't have one signature. And they actually have different behavior in different cases. So this is why it's difficult to like retrofit this into existing Python code and make it play well with typing. You're gonna have to design for that.
Okay, so there's an interesting distinction that people that program Python might be interested in is def versus fn. So it's two different ways to define a function. and FN is a stricter version of def. What's the coolness that comes from the strictness?
So here you get into what is the trade-off with the superset.
Yes.
Okay, so superset, you have to, or you really want to be compatible. Like if you're doing a superset, you've decided compatibility with existing code is the important thing, even if some of the decisions they made were maybe not what you choose. Okay. So that means you put a lot of time in compatibility, and it means that you get locked into decisions in the past, even if they may not have been a good thing. You know, systems programmers typically like to control things, right? And they want to make sure that, not in all cases, of course, and even systems programmers are not one thing, right? But often you want predictability. And so one of the things that Python has, for example, is that if you find a variable, you just say x equals 4. I have a variable named x. Now I say some long name equals 17. Print out some long name. Oops, but I typoed it. Right. Well, the Python compiler doesn't know in all cases what you're defining and what you're using, and did you typo the use of it or the definition? Right. And so for people coming from typed languages, again, I'm not saying they're right or wrong, but that drives them crazy because they want the compiler to tell them, you typoed the name of this thing. Mm-hmm. And so what FN does is it turns on, as you say, it's a strict. And so it says, okay, well, you have to actually intentionally declare your variables before you use them. That gives you more predictability, more error checking, things like this, but you don't have to use it. And this is a way that Mojo is both compatible, because defs work the same way the defs have always worked, but provides a new alternative that gives you control and allows certain kinds of people that have a different philosophy to be able to express that and get that.
Well, usually, if you're writing Mojo code from scratch, you'll be using FN.
It depends on your mentality. Right? It's not that def is Python and FN is Mojo. Mojo has both. It loves both. Right? It really depends on. Yeah, exactly. Are you playing around and scripting something out? Is it a one-off throwaway script? Cool. Python is great.
I'll still be using FN.
Well, so
Yeah, I love strictness.
okay. Well, so
Control, power.
you also like suffering, right?
Yes.
How many pull-ups?
I've lost count.
Yeah, exactly.
At this point.
So I mean, that's cool. I love you for that.
Yeah.
And I love other people who like strict X, right? But I don't want to say that that's the right thing, because Python's also very beautiful for hacking around and doing stuff and research and these other cases where you may not want that.
See, I just feel like maybe I'm wrong on that, but it feels like strictness leads to debugging. Sometimes I'm going from, even on a small project, from zero to completion. It just, I guess it depends how many bugs you generate usually.
Well, so I mean, it's again lessons learned looking at the ecosystem. It's really, I think it's, if you study some of these languages over time, like the Ruby community, for example, Ruby is a pretty well developed, pretty established community, but along the path, they really invested in unit testing. So I think that the Ruby community has really pushed forward the state of the art of testing because they didn't have a type system that caught a lot of bugs in compile time, right? And so you can have the best of both worlds. You can have good testing and good types, right, and things like this. But I thought that was really interesting to see how certain challenges get solved. And in Python, for example, the interactive notebook kind of experiences and stuff like this are really amazing. If you typo something, it doesn't matter. It just tells you that's fine, right? So I think that the trade-offs are very different if you're building a large-scale production system versus you're building and exploring a notebook.
Speaking of control, the hilarious thing, if you look at code I write just for myself for fun, it's like littered with asserts everywhere.
Yeah.
it's a kind of
yeah, you like that.
it's basically saying the dictatorial way, this should be true now, otherwise everything stops.
Well, and that is a sign. I love you, man. But that is a sign of somebody who likes control.
Yeah.
And so, yes, I think that you'll like FN. I think you'll like Mojo.
Therapy session. Yes, I definitely. Speaking of asserts, exceptions are called errors. Why is it called errors?
So we use the same. We're the same as Python, right? But we implement it very differently, right? So if you look at other languages like Python, C++, our favorite, right? C++ has this thing called zero cost exception. Yeah. So this is, in my opinion, something to learn lessons from.
It's a nice polite way of
Yeah.
saying it.
And
Yeah.
so zero cost exception handling, the way it works is that it's called zero cost because if you don't throw an exception, there's supposed to be no overhead for the non-error code. And so it takes the error path out of the common path. It does this by making throwing an error extremely expensive. And so if you actually throw an error with a C++ compiler using exceptions, let's go look up in tables on the side and do all this stuff. And so throwing an error could be like 10,000 times more expensive than returning code faster. Also, it's called zero cost exception, but it's not zero cost by any stretch of the imagination because it massively bloats out your code, your binary. It also adds a whole bunch of different paths because of structures and other things like that. Reduce optimizations, all these effects. And so this thing that was called zero cost exceptions, it really ain't. Okay. Now, if you fast forward to newer languages, and this includes Swift and Rust and Go and now Mojo. Well, in Python, it's a little bit different because it's interpreted, and so like it's got a little bit of different going on. But if you look at languages, many newer languages say, okay, well, let's not do that zero cost exception handling thing. Let's actually treat throwing an error the same as returning a variant, returning either the normal result or an error. Now, programmers generally don't want to deal with all the typing machinery and like pushing around a variant. And so you use all the syntax that Python gives us, for example, try and catch, functions that raise and things like this. You raises, decorator on your function, stuff like this. And if you want to control that, and then the language can provide syntax for it. But under the hood, the way the computer executes it, throwing an error is basically as fast as returning something.
That's exactly something from a compiler perspective.
And so this is actually, I mean, it's a fairly nerdy thing, right? Which is why I love it. But this has a huge impact on the way you design your APIs. Right? So in C++, huge communities turn off exceptions because the cost is just so high. Right? And so the zero cost is so high, right? And so that means you can't actually use exceptions in many libraries. Right? And even for the people who do use it, well, okay, how and when do you want to pay the cost? If I try to open a file, should I throw an error? Well, what if I'm probing around looking for something, right? I'm looking it up in many different paths. Well, if it's really slow to do that, maybe I'll add another function that doesn't throw an error, returns an error code instead, and I have two different versions of the same thing, so it causes you to fork your APIs. And so, one of the things I learned from Apple and I still love is the art of API design is actually really profound. I think this is something that Python's also done a pretty good job at in terms of building out this large-scale package ecosystem. It's about having standards and things like this. And so, we wouldn't want to enter a mode where, there's this theoretical feature that exists in language, but people don't use it in practice. Now, I'll also say one of the other really cool things about this implementation approach is that it can run on GPUs and can run on accelerators and things like this. And that standard zero-cost exception thing would never work on an accelerator. And so this is also part of how Mojo can scale all the way down to like little embedded systems to run on GPUs and things like that.
Can you actually say about maybe is there some high-level way to describe the challenge of exceptions and how they work in code during compilation? So just this idea of percolating up a thing, an error.
Yeah. So the way to think about it is think about a function that doesn't return anything. Just the simple things, right? So you have function 1 calls function 2, calls function 3, calls function 4. Along that call stack, there are try blocks. And so if you have function 1 calls function 2 has a try block, and then within it, it calls function 3. Right? Well, what happens if function 3 occurs? Well, actually, start simpler. What happens if it returns? Well, if it returns, it's supposed to go back out and continue executing and then fall off the bottom of the try block. That's good. If the function throws, you're supposed to exit the current function and then get into the except clause, right? And then do whatever goes there and then keep following on. And so the way that a compiler like Mojo works is that the call to that function, which happens in the except clause, calls the function, and then instead of returning nothing, it actually returns a variant between nothing and an error. And so if you return normally, go off the bottom, if you return nothing. And if you throw an error, you return the variant that is an error. Right? So when you get the call, say, okay, cool, I called the function. Hey, I know locally I'm in the try block. Right? So I call the function and then I check to see what it returns. Aha, if it's that error thing, jump to the except line.
And that's all done for you behind the scenes.
Exactly. And so the compiler is always for you. And I mean, one of the things if you dig into how this stuff works in Python, because it's more complicated because you have finally blocks, which now you need to go into, do some stuff. Those can also throw and return.
Wait, what?
Yeah, I didn't like the stuff matter for compatibility. Like there's
nesting.
There's with clauses, and so with clauses are kind of like finally blocks with some special stuff going on, and so there's
Nesting in general, nesting of anything, nesting of function should be illegal.
well,
It just feels like it adds a level of complexity.
I'm merely an implementer, and so this is again one of the trade-offs you get when you decide to go superset is you get to implement a full fidelity implementation of the thing that you decided is good, and so yeah, I mean we can complain about the reality of the world. We can shake our fists, but
It always feels like you shouldn't be allowed to do that, like to declare functions inside functions. Inside functions.
oh, wait, what happened to the Lisp guy?
No, I understand that, but Lisp is what I used to do in college.
And so now you've grown up.
Yeah, we've all done things in college.
Wait a second. Wait a second.
I love Lisp. I love Lisp.
Okay, well, yeah, I was gonna say you're afraid of me irritating all learners.
Yeah,
Like,
it worked as a joke in my head.
yeah. So nested functions are, joking aside, actually really great and for certain things, right? And so these are also called closures. Closures are pretty cool, and you can pass callbacks, which is like patterns.
So speaking of which, I don't think you have nested functions implemented yet in Mojo.
We don't have lambda syntax, but we do have nested functions.
But there's a few things on the roadmap they have that would be cool to just fly through because it's interesting to see, how many features there are in the language, small and big.
Yeah.
You have to implement.
Yeah.
So first of all, there's tuple support, and that has to do with some very specific aspect of it, like the parentheses or not parentheses. That
Yeah, this is just a totally syntactic thing.
a syntactic thing. Okay, it's cool still. So keyword arguments and functions.
Yeah, so this is where in Python you can say call function x equals 4.
Yeah.
And x is the name of the argument.
That's a nice sort of documenting some type of feature.
Yeah, I mean, and again, this isn't rocket science to implement. It's just a lot.
It's just on the list.
The bigger features are things like traits.
Mm-hmm.
So traits are when you want to define abstract. So when you get into typed languages, you need the ability to write generics. So you want to say, I want to write this function, and I want to work on all things that are arithmetic-like. Well, what is arithmetic-like? Well, arithmetic-like is a categorization of a bunch of types. So again, you can define it in many different ways, and I'm not going to go into ring theory or something. But you can say it's arithmetic-like if you can add, subtract, multiply, divide, okay. Right? And so what you're saying is there's a set of traits that apply to a broad variety of types. And so there are all these arithmetic-like, all these tensors and floating point integer, and there's this category of types. And then I can define on an orthogonal axis algorithms that then work against types that have those properties. And so this is it's a widely known thing. It's been in Swift across many languages, so it's not Haskell, which is where everybody learns their tricks from. But we need to implement that, and that'll enable a new level of expressivity.
So classes.
Yeah, classes are a big deal.
It's a big deal. Still to be implemented. Like you said, lambda syntax. And there's like detailed stuff like whole module import, support for top level code and file scope, and then global variables also. So being able to have variables outside of the top level.
Well, and so this comes back to where Mojo came from and the fact that it's 0.1, right? And so Modular's building an AI stack, right? And an AI stack is a bunch of problems working with hardware and running high-performance kernels and doing this kernel fusion thing I was talking about and getting the most out of the hardware. And so we've really prioritized and built Mojo to solve Mojo's problem. Right now, our North Star is build out and support all the things. And so we're making incredible progress. By the way, Mojo's only like 7 months old. So that's another interesting thing.
But, I mean, part of the reason I wanted to mention some of these things is like there's a lot to do, and it's pretty cool how you just kind of. Sometimes you take for granted how much there is in the programming language, how many cool features you kind of rely on. And this is kind of a nice reminder when you lay it as a to-do list.
Yeah, and so, I mean, but also you look into, it's amazing how much is also there. I mean, you take it for granted that a value, if you define it, it will get destroyed automatically. But that little feature itself is actually really complicated, given the way the ownership system has to work, and the way that works within Mojo is a huge step forward from what Rust and Swift does.
But can you say that again? When the value you define it gets destroyed on
Yeah, so like say you have a string. You can see you define a string on the stack, or whatever that means, like in your local function. Right? And so you say, like, whether it be in a def, let's say it's just say x equals hello world. Right? Well, if your string type requires you to allocate memory, then when it's destroyed, you have to deallocate it. So in Python and in Mojo, you define that with the del method. Right? Where does that get run? Well, it gets run sometime between the last use of the value and the end of the program. Like in this, you now get into garbage collection, you get into like all these long debated, you talk about religions and trade-offs and things like this. This is a hugely hotly contested world. And if you look at C++, the way this works is that if you define a variable or a set of variables within a function, they get destroyed in a last in, first out order. So it's like nesting. Okay? This has a huge problem because if you define a big scope, you define a whole bunch of values at the top, and then you use them, and then you do a whole bunch of code that doesn't use them, they don't get destroyed until the very end of that scope. And so this also destroys tail calls, so good functional programming, right? This has a bunch of different impacts on, you talk about reference counting optimizations, things like this, a bunch of very low-level things. And so what Mojo does is it has a different approach on that from any language I'm familiar with, where it destroys them as soon as possible. And by doing that, you get better memory use, you get better predictability, you get tail calls that work, you get a bunch of other things, you get better ownership tracking. There's a bunch of these very simple things that are very fundamental, that are already built in there in Mojo today, that are the things that nobody talks about generally, but when they don't work right, you find out and complain about.
Is it trivial to know what's as soon as possible to delete a thing that's not going to be used again?
Yeah, well, I mean, it's generally trivial. It's after the last use. So if you find x as a string, and then you have some use of x somewhere in code
within that scope, maybe within the scope is accessible.
It's exactly. So you can only use something within its scope. So then it doesn't wait until the end of the scope to delete it. It destroys it after the last use.
But there's kind of some very eager machine that's just sitting there and deleting.
Yeah, it's all in the compiler, so it's not a which is also cool. And so, and this is actually non-trivial because you have control flow.
Yeah, right.
And so it gets complicated pretty quickly and stuff, but like getting this right is not.
So you have to insert delete like in a lot of places.
Potentially, yeah. And so the compiler has to reason about this. And so where, again, it's experience building languages and not getting this right. So again, you get another chance to do it. You get basic things like this right. But it's extremely powerful when you do that. Yeah. So there's a bunch of things like that that kind of combine together. And this comes back to you get a chance to do it the right way, do it the right way, and make sure that every brick you put is really good, so that when you put more bricks on top of it, they stack up to something that's beautiful.
But there's also, like, how many design discussions do there have to be about particular details, like implementation of particular small features? Because the features that seem small, I bet some of them might be like really require really big design decisions.
Yeah. Well, so I mean, let me give you another example. Python has a feature called async await. So it's a new feature. I mean, in the long arc of Python history, it's a relatively new feature, right? That allows way more expressive asynchronous programming. Okay. Again, this is Python's a beautiful thing, and they do things that are great for Mojo for completely different reasons. The reason that async await got added to Python, as far as I know, is because Python doesn't support threads. Okay, and so Python doesn't support threads, but you want to work with networking and other things like that that can block. I mean, Python does support threads; it's just not its strength. And so they added this feature called async await. It's also seen in other languages like Swift, JavaScript, and many other places as well. Async await in Mojo is amazing. We have a high performance heterogeneous compute runtime underneath the covers that then allows non-blocking I/O, so you get full use of your accelerator. That's huge, turns out. It's actually really an important part of fully utilizing shit. We talk about design discussions. That took a lot of discussions, and it probably will require more iteration. And so my philosophy with Mojo is that we have a small team of really good people that are pushing forward, and they're very good at the extremely deep, knowing how compiler and runtime and like all the low-level stuff works together. They're not perfect. Same thing as the Swift thing. Right? And this is where one of the reasons we released Mojo much earlier is so we can get feedback. And we've already renamed a keyword data community feedback. We use an ampersand, and now it's named. We're not renaming existing Python keywords. That breaks compatibility. Right? We're renaming things we're adding and making sure that they are designed well. We get usage experience. We iterate in the community because, again, if you scale something really fast and everybody writes all their goodness or using it in production, then it's impossible to change. And so you want to learn from people. You want to iterate and work on that early on. And this is where design discussion is actually quite important.
Could you incorporate an emoji into the language, into the main language?
Do you have a favorite one?
Well, I really like interesting humor, like Rothschild or whatever, rolling in the floor laughing. So that could be like a. What would that be? The use case for that, like an exception, throw an exception or some sort.
You could fully file a feature request.
Or maybe a hard one. It has to be a hard one.
People told me that I've been saying. So this is. I'm liking this.
I'm gonna use the viral nature of the internet to actually get this passed.
I mean, it's funny you come back to the flame emoji file extension, right? We have the option to use the flame emoji, which just even that concept comes, for example, the people who get up say, "No, I've seen everything."
Yeah, there's something. It kind of it's reinvigorating. It's like, oh, that's possible. That's really cool. For some reason, that makes everything else really exciting.
The world is ready for this stuff. And so, when we have a package manager, we clearly have to innovate by having the compiled package thing be the little box with the O on it, right? I mean, it has to be done.
It has to be done. Is there some stuff on the roadmap that you're particularly stressed about or excited about that you think about a lot?
I mean, as a today snapshot, which will be obviously tomorrow, the lifetime stuff is really exciting. So lifetimes give you safe references to memory without dangling pointers. And so this has been done in languages like Rust before, and so we have a new approach, which is really cool. I'm very excited about that. That'll be out to the community very soon. The traits feature is really a big deal. And so that's blocking a lot of API design. So there's that. I think that's really exciting. A lot of it is these kind of table stakes features. One of the things that is, again, also lessons learned with Swift is that programmers in general like to add syntactic sugar. And so it's like, oh, well, this annoying thing, like in Python, why can't I just use plus? Def plus, come on. Why can't I just do that, right? And so for a little bit of syntactic sugar, it makes sense, it's beautiful, it's obvious. We're trying not to do that. And so for two different reasons, one of which is that, again, lesson learned with Swift. Swift has a lot of syntactic sugar. Maybe good thing, maybe not, I don't know. But because it's such an easy and addictive thing to do, sugar makes your blood get crazy, right? The community will really dig into that and want to do a lot of that. And I think it's very distracting from building core abstractions. Second is we want to be a good member of the Python community. Right? And so we want to work with the broader Python community. And yeah, we're pushing forward a bunch of systems programming features, and we need to build them out to understand them. But once we get a long ways forward, I want to make sure that we go back to the Python community and say, okay, let's do some design reviews. Let's actually talk about this stuff. Let's figure out how we want this stuff all to work together. syntactic sugar just makes all that more complicated. So.
And list comprehension, like that's really complex. And my favorite, dictionaries.
Yeah, there's some basic stuff. 0.1.
0.1.
But nonetheless, it's actually still very interesting and useful.
As you mentioned, modular is very new. Mojo is very new. It's a relatively small team.
Yeah.
It's building up this gigantic stack, this incredible stack that's going to perhaps define the future of development of our AI overlords.
We just hope it will be useful.
As do all of us. So what have you learned from this process of building up a team? Maybe one question is, how do you hire great programmers, great people that operate in compiler, hardware, machine learning, software, interface design space,
Yeah.
and maybe are a little bit fluid in what they can do.
So
Language design.
So building a company is just as interesting in different ways as building a language. Like different skill sets, different things, but super interesting. And I've built a lot of teams, a lot of different places. If you zoom in from the big problem into recruiting, well, so here's our problem. Okay, I'll be very straightforward about this. We started modular with a lot of conviction about we understand the problems, we understand the customer pain points. We need to work back from the suffering in the industry, and if we solve those problems, we can be useful for people. The problem is that people we need to hire, as you say, are all these super specialized people who have jobs at big tech world. And I don't think we have product market fit in the way that a normal startup does. So we don't have product market fit challenges because right now everybody's using AI and so many of them are suffering and they want help. So again, we started with strong conviction. Now, again, you have to hire and recruit the best, and the best all have jobs. And so what we've done is we said, okay, well, let's build an amazing culture. Start with that. That's usually not something a company starts with. Usually you hire a bunch of people and then people start fighting and it's really gigantic mess. And then you try to figure out how to improve your culture later. My co-founder Tim in particular is super passionate about making sure that that's right. And we spent a lot of time early on to make sure that we can scale.
So can you comment, sorry, before we get to the second, what makes for a good culture?
There's many different cultures, and I've learned many things from
you work with several very unique, almost famously unique cultures.
And some of them I learned what to do, and some of them I learned what not to do. Okay, and so we want an inclusive culture. I believe in amazing people working together. And so I've seen cultures where you have amazing people and they're fighting each other. I see amazing people and they're told what to do. Like, thou shalt line up and do what I say. It doesn't matter if it's the right thing, do it. Right? And neither of these is and I've seen people that have no direction, they're just kind of floating in different places. And they want to be amazing, they just don't know how. And so a lot of it starts with have a clear vision. So we have a clear vision of what we're doing. And so I kind of grew up at Apple in my engineering life, right? And so a lot of the Apple DNA rubbed off on me. My co-founder Tim also is like a strong product guy. And so what we learned is, I started at Apple that you don't work from building cool technology. You don't work from come up with cool products and think about the features you'll have in the big checkboxes and stuff like this. Because if you go talk to customers, they don't actually care about your product. They don't care about your technology. What they care about is their problem. Right? And if your product can help solve their problems, well, hey, they might be interested in that. Right? And so if you speak to them about the problems, if you understand and you have compassion, you understand what people are working with, then you can work backwards to building an amazing product.
So the vision is
and then you can work backwards on solving the problem. And at Apple, it's I think pretty famously said that for every there's 100 no's for every yes. I would refine that to say that there's 100 not yets for every yes. But famously, if you go back to the iPhone, for example, right, the iPhone 1, many people laughed at it because it didn't have 3G, it didn't have copy and paste. Right? And then a year later, okay, finally it has 3G, but it still doesn't have copy and paste. It's a joke. Nobody will ever use this product, blah, 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 blah. Right? Well, year 3, it has copy and paste, and people stop talking about it. Right? And so being laser focused and having conviction and understanding what the core problems are and giving the team the space to be able to build the right tech is really important. Also, I mean, you come back to recruiting, you have to pay well, right? So we have to pay industry-leading salaries, benefits, this, that's a big piece. We're a remote-first company, and so we have to. So remote first has a very strong set of pros and cons. On one hand, you can hire people from wherever they are and attract amazing talent, even if they live in strange places or unusual places. On the other hand, you have time zones. On the other hand, you have like everybody on the internet will fight if they don't understand each other, and so we've had to learn how to like have a system where we actually fly people in, get the whole company together periodically, and get more troops together.
There's less intimacy to the in-person stuff. I guess you lose, but maybe you don't. Maybe if you get to know each other well, you trust each other.
Well, so when the pandemic first hit, I mean, I'm curious about your experience too. The first thing I missed was having whiteboards, right? Those design discussions where like I can high intensity work through things, get things done, work through the problem of the day, understand where we're on, figure out and solve the problem, move forward. But we figured out ways to work around that now. With, all these screen sharing and other things like that we do. The thing I miss now is sitting down at a lunch table with the team. The spontaneous things, like the coffee bar things, and the bumping into each other and getting to know people outside of the transactional solve a problem over Zoom.
And I think there's just a lot of stuff that I'm not an expert at this. I don't know who is. Hopefully, there's some people. There's stuff that somehow is missing on Zoom. Even with the whiteboard, if you look at that, if you have a room with one person at the whiteboard and there's like 3 other people at a table, there's first of all, there's a social aspect to that where you just shoot the shit a little bit, almost like
as people are just kind of coming in and
that. But also while like it's a breakout discussion that happens for like seconds at a time, maybe an inside joke. It's like this interesting dynamic that happens.
You're bonding.
Yeah, you're bonding, but through that bonding, you get the excitement. There's certain ideas that are like bullshit, and you'll see that in the faces of others that you won't see necessarily on Zoom. Something, it feels like that should be possible to do without being in person.
Well, I mean, in person is very different than it. It's worth it, but you can't always do it. And so, again, we're still learning. We're all still learning, like humanity, the reality, right? But what we found is that getting people together, whether it be a team or a whole company or whatever, is worth the expense because people work together and are happier after that. Like it just like there's a massive period of time where you're like, go out and things start getting frayed, put people together, and then you realize that we're all working together. We see things the same way. We work through the disagreement or the misunderstanding. We're talking across each other, and then we work much better together. And so things like that, I think, are really quite important.
What about people that are kind of specialize in very different aspects of the stack working together? What are some interesting challenges there?
Yeah, well, so I mean, there's lots of interesting people, as you can tell. Hard to deal with. But
you're one of the most lovely people.
So there's different philosophies in building teams. For me, and so some people say hire 10x programmers, and that's the only thing we do, whatever that means, right? What I believe in is building well-balanced teams that have people that are different in them. You have all generals and no troops, or all troops and no generals, or you have all people that think in one way and not the other way. What you get is you get a very biased and skewed and weird situation where people end up getting out. And so what I like to do is I like to build teams of people where they're not all the same. We do have teams that are focused on like runtime or compiler, GPU or accelerator, or whatever the speciality is, but people bring a different take and have different perspective, and I look for people that complement each other. And particularly if you look at leadership teams and things like this, you don't want everybody the same way. You want people bringing different perspectives and experiences, and so I think that's really important.
That's team, but what about building a company as ambitious as modular? What some interesting questions there?
Oh, I mean, so many. One of the things I love about Modular's the first company I built from scratch. One of the first things that was profound was I'm not cleaning up somebody else's mess, right? And so if you look at
And that's
so
liberating.
it's super liberating, and also the projects I built have not been core to the product of the company. Swift is not Apple's product, right? LAR is not Google's revenue machine, whatever. Right? It's not. It's important, but it's like working on the accounting software or the retail giant or something, right? It's like enabling infrastructure. And so modular, the tech we're building is here to solve people's problems. Like it is directly the thing. And so this is a really big difference. And what it means for me as a leader, but also for many of our engineers, is they're working on the thing that matters. And that's actually pretty, again, for sometimes like that's usually not the case, right? And so that's also pretty exciting and quite nice. But one of the ways that this manifests is it makes it easier to make decisions. And so one of the challenges I've had in other worlds is it's like, okay, well, community matters somehow for the goodness of the world. Like, sure, open source matters theoretically, but I don't want to pay for a t-shirt, right? Or some swag. Like, well, t-shirts cost $10 each. You can have 100 t-shirts for $1,000. To a megacorp, $1,000 is uncountably, can't count that low. Yes. Right? But justifying it and getting a t-shirt, you make like a t-shirt.
I would 100% like a t-shirt. Are you joking?
Fire emoji t-shirt. So,
I will treasure this.
is that a good
I will pass it down to my grandchildren.
And so, it's very liberating to be able to decide, I think that I should have a t-shirt. Right? And it becomes very simple. I like Lex.
This is awesome. So I have to ask you about one of the interesting developments with large language models is that they're able to generate code recently really well.
Yes.
To a degree that maybe I don't know if you understand, but I struggle to understand this because it forces me to ask questions about the nature of programming and the nature of thought, because the language models are able to predict the kind of code I was about to write so well.
Yep.
That it makes me wonder like how unique my brain is and where the valuable ideas actually come from. Like how much do I contribute in terms of ingenuity, innovation to code I write or design and that kind of stuff. When you stand on the shoulders of giants, are you really doing anything? And what LLMs are helping you do is they help you stand on the shoulders of giants in your program. There's mistakes. They're interesting that you learn from. But I would love to get your opinion first, high level, of what you think about this impact of large language models when they do program synthesis, when they generate code.
Yeah, well, so I don't know where it all goes. I'm an optimist. I'm a human optimist. I think that things I've seen are that a lot of the LLMs are really good at crushing leak code projects, and they can reverse link lists like crazy. Well, it turns out there's a lot of instances of that on the internet, and it's a pretty stock thing. And so if you want to see standard questions answered, LLMs can memorize all the answers, and that can be amazing. Also, they do generalize out from that, and so there's good work on that. But I think that in my experience building something like Mojo, where you talk about these things, you talk about building an applied solution to a problem. It's also about working with people. It's about understanding the problem. What is the product we want to build? What are the use cases? What are the customers? You can't just go survey all the customers because they'll tell you that they want a faster horse. Maybe they need a car, right? And so a lot of it comes into, I don't feel like we have to compete with LLMs. I think they'll help automate a ton of the mechanical stuff out of the way. And just like, I think we all try to scale through delegation and things like this. Delegating rote things to an LLM, I think, is an extremely valuable approach that will help us all scale and be more productive.
But I think it's a fascinating companion.
But I'd say I don't think that means that we're going to be done with coding.
So, but there's power in it as a companion. And,
Absolutely.
From there, I would love to zoom in onto Mojo a little bit. Do you think about that? Do you think about LLMs generating Mojo code and helping sort of, if When you design a new programming language, it almost seems like, man, it would be nice to sort of almost as a way to learn how I'm supposed to use these things for them to be trained on something.
Yeah. Good. So I do lead an AI company, so maybe there will be a Mojo LLM at some point. But if the question is like, how do we make a language to be suitable for LLMs?
Yeah.
I think that the cool thing about LLMs is you don't have to, right? And so if you look at what is English or any of these other terrible languages that we as humans deal with on a continuous basis, they're never designed for machines, and yet they're the intermediate representation. They're the exchange format that we humans use to get stuff done, right? And so these programming languages, they're an intermediate representation between the human and the computer, or the human and the compiler, roughly, right? And so I think the LLMs will have no problem learning whatever keyword we pick.
Maybe the fire emoji.
Maybe that's going to break it. It doesn't tokenize.
No, the reverse of that, it will actually enable it, because one of the issues I could see with being a superset of Python is there would be confusion about the gray area. So it would be mixing stuff. But
I'm a human optimist and also optimist. I think we can solve that problem. But you look at that and you say, okay, well, reducing the rote thing, right? Turns out compilers are very particular, and they really want things. They really want the indentation to be right. They really want the colon to be there on your else, or else it will complain, right? I mean, compilers could be better at this, but LLMs can totally help solve that problem. And so I'm very happy about the new predictive coding and copilot type features and things like this, because I think it will all just make it more productive.
It's still messy and fuzzy and uncertain, unpredictable. So, but is there a future you see, given how big of a leap GPT-4 was, where you start to see something like LLMs inside a compiler?
I mean, you could do that. Yeah, absolutely. I mean, I think that'd be interesting.
Is that wise?
Well, I mean, it would be very expensive. So compilers run fast and they're very efficient. LLMs are currently very expensive. There's on-device LLMs and there's other things going on, and so maybe there's an answer there. I think that one of the things that I haven't seen enough of is that, so LLMs to me are amazing when you tap into the creative potential of the hallucinations, right? And so if you're doing creative brainstorming or creative writing or things like that, the hallucinations work in your favor. If you're writing code that has to be correct because you're going to ship it in production, then maybe that's not actually a feature. And so I think that there has been research and there has been work on building algebraic reasoning systems and kind of like figuring out more things that feel like proofs. And so I think that there could be interesting work in terms of building more reliable at scale systems, and that could be interesting. But if you chase that rabbit hole down, the question then becomes, how do you express your intent to the machine? And so maybe you want LLM to provide the spec, but you have a different kind of net that then actually implements the code.
Right, so it's to use the documentation and inspiration versus the actual implementation.
Yeah, actually.
Since successful modular would be the thing that runs, I say so jokingly, our AI overlords, but AI systems that are used across, I know it's a cliche term, but Internet of Things, so across.
So I'll joke and say, like, AGI should be written.
Yeah, AGI should be written. You're joking, but it's also possible that it's not a joke. That a lot of the ideas behind Mojo's seems like the natural set of ideas that would enable at scale training and inference of AI systems. So I just have to ask about the big philosophical question about human civilization. The folks like Eliezer Yudkowsky are really concerned about the threat of AI. Do you think about the good and the bad that can happen at scale deployment of AI systems?
Well, so I've thought a lot about it, and there's a lot of different parts to this problem, everything from job displacement to Skynet and things like this. And so you could zoom into subparts of this problem. I'm not super optimistic about AGI being solved next year. I don't think that's going to happen personally.
So you have a kind of Zen-like calm about, because there's a nervousness because the leap of GPT-4 seems so big.
Sure.
It's like we're there's some kind of transition here. You're thinking.
Well, so I mean, there's a couple of things going on there. One is I'm sure GPT-5 and 7 and 19 will be also huge leaps. They're also getting much more expensive to run. And so there may be a limiting function in terms of just expense on one hand and train. That could be a limiter that slows things down. But I think the bigger limiter is outside of like Skynet takes over, and I don't spend any time thinking about that because if Skynet takes over and kills us all, then I'll be dead. So I don't worry about that. So you know, I mean, that's just okay. If other things to worry about, I'll just focus on.
Yeah,
I'll focus and not worry about that one. But I think that the other thing I'd say is that AI moves quickly, but humans move slowly. We adapt slowly. And so what I expect to happen is just like any technology diffusion, like the promise and then the application takes time to roll out. And so I think that I'm not even too worried about autonomous cars defining away all the taxi drivers. Remember, autonomy was supposed to be solved by 2020.
boy, do I remember.
So like I think that on the one hand we can see amazing progress, but on the other hand we can see that the reality is a little bit more complicated, and it may take longer to roll out than you might expect.
Well, that's in the physical space. I do think in the digital space, the stuff that's built on top of LLMs that runs, the millions of apps that can be built on top of them, and they could be run on millions of devices, millions of types of devices.
Yeah.
I just think that the rapid effect it has on human civilization could be truly transformative too.
Well, and there I think it depends on, are you an optimist or pessimist or masochist.
Just to clarify, optimist about human civilization.
Me too. And so I look at that as saying, okay, cool, what will AI do? Right. And so some people say, oh my God, it's going to destroy us all. How do we prevent that? I kind of look at it from is it going to unlock us all? Right. You talk about coding. Is it going to make so I don't have to do all the repetitive stuff? Well, suddenly that's a very optimistic way to look at it. And you look at what a lot of these technologies have done to improve our lives. And I want that to go faster.
What do you think the future of programming looks like in the next 10, 20, 30, 50 years? With LLMs and with Mojo, with modular, like the vision for devices, the hardware to compilers to the different stacks of software.
Yeah. So what I want, I mean, coming back to my arch nemesis, right? It's complexity, right? So again, me being the optimist, if we drop down complexity, we can make these tools, these technologies, these cool hardware widgets accessible to way more people, right? And so what I'd love to see is more personalized experiences, more things, the research getting into production instead of being lost at NeurIPS, right? And like these things that impact people's lives by entering products. And so one of the things that I'm a little bit concerned about is right now, the big companies are investing huge amounts of money and are driving the top line of AI capability forward really quickly. But if it means that you have to have $100 million to train a model or more, or $1 billion, right? Well, that's going to make it very concentrated with very few people in the world that can actually do this stuff. I'd much rather see lots of people across the industry be able to participate and use this. And you look at this, I mean, a lot of great research has been done in the health world, looking at like detecting pathologies and doing radiology with AI and like doing all these things. Well, the problem today is that to deploy and build these systems, you have to be an expert in radiology and an expert in AI. And if we can break down the barriers so that more people can use AI techniques, it's more like programming Python, which roughly everybody can do if they want to, right? Then I think that we'll get a lot more practical application of these techniques, a lot more nichier, cool but narrower domains. I think that's going to be really cool.
Do you think we'll have more or less programmers in the world? No.
Well, so I think we'll have more programmers, but they may not consider themselves to be programmers.
That'd be a different need.
Right? I mean, do you consider somebody that uses, I think that arguably the most popular programming language is Excel, right?
Yep.
And so do they consider themselves to be programmers? Maybe not. I mean, some of them make crazy macros and stuff like that, but what you mentioned Steve Jobs, it's the bicycle for the mind. It allows you to go faster, right? And so I think that as we look forward, right, what is AI? I look at it as hopefully a new programming paradigm. It's like object-oriented programming. Right? If you want to write a cat detector, you don't use forwards. It turns out that's not the right tool for the job, right? And so right now, unfortunately, because it's not unfortunately, but it's just kind of where things are. AI is this weird, different thing. It's not integrated into programming languages and the tool chains, and all the technology is really weird and it doesn't work right, and you have to babysit it, and every time you switch somewhere it's different. It shouldn't be that way. When you change that, when you fix it, so that suddenly, again, the tools, technologies can be way easier to use. You can start using them. And so that's what I'm excited about.
What kind of advice could you give to somebody in high school right now, or maybe early college, who's curious about programming and feeling like the world is changing really quickly?
Yeah.
What kind of stuff to learn? What kind of stuff to work on? Should they finish college? Should they go work at a company? Should they build a thing? What do you think?
Well, so one of the things I'd say is that you'll be most successful if you work on something you're excited by. And so don't get the book and read the book cover to cover and study and memorize and recite and flashcard. And go build something. Like, go solve a problem. Go build the thing that you want to exist. Go build an app. Go train a model. Like, go build something that actually use it and set a goal for yourself. If you do that, then there's the success, there's the adrenaline rush, there's the achievement, there's the unlock that I think is where, if you keep setting goals, and you keep doing things and building things, learning by building, it's really powerful. In terms of career advice, everybody's different. It's very hard to get generalized advice. I'll speak as a compiler nerd. If everybody's going left, sometimes it's pretty cool to the right.
Yeah.
And so just because everybody's doing a thing, it doesn't mean you have to do the same thing and follow the herd. In fact, I think that sometimes the most exciting paths of life lead to being curious about things that nobody else actually focuses on. And it turns out that understanding deeply parts of the problem that people want to take for granted makes you extremely valuable and specialized in ways that the herd is not. And so, again, there's lots of rooms for specialization, lots of rooms for generalists. There's lots of room for different kinds of parts of the problem. But I think that it's just because everybody's doing one thing doesn't mean you should necessarily do it.
And now the herd is using Python, so if you want to be a rebel, go check out Mojo and help Chris and the rest of the world fight the arch nemesis of complexity. Because simple is beautiful.
There you go.
Chris, you're an incredible person. You've been so kind to me ever since we met. You've been extremely supportive. I'm forever grateful for that. Thank you for being who you are, for being legit, for being kind, for fighting this really interesting problem of how to make AI accessible to a huge number of people, huge number of devices.
So Lex, you're a pretty special person, right? And so I think that one of the funny things about you is that besides being curious and pretty damn smart, you're actually willing to push on things. And I think that you've got an agenda to make the world think, which I think is a pretty good agenda.
It's a pretty good one. Thank you so much for talking to me, Chris.
Yeah, excellent.
Thanks for listening to this conversation with Chris Lapper. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Isaac Asimov. I do not fear computers. I fear the lack of them. Thank you for listening. We hope to see you next time.
The ribosome, like I mentioned a little while back, can make an elephant one molecule at a time. Ribosomes are slow. They run at about one molecule a second, but ribosomes make ribosomes. So you have choices of them, and that makes an elephant. In the same way, these little assembly robots I'm describing can make giant structures at heart because of the robot can make the robot. So more recently, to my students Amira and Miana, had a Nature Communication paper showing how this robot can be made out of the parts it's making. So the robots can make the robots, so you build up the capacity of robotic assembly.
Following is a conversation with Neil Gershon, the director of MIT's Center for Bits and Atoms, an amazing laboratory that is breaking down boundaries between the digital and physical worlds, fabricating objects and machines at all scales of reality, including robots and automata that can build copies of themselves and self-assemble into complex structures. His work inspires millions across the world as part of the maker movement to build cool stuff, to create, the very act that makes life so beautiful and fun. This is the Let's Read More podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Neil Gershon. You have spent your life working at the boundary between bits and atoms, so the digital and the physical. What have you learned about engineering and about nature reality from working at this divide, trying to bridge this divide?
I learned why von Neumann and Turing made fundamental mistakes. I learned the secret of life.
Yeah.
I learned how to solve many of the world's most important problems, which all sound presumptuous, but all of those things I learned at that.
Okay, so Turing and von Neumann, let's start there. Some of the most impactful, important humans who have ever lived in computing. Why were they wrong?
So I worked with Andy Gleason, who is Turing's counterpart. So just for background, if anybody doesn't know, Turing is credited with the modern architecture of computing, among many other things. Andy Gleason was his US counterpart. And you might not have heard of Andy Gleason, but you might have heard of the Hilbert problems. And Andy Gleason solved the fifth one. So he was a really notable mathematician. During the war, he was Turing's counterpart. Then von Neumann is credited with the modern architecture of computing, and one of his students was Marvin Minsky. So I could ask Marvin what Johnny was thinking, and I could ask Andy what Alan was thinking. And what came out from that, what I came to appreciate as background, I never understood the difference between computer science and physical science. But Turing's machine, that's the foundation of modern computing, has a simple physics mistake, which is the head is distinct from the tape. So in the Turing machine, there's a head that programmatically moves and reads and writes the tape. The head is distinct from the tape, which means persistence of information is separate from interaction with information. Then von Neumann wrote deeply and beautifully about many things, but not computing. He wrote a horrible memo called the first draft of a report on the EDVAC, which is how you program a very early computer. In it, he essentially roughly took Turing's architecture and built it into a machine. So the legacy of that is the computer somebody's using to watch this is spending much of its effort moving information from storage transistors to processing transistors, even though they have the same computational complexity. So in computer science, when you learn about computing, there's a ridiculous taxonomy of about 100 different models of computation, but they're all fictions. In physics, a patch of space occupies space, it stores state, it takes time to transit, and you can interact. That is the only model of computation that's physical. Everything else is a fiction. So I really came to appreciate that a few years back when I did a keynote for the annual meeting of the supercomputer industries, and then went into the halls and spent time with the supercomputer builders, and came to appreciate, see, if you're familiar with the movie The Metropolis, people would frolic upstairs in the gardens, and down in the basement, people would move levers. And that's how computing exists today, that we pretend software is not physical, it's separate from hardware. And the whole canon of computer science is based on this fiction that bits aren't constrained by atoms, but all sorts of scaling issues in computing come from that boundary, but all sorts of opportunities come from that boundary. And so you can trace it all the way back to Turing's machine making this mistake between the head and the tape. Von Neumann, he never called it von Neumann's architecture. He wrote about it in this dreadful memo, and then he wrote beautifully about other things to talk about. Now, to end a long answer, Turing and von Neumann both knew this. So all of the canon of computer scientists credits them for what was never meant to be a computer architecture. Both Turing and von Neumann ended their life studying exactly how software becomes hardware. So von Neumann studied self-reproducing automata, how a machine communicates its own construction. Turing studied morphogenesis, how genes give rise to form. They ended their life studying the embodiment of computation, something that's been forgotten by the canon of computing, but developed sort of off to the sides by a really interesting.
So there's no distinction between the head and the tape, between the computer and the computation. It is all computation.
Right. So I never understood the difference between computer science and physical science. And working at that boundary helped lead to things like my lab was part of doing, with a number of interesting collaborators, the first faster than classical quantum computations. We were part of a collaboration creating the minimal synthetic organism where you design life in a computer. Those both involve domains where you just can't separate hardware from software. The embodiment of computation is embodied in these really profound ways.
So the first quantum computation, synthetic life in the space of biology, the space of physics at the lowest level, the space of biology at the lowest level. So let's talk about CBA, Center of Bits and Atoms. What's the origin story of this MIT, legendary MIT center that you were a part of creating?
In high school, I really wanted to go to vocational schools where you learn to weld and fix cars and build houses. And I was told, no, you're smart. You have to sit in the room. And nobody could explain to me why I couldn't go to vocational school. I then worked at Bell Labs, this wonderful place before deregulation, legendary place. And I would get union grievances because I would go into the workshop and try to make something. They would say, no, you're smart. You have to tell somebody what to do. And it wasn't until MIT, and I'll explain how CBA started, but I could create CBA, that I came to understand this is a mistake that dates back to the Renaissance. So in the Renaissance, the liberal arts emerged. And liberal doesn't mean politically liberal. This was the path for liberation, birth of humanism. And so the liberal arts were the trivium, quadrivium, roughly language, natural science. And at that moment, what emerged was this dreadful concept of the illiberal arts. So anything that wasn't the liberal arts was for commercial gain and was just making stuff and wasn't valid for serious studies. And so that's why we're left with learning to weld wasn't a subject for serious study. But the means of expression have changed since the Renaissance. So micro machining or embedded coding is every bit as expressive as painting a painting or writing a sonnet. So never understanding this difference between computer science and physical science, the path that led me to create CBA with colleagues was I was what's called a junior fellow at Harvard. I was visiting MIT through Marvin because I was interested in the physics of musical instruments. This will be another slight digression. In Cornell, I would study physics, and then I would cross the street and go to the music department where I played the bassoon, and I would trim reeds and play the reeds, and they'd be beautiful, but then they'd get soggy. And then I discovered in the basement of the music department at Cornell was David Gordon, who you might not have heard of, but is legendary in electronic music because he was really the first electronic musician. So Bob Moog, who invented Moog synthesizers, was a physics student at Cornell, like me, crossing the street. And eventually he was kicked out and invented electronic music. David Gordon was the first musician who created electronic music. So he's legendary for people like Phil Glass and Steve Reich. And so that got me thinking about, I would behave as a scientist in the music department, but not in the physics department, but not in the music department. Got me thinking about what's the computational capacity of a musical instrument. And through Marvin, he introduced me to Todd Backover at the Media Lab. He's just about to start a project with Yo-Yo Ma that do a collaboration to instrument a cello, to extract Yo-Yo's data and bring it out into computational environments.
What is the computational capacity of the musical instrument? As we continue on this tangent, we'll shall return to CBA.
Yeah. So one part of that is to understand the computing. And if you look at like the finest time scale and length scale you need to model the physics, It's not heroic. A good GPU can do teraflops today. That used to be a national class supercomputer. Now it's just a GPU, and that's about, if you take time scales relevant to the physics, that's about the scale of the physics computing. For Yo-Yo, what was really driving it was he's completely unsentimental about the Strat. It's not that it makes some magical wiggles in the sound wave. It's performance as a controller, how he can manipulate it as an interface device.
Interface between what and what exactly?
Him and sound. And so what it led to was, I had started by thinking about ops per second, but Yo-Yo's question is really resolution and bandwidth. It's how fast can you measure what he does, and the bandwidth and the resolution of detecting his controls and then mapping them into sounds. And what he found was, if you instrument everything he does and connect it to almost anything, it sounds like Yo-Yo. That the magic is in the control, not in ineffable details in how the wood wiggles. And so with Yo-Yo and Todd, that led to a piece. And towards the end, I asked Yo-Yo what it would take for him to get rid of his Strat and use our stuff. And his answer was just logistics. It was, at that time, our stuff was like a rack of electronics and lots of cables and some grad students to make it work. Once the technology becomes as invisible as the Strat, then sure, absolutely, he would take it. And by the way, as a footnote on the footnote, an accident in the sensing of Yo-Yo's cello led to a $100 million a year auto safety business to control airbags in cars. I had to instrument the bow without interfering with it. So I set up local electromagnetic fields where I would detect how those fields interact with the bow he's playing. But we had a problem that his hand, whenever his hand got near these sensing fields, it would start sensing his hand rather than the materials on the bow. And I didn't quite understand what was going on with that interference. So my very first grad student ever, Josh Smith, did a thesis on tomography with electric fields, how to see in 3D with electric fields. Then through Todd, and at that point, research scientist in my lab, Joe Paradiso, it led to a collaboration with Penn Teller, where we did a magic trick in Las Vegas to contact Houdini. And sort of these fields are sort of like, contacting spirits. So we did a magic trick in Las Vegas. And then the crazy thing that happened after that was Phil Rittmuller came running into my lab. He worked with, this became with Honda and NEC, airbags were killing infants in rear-facing child seats. Cars need to distinguish a front-facing adult where you'd save the life versus a bag of groceries where you don't need to fire the airbag versus a rear-facing infant where you would kill it. And so the seat need to, in effect, see in 3D to understand the occupants. And so we took the Penn and Teller magic trick derived from Josh's thesis from Yo-Yo's cello to an auto show, and all the car companies said, great, when can we buy it? And so that became Ellis's, and it was a $100 million a year business making sensors. There wasn't a lot of publicity because it was in the car, so the car didn't kill you. So they didn't sort of advertise, we have nice sensors so the car doesn't kill you, but it became a leading auto safety sensor.
And that started from cello and the question of the computational capacity,
right.
Musical instrument.
Right. So now to get back to MIT, I was spending a lot of outside time at IBM research that had gods of the foundations of computing. There's amazing people there. And I'd always expected to go to IBM to take over a lab, but at the last minute pivoted and came to MIT to take a position in the Media Lab and start what became the predecessor to CBA. Media Lab is well known for Nicholas Negroponte. What's less well known is the role of Jerry Wiesner. So Jerry was MIT's president, before that Kennedy Science Advisor, grand old man of science. At the end of his life, he was frustrated by how knowledge was segregated. And so he wanted to create a department of none of the above, a department for work that didn't fit in departments. And the Media Lab, in a sense, was a cover story for him to hide a department. As MIT's president towards the end of his tenure, he said, I'm going to make a department for things that don't fit the departments. The departments would have screamed. But everybody was sort of paying attention to Nicholas creating the Media Lab, and Jerry kind of hid in it a department called Media Arts and Sciences. It's really the department of none of the above. And Jerry explaining that and Nicholas then confirming it is really why I pivoted and went to MIT. Because my students who help create quantum computing or synthetic life get degrees from Media Arts and Sciences, this department of none of the above. So that led to coming to MIT with Todd and Joe Paradiso and Mike Hawley. We started a consortium called Things That Think, and this was around the birth of the Internet of Things and RFID. But then we started doing things like work we can discuss that became the beginnings of quantum computing and cryptography and materials and logic and microfluidics. And those needed much more significant infrastructure and were much longer research arcs. So with a bigger team of about 20 people, we wrote a proposal to the NSF to assemble one of every tool to make anything of any size. Was roughly the proposal.
One of any tool to make anything of any size.
So there's usually nanometers, micrometers, millimeters, meters are segregated, input and output is segregated. We wanted to look just very literally at how digital becomes physical, physical becomes digital. And fortunately, got NSF on a good day, and they funded this facility of one of almost every tool to make anything. And so with a group of 4 colleagues that included Joe Jacobson, Mike Stein, Scott Canales, we launched CGA.
So we've been talking about nanoscale, microscale, nanostructures, microstructures, macrostructures, electron microscopes that focus on gene probes and nanostructures, laser, micro machining, and X-ray microtomography for microstructures, multi-axis machining, 3D printing for microstructures, and some examples. What are we talking about in terms of scale? How can we build tiny things and big things?
Yeah, so a well-equipped research lab has the sort of tools we're talking about, but they're segregated in different places. They're typically also run by technicians where you then have an account and a project in charge. All of these tools are essentially when you don't know what you're doing, not when you do know what you're doing. In that they're when you need to work across the scale. Where we don't, once projects are running in this facility, we don't charge for time, we don't make a formal proposal, schedule, and the users really run the tools, and it's for work that's kind of inchoate that needs to stand with this sort of analysis. And so, working the project today, ranges from developing septuple electronics for the lowest power computing to micromachining diamonds to take 10 million RPM bearings for molecular spectroscopy studies, up to exploring robots to build 100-meter structures in space.
Okay, can we just 3 things just mentioned? Let's start with the biggest. What are some of the biggest stuff you're thinking?
Sure. So, viewed from one direction, what we're talking about is a crazy random scheme, almost unrelated project. But if you rotate 90 degrees, it's really just a core thought over and over again. Just very literally how bits and atoms relate, how digital, it just right from digital to physical in many different domains. But it's really just the same idea over and over again. So to understand the biggest things, let me go back to bring in now Sean as well as Von Neumann. Yeah. So what is digital? The casual obvious answer is digital and not computer. But that's wrong. There's a much deeper answer, which is Claude Shannon at MIT wrote the best master's thesis ever. In his master's thesis, he invented our modern notion of digital logic. Where it came from was Van Evenbush was a grand old man at MIT. He created the post-war research establishment that led to the National he made an important mistake. But he also made the differential analyzer, which was the last grade analog computer. So it was a room full of gears and pulleys, and the longer it ran, the worse the answer was. And Shannon worked on it as a student, and he got so annoyed in his master's thesis he invented Guinness. But he then went on to Bell Labs, and what he did there was communication was beginning to expand. There was more demand for phone lines. And so there's a question about how many phone lines you could, phone messages you could send out wide. And you could try to just make it better and better. He asked a question nobody had asked, which is rather than make it better and better, what's the limit to how good? And he proved a couple things, but one of the main things he proved was a threshold theorem for channel capacity. And so what he showed was my voice to you right now is coming as a wave per second, and the further you get, the worse it sounds. But people watching this are getting it as infinite packets of data in a network. When the computer you're watching this gets the packets of information, it can detect and correct an error. And what Shannon showed is if the noise in the cable to the people watching them is above a threshold, but if the noise is below a threshold, for a linear increase in the energy representing our conversation, the error rate goes down exponentially. Exponentials are fast. There's very few of them in engineering. And the exponential reduction of error below a threshold, if you restore state, is called the threshold theorem. That's what led to digital. That means unreliable things are reliable. So Shannon did that for communication. Then von Neumann was inspired by that and applied it to computation. And he showed how an unreliable computer can operate reliably by using the same threshold property of restoring state. It was then forgotten many years. We had to rediscover it, in fact, in the quantum computing era, when things are very unreliable. But now to go back to how does this relate to the biggest insight? So in fabrication, MIT invented computer-controlled manufacturing of systems. Jet aircraft were just emerging. There was a limit to turning cranks on a machine, on a milling machine, to make parts for jet aircraft. Now, this is a messy story. MIT actually stole computer-controlled machines invented who thought it at MIT. Wanted to do a joint project with the Air Force, and MIT effectively stole it from them. So kind of a messy history. But that sounds like the birth of computer-controlled machines, like computer. There are a number of inventors of 3D printing. One of the companies spun off my lab by Max Lebowski's Form Lab, which is now a $1 trillion 3D printing company. That's the modern version. But all of that's analog, meaning the information is in the control computer. There's no information in materials. And so it goes back to John Edward Bush's analog computer. If you make a mistake in printing or machining, just the mistake of human. The real birth of computerized digital manufacturing is 4 billion years ago. That's the evolutionary age of the ribosome. So the way you're manufactured is there's a code that describes you, the genetic code. It goes to a micro machine, the ribosome, which is this molecular factory that builds the molecules that are you. The key thing to know about that is there are about 20 amino acids that get assembled. And in that machinery, it does everything Shannon and Rabbi taught us. We detect and correct errors. So if you mix chemicals, the error rate is about a part per 100. When you make elongated protein in the ribosome, it's about a part per 10 to the 4. When you replicate DNA, this extra level of error correction, it's a part per 10 to the 8. And so in the molecules that make you can detect and correct errors, and you don't need a ruler to make you. The geometry comes from the parts. So now, compare a child playing with Lego and a state-of-the-art 3D printer or computerized television. The tower made by a child is more accurate than a motor controller because the act of snapping the bricks together gives you a constraint on join bricks made out of distant materials. You don't need a ruler for Lego because the geometry locally gives you the parts. And there's no Lego trash. The parts have enough information to just assemble them. Those are exactly the properties of a digital code.
The unreliable is nuclear.
Yes, absolutely. So what the ribosome figured out 4 billion years ago is how to embody these properties, these digital properties, but not for communication or computation in effect, but for construction. So a number of projects in my lab have been studying the idea of digital materials. And think of a digital material just as Lego bricks. Well, the precise meaning is a discrete set of parts reversibly joined with global geometry determined from local constraints. And so it's digitizing materials. And so coming back to what are the biggest things I've made, my lab is working with the aerospace industry. So Spirit Aero and Boeing factories. They asked us for how to join composites. When you make a composite airplane, you make these giant wing and fuselage parts. And they asked us for a better way to stick them together because the joints were a place of failure. And what we discovered was instead of making a few big parts, if you make little loops of carbon fiber and you reversibly link them in joints, and you do it in a special geometry that balances being under constrained and over constrained with just the right degrees of freedom. We set the world record for the highest modulus ultralight material just by, in effect, making carbon fiber Lego. So lightweight materials are crucial for energy efficiency. Just let us make the lightest weight, high modulus material. We then showed that with just a few part types, we can tune the material properties, and then you can create really wild robots that instead of having a tool the size of a jumbo jet to make a jumbo jet, you can make little robots that walk on these cellular structures to build the structures, where they aerocorrect their position on the structure and they navigate on the structure. And so using all of that with NASA, we made morphing airplanes. A former student, Teddy Chung, mentioned that made a morphing airplane the size of NASA Langley's biggest wind tunnel. With Toyota, we've made super efficiency race cars. We're right now looking at projects with NASA to build these for things like space telescopes and space habitats, where the ribosome, who I mentioned a little while back, can make an elephant one molecule at a time. Ribosomes are slow; they run at about 1 molecule a second, but ribosomes make ribosomes. So you have thousands of them, not choices of them, and that makes an elephant. In the same way, these little assembly robots describe can make giant structures at heart because of the robot can make the robots. So more recently, two of my students, Mira and Miata, had a Nature communication paper showing how this robot can be made out of the parts it's making. So the robot can make the robot, so you build up the capacity of robotic assembly and self-replicate.
You leave on these what is a robot to walk around to do air correction? Where's the robot that can self-replicate the materials that is given? What does that look like? What are we talking about?
So
This is fascinating.
yeah, the answer is different at different length scales. So to explain that, in biology, primary structure is the code in the messenger RNA that says what the ribosome should show. Secondary structure are geometrical motifs, so things like helices or sheets. Tertiary structures are functional elements like electron donors or receptors. Quaternary structure is things like molecular motors that are moving by mouth or making the synapses of the brain. So there's that hierarchy of primary, secondary, tertiary, quaternary. Now, what's interesting is if you want to buy electronics today from a vendor, there are hundreds of thousands of types of resistors and capacitors or transistors. Huge inventory. All of biology is just based on this inventory of 20 parts in amino acids. And by composing them, you can create all of life. And so, as part of this digitization of materials, we're in effect trying to create something like amino acids for engineering, creating all of technology from 20 parts. As another discussion, I started Office for Science in Hollywood, and Martian, where I did a program with Bill Nye and a few others on how to actually build a civilization on Mars that they described in a way that I like. Is I was talking about how to go to Mars without budget, and the part it's sort of how to create life in non-living materials. So if you think about this primary, secondary, tertiary complex structure, in my lab we're doing that, but on different length scales for different purposes. So we're making micro robots out of like nanobricks, and to make the robots to build large-scale structures in space, the elements of the robots now are centimeters rather than micrometers. So the assembly robots for the bigger structures are there are the cells that make up the structure, but then we have functional cells, and so cells that can process and actuate. Each cell can like move 1 degree of freedom, or attach or detach, or process. Now, those elements I just described, we can make out of the still smaller parts. So eventually there's a hierarchy of the little parts make little robots that make bigger parts of bigger robots up to that hierarchy. And we can really get to nice. Right. Early on, I tried to go in a straight line from the bottom to the top, and that ended up being a bad idea. Instead, we're kind of doing all of these parallel and then growing together. And so to make the larger scale structures, like there's a lot of hype right now about 3D printed houses where you have a printer the size of the house. We're now working on using swarms of these, table scale robots that walk on the structures to place the parts much more efficiently.
But you're saying you can't for now go through very small big.
That'll come. That'll come in stages.
Curious to leave on this idea. Starting from Neumann's self-replicating compound dimensions. It's just a beautiful idea.
So that's at the heart of all of it. In the stack I described, so one student, Bill Langford, made these micro robots out of parts that then we're using for Miana's bigger robots up to this hierarchy. And it's really realizing this idea of the self-reproducible automata. So von Neumann, when I complained about the von Neumann architecture, it's not fair to von Neumann because he never claimed it as his architecture. He really wrote about it this one from the memo that led to all sorts of lawsuits and fights about the early days of computing. He did beautiful work on reliable classification of devices, and towards the end of his life, what he studied was how, I have to say this precisely, how a computation communicates its own construction. So a computation can store a description of how to build itself. But now there's a really hard problem, which is how, if you have that in your mind, how do you transfer it and break up a thing that then contains it? So how do you give birth to a thing that knows how to make a thing? And so with Stan Kulov, he invented cellular automata as a way to simulate this. But that was theoretical. Now the work I'm describing in my lab is fundamentally how to realize self-reproducing automata. And so, this is something von Neumann thought very, very beautifully about theoretically. And it's right at this intersection. It's not communication or computation or fabrication. It's right at this intersection where communication and computation meets fabrication. Now, the reason self-reproducing automata intellectually is so important is this is the foundation of life. This is really just understanding the essence of how to life. And in effect, we're trying to create life around material. The reason it's so important technologically is because that's how you scale plasticity. That's how you can make an elephant from a ribosome, because the elephant assemblers assemble.
The simple building blocks.
Yeah.
That inside themselves contain information how to build more building blocks and between each other construct arbitrarily complex items.
Right. Now let me give you the numbers. So let me relate this to right now we're living in AI mania explosion. Let me relate that to what we're talking about. 100 petaflop computer, which is a current generation supercomputer, but not quite the biggest ones, does 10 to the 17 ops per second. Your brain does 10 to the 17 ops per second. It has about 10 to the 15 synapses and then about 100 hertz. So as of a year or two ago, the performance of a big computer matched the brain. So you could view AI as a breakthrough, but the real story is within about a year or two ago, that the supercomputer has about 10 to the 15 transistors in the processors, 10 to the 15 transistors in the memory, which is the synapses in your brain. So the real breakthrough was the computers matched the computational capacity of the brain, and so we'd be sort of derelict if they couldn't do it about the thing. But now the reason I'm mentioning that is the chip fab making the supercomputer is placing about 10 to the 10 transistors a second. While you're digesting your lunch right now, you're placing about 10 to the 18 parts a second. There's an 8 order of magnitude difference. So in computational capacity, it's done, it's cut up. But there's 8 orders of magnitude difference in the rate at which biology can build versus state-of-the-art manufacturing can build. And that distinction is what we're talking about. That distinction is not analog, but this deep sense of digital fabrication, combining codes and instruction. So a description doesn't describe it, the description becomes the thing.
So you're saying, I mean, this is one of the cases that make this is this third revolution. We've seen them in Iran communication, we've seen them in Moore's law, like I wrote in computation, and you're anticipating we're going to see that in digital fabrication. Can you actually, first of all, describe what you mean by this term, digital fabrication?
So the casual meaning is a computer controls the code through the matrix. And that was invented when MIT started playing computers. There's the deep meaning of what the ribosome is, of a digital description doesn't describe it, and a digital description becomes the thing. That's the path to the Star Trek revolution. And that's the thing that doesn't exist. Now, I think the best way to understand what this roadmap looks like is to now bring in cloud labs and how they relate to all of this.
What are cloud labs?
So here's the sequence. With colleagues, I accidentally started a network of what's now 2,500 digital fabrication community labs, or fab labs, right now in 125 countries, and they double every year and a half. That's called Lass's Law after Sherry Lassiter will explain. So here's the sequence. We started Center for Bits and Atoms to do the kind of research we're talking about. We had all of these machines, and then had a problem. It would take a lifetime of classes to learn to use all the machines. So with colleagues who helped start CBA, we began a class modestly called How to Build a Machine. And there's no big agenda. It was aimed at a few research students to use the machine. And it was completely unprepared for the first time we taught it. We were swamped by, every year since, hundreds of students try to take the class. It's one of the most oversubscribed classes at MIT. Students would say things like, can you teach this at MIT? It seems too useful. It's just how to work these machines. And the students in the class, I would teach them all the skills to use all these tools, and then they would do projects integrating them. And they're amazing. So Kelly was a sculptor, no engineering background. Her project was she made a device that saves up screens when you're mad and plays them back later. And
Saves up screams when you're mad, plays them back later.
You scream into this device and it deadens the sound, records it, and then it's convenient releases your screen.
You just creation, the art, and the brilliance. Who is this? The brilliance?
Gone on to do a number of interesting things. Regent has gone on to do a number of interesting things. Made a dress instrumented with sensors and spies. When somebody creepy comes close, it would defend your personal space. Another project early on was a web browser for parrots, which had the cognitive ability of a young child that parrots surf the internet. Another was an alarm clock you wrestle with and move your way. And what connects all of these is, so MIT made the first real-time computer in the world. That was transistorized as the TX. The TX was spun off from MIT as the PDP. PDPs were the mini computers that created the Ken Olsen, the head of digital, famously said you don't need a computer at home. There's a little background to that, but that completely missed computing became personal. So I mentioned all of that because I was asked how to do digital fabrication, but not really why. The students in this how to make class were showing me that the killer app of digital fabrication is personal fabrication.
Yeah, how do you jump within personal fabrication?
So Kelly didn't like the string body because it was her thesis. She wasn't ready for research paper. It wasn't a business model. She wanted this because she wanted money. It was personal expression, going back to me in vocational school. It was personal expression in these new means of expression. So that's happened every year since.
It literally is called, the course is literally called How to Make Almost Anything.
Yeah.
A legendary course.
Yeah.
I mean,
and it's grown to multiple labs at MIT with as many people involved as teaching as taking it. There's even a Harvard lab for MIT class.
what have you learned about humans colliding with the God lab, about what the capacity is creating to build?
I mentioned Marvin, another mentor at MIT, sadly no longer living, is Seymour Papert. So Papert studied with Piaget. He came to MIT to get access to the early. Piaget was a pioneer in how kids learn. Papert came to MIT to get access to the early computers with the goal of letting kids play with them. Piaget showed kids are like scientists. They learn as scientists, then it gets kind of throttled out of them. Seymour wanted to have kids have a broader landscape. But Seymour's work led to Lego, Logo, Mindstorm, all that stuff. As Fab Lab spread, and we started creating educational programs for kids in them, Seymour said something really interesting. He made a gesture. He said it was a thorn in his side that they invented what's called the Turtle, a robot history, early robot history program that connected to a mainframe computer. Seymour said the goal was not for the kids to program the robot, it was for the kids to create the robot. And so in that sense, the Fab Labs, which for me were just this after that, he described as sort of this fulfillment of the art of kids learn by experimenting. It was to give them the tools to create, not just assemble things and program things, but actually create. So coming to your question, what I've learned is MIT, a few years back, somebody added up businesses from spun off in MIT, and it's the world's 10th to 100 falls between India and Russia. And I view that in a way as a bad number because it's only a few thousand people, and these aren't uniquely the 4,000 greatest people, it's just a productive environment for them. And what we found is in lone Indian villages and African county towns and Arctic hamlets, I find exactly, precisely that profile. So inside of a few hours above, so way above the Arctic Circle, so far north the satellite dish is the ground, that's the sky. Hans Christian in the lab was considered a problem in the local school because they couldn't teach him anything. I showed him a few projects. Next time he came back, he was designing and building little robot vehicles. And in South Africa, I mentioned Social Govi, in this apartheid township, the local technical institute taught kids how to make bricks and fold sheets. It was punitive. But Tapiso in the Fab Lab was actually doing all the work in my classes. And so over and over, we found precisely the same kind of bright, inventive creativity. And historically, the answer was go with your smart, go away, sort of like me in vocational school. But in this cloud network, what we could then do is, in effect, bring the world together. Now let's look at the scale of all of this. So there's one Earth, 1,000 cities, 1 million towns, 1 billion people, a trillion things. There was one whirlwind computer, MIT made the first real-time computer. There were thousands of PDQs. There were millions of hobbyist computers that came from that. Billions of personal computers, trillions of internet things. So now if we look at this Fab Lab story, 1952 was the empty. There are now thousands of Fab Labs, and the Fab Lab costs exactly the same cost of complexity of the mini computer. So on the mini computer, it didn't fit in your pocket, it filled the room. But video games, email, word processing, really anything you do with the internet, anything you do with the computer today happened at that era because it got on the scale of a work group, not a corporation. In the same way, fab labs are like the mini computers inventing how does the world work to make something. Then, if you look at that scaling, labs today are transitioning from buying a machine to make machines making machines. So we're transitioning to go to a fab lab, not to make a project, but to make a new machine. So we talked about the deep sense of self-application as a very practical sense of fab lab machines making fab lab machines. And so that's the equivalent of the hobbyist computer board, or what it's called the outdoor experiment. Then the work we spent a while talking about assemblers and self-assemblers, that's the equivalent of smartphones and Internet of Things. That's when, so the assemblers are like the smartphones, or a smartphone today has the capacity of what used to be a supercomputer in your pocket. And then the smart thermostat on your wall has the power of the original PDP computer. Not metaphorically, but literally, and now there's trillions of them. In the same sense, that when we finally merge material with the machines and self-assembly, that's like the Internet of Things. But here's the important lesson. If you look at the computing analogy, computing expanded exponentially, but it really didn't fundamentally change. The core things happened in that transition in the mini computer era. So in the same sense, the research now, like we spent a while talking about, is how we get to the replicator. Today, you can do all of that if you close your eyes and the whole fab lab as a machine. In that room, you can make some of those things, but you need a lot of inputs. Bit by bit, the inputs will go down, and the size of the room will go down as we go through each of the stages.
So how difficult is it to create a self-replicating assembler, self-replicating machine that builds copies of itself and builds more complicated versions of itself? Just kind of the dream which pushing as an engineer opportunity.
I had a student, Nadia Peak with Jonathan Ward, who for me started this idea of how do we use the tools in my lab to make the tools in the lab. In a very clear sense, they are making self-replicating machines. So one of the really cool things that happens is there's a whole network of machine builders around the world. So there's Danielle down in Germany, Jens in Norway. Each of these people has learned the skills to go into a fab lab. And so we started creating a network of super fab. So the fab lab can make a machine, but it can't make a number of different parts of the machine. So in places like Bhutan, or the south of India, we started creating super fab labs that have more advanced tools to make the parts of the machine so that the machines themselves become even cheaper. So that is self-reproducing machines, but need to feed it things like bearings or motors. But other than that, they're making those things. And I should note as a footnote, the stack I described of computers controlling machines to make machines to assemble and self-assembly, view that as Fab 1, 2, 3, 4. So we're transitioning from Fab 1 to Fab 2, and the research in the lab is 3 and 4. At this Fab 2 stage, a big component of this is sustainability of the material feedstocks. So Alicia, my lead is leading a great effort looking at how you take forest products and coffee grounds and seashell within a range of locally available materials and produce the high-tech materials that go into the lab. So all of that is machine building today. Then, back in the lab, what we can do today is we have robots that build structures that can assemble more robots that build structures. We have finer resolution robots that can build mechanical systems. So robots that can build robots that can walk and manipulate. And we're just now, we have a project at the layer below that where the family's attention today is $1 billion chip project. But a really interesting thing we can do is today the smallest transistors you buy as a simple transistor, just commercially for electronics, is actually the size of an early transistor in integrated. So we're using these machines, making assemblers to place those parts to not use $1 billion chip fab to make a circuit, but actually assemble real electronics.
So have a fire of precise actuators, manipulators, so all these pieces.
Right, that's a research project on outside on the speed assembly of integrated electronics. And we're just at the point to really start to take seriously this notion of not having a chip fab make integrated electronics, but having not a 3D printer, but a thing that's a cross between a pick and place like circuit 2D. The 3D printer extrudes in 3D. We're making sort of a micro manipulator that acts like a printer, but it's placing build electronics in 3D.
But it's not manipulated to choose a bunch of them versus one single.
So that's a great question. So I advertise that almost will not complain for the students whose thesis can walk out of the printer. So you have to print the thesis with the means to exit the printer, and it has to contain its description of the thesis that says
It's a really good. I mean, it's a fun example of exactly what people are talking.
and I've had a few students almost get to that. And so, in what I'm describing, there's we're getting closer, but it's still close to really go from. So there's a layer below the transistors where we assemble the base material of the transistor. We're now just at the edge of assembling the transistors to make circuits. We can assemble the micro parts to make the micro robots. We can assemble the bigger robots. And in the coming years, we can patch together all of those.
Basically, we see a vision of just endless billions of robots at different scales, self-replicating and building complex structures.
Yes. And the but to the yes but is, let me clarify two things. One is that immediately raises King Charles' fear of crazy, runaway, you can self-reproducing. The reason why there are many things I could tell you to worry about, but that's not one of them, is if you want things to honestly self-reproduce and take over the world, that means they need to compete with nature on using the resources of nature, like water and sunlight. And in light of everything I'm describing, biology knows everything I told you. Every single thing I explain, biology already knows how to do. What I'm describing isn't new for biology, it's new for non-biological systems. So in the digital era, the economic bin ended up being centralized, the big platforms. In this world of machines that make machines, I'm asked, for example, what's the killer opportunity? Who's going to make all the money? Who to invest in? But if the machine can make the machine, it's not a great business to invest in the machine. In the same way that if you can think globally but produce locally, then the way that technology goes out into society isn't a function of central control, but is fundamentally distributed. Now, that raises an obvious kind of concern, which is, well, doesn't this mean you could make bombs and guns and all of that? The reason that's much less of a problem you would think is making bombs, guns, and all of that is a very well-met market. Anywhere we go, there's a fine supply chain for weapons. Now, hobbyists are making guns for ages, and guns are available just about anywhere. So you could go into the lab and make a gun. Today, it's not a very good gun, and guns are usually available. So generally, if we run these live at war zones, what we find is people don't go to them to make weapons, which you can argue do anyway. It's an alternative to making weapons. Coming back to your question, I'd say the single most important thing I've learned is the greatest natural resource of the planet is this amazing density of bright young people whose brains are underused. And you could view the social engineering of this lab work as creating the capacity for them. And so, in the end, the way this is going to impact society isn't going to be control of how it uses it. And it's been really gratifying for me to see just how it goes.
Yeah, but what if it just
ways the evolution of exponential scaling of digital application. So you said, self-replicating now. Right? This is the great guru fear. It's a caricature of fear. But nevertheless, there's interesting, just like you said, like spam and all these kinds of things that came with scaling communication and competition. What are the different ways that malevolent actors would use this?
Yeah, well, first, let me start with the benevolent story, which is trash is an analog concept. There's no trash in the parts. All the parts get assembled and used. Trash means something doesn't have enough information to tell you how to use it. It's as simple as there's no trash in a Lego brick. When you assemble Lego, the Lego bricks have enough information to disassemble it. So as you go through this Fab 1, 2, 3, 4 story, one of the implications of this transition from printing to assembly. So the real breakthrough technologically isn't additive versus subtractive, which is take a lot of attention and hype. If 3D printers are useful, we spun off companies like Forum Lab, led by Max for 3D printing. But in a Fab Lab, it's one of maybe 10 machines. It's used, but it's only part of the machine. The real technological change is when we go from printing and cutting to assembling and disassembling. But that reduces inventories of hundreds of thousands of parts to just having a few parts to make almost anything. It reduces global supply chains to locally sourced these building blocks. But one of the key implications is it gets rid of technological trash because you can disassemble and reuse the parts, not throw them away. So initially that's a good for things at the end of long supply chains, like satellites on orbit. But one of the things coming is eliminating the trash through the use of the building blocks.
So, like when you think about 3D printers, you think about addition, subtraction. When you think about the other options available to you in that parameter space, it's going to be assembly, disassembly, cutting, you said.
So the 1952 MC mill was subtracted. You remove a few. And 3D printing additive, and there's a couple claims to the invention of 3D printing. That's closer to what's called net shapes, which is you don't have to cut away the material you don't need to just remove it. And so that's the 3D printing revolution. But there are all sorts of limitations on 3D printing to the kinds of materials you can print, the kind of functionality you can print. We're just not going to get to making everything in a cell phone on a single printer. But I do expect to make everything in a cell phone with an assembly. And so instead of printing and cutting technologically, it's this transition to assembling and disassembling. Going back to Shannon and Van Neumann, going back to the ribosome 4 billion years ago. Now, we come to malevolence. Let me tell you a story about I was doing a briefing for the National Academy of Sciences group that advises the intelligence community. And I talked about the kind of research we do. And at the very end, I showed a little video clip of Valentine in Ghana making a local girl making circus comedy in the top. And I showed that to this room full of people. One of the members of the intelligence community got up livid and said, "How dare you waste our time showing us a young girl in an African village making circus electronics? We're looking at, we need to know about disruptive threats to the future of the United States." And somebody else got up in the room and yelled at him, "You idiot, I can't think of anything more important than this." But for two reasons. One reason was because if we rely on like informational superiority in the battlefield, it means other people who get access to it. But this intelligence person's point, listen, wasn't that, it was getting at the root causes of conflict. Is if this young girl in African village could actually master surface electronics, it changes some of the most fundamental things about recruitment for terrorism, impact of economic migration, basic assumptions about economy. It's just existential for the future of the planet.
But With just with the pandemic, I love to guns. The possibilities that are positive are endless,
Yeah.
but the possibilities that are negative are still nonetheless extremely important. There's both positive and negative. What do you do with a large number of general samples?
Yeah. With the Fab Labs, you could roughly make a biolab on the side. Now that's terrifying because making self-reproducing gray glue that outcompetes biology, I consider doing because biology knows everything I'm describing. It's really good at what it does. In how to grow almost anything, you learn skills in biotechnology that you make serious biology.
And when you combine some of the innovations you see with large language models, some of the innovations you see with the applications of AI for designing biological systems, for writing programs, and the large language models increasingly so, there seems to be an interesting dance here of automating the design stage of complex systems using AI, and then that's the bits. And you could leap now, the innovations you're talking about, you can leap from the complex systems in the digital space to the printing, to the creation, to the assembly at scale of complex systems in the physics.
Yeah, so something to be scared about is the Fab Lab can make a biolab can make biotechnology, somebody could learn to make a virus. That's scary. Unlike some of the things I said, I don't worry about. That's something I really worry about. That is scary. Now, how do you deal with that? Prior threats we dealt with command and control. So, like early color copiers had unique codes, and you could tell which copier did them. Eventually, you couldn't keep up with that. There was a famous meeting at a seminar in the early days of DNA, where that community recognized the dangers of what it was doing and put in place a regime to help manage it. And so that led to the kind of research management. So MIT has an office that supervises research, and it works with the national office. That works if you can identify who's doing it. It doesn't work in this world we're describing. So anybody could do this anywhere. And so what we found is you can't contain this. It's already out. You can't forbid because there is command and control. The most useful thing you can do is provide incentives for control. So, but really the heart of what we do is you could do this by yourself in the basement for various reasons, or you could come into a place in the life where you get help and you get community and you get resources. And there's an incentive to do it in the open, not in the dark. And that might sound naive, but in the sort of places we're working, again, bad people do bad things in these places already, but providing openness, providing transparency is a key part of managing. And so it transitions from regulating risks as regulation to soft power management.
But there's so much potential for good in this capacity that Fab Labs and the ability and the tools of creation.
Yeah, and I don't say that as really naive. I say that empirically, just years of seeing how this plays out already.
I wonder if it's the early days of personal computers, though, before we get to that.
In the end, most fundamentally, literally the mother of all problems is who designed us. So assume success in that you're going to transition to the machines, and all of these new sort of social systems we're describing will help manage them, and curate them, and democratize them. If we close the gap I just led off with of 10 to the 10 to 10 to the 18 between chip fab and you, We're ultimately, in marrying communication, computation, and fabrication, going to be able to create unimaginable complexity. And how do you design that? And so I'd say the deepest of all questions that I've been working on goes back to the oldest part of our genome. So in our genome are called hotspots, and these are morphogenes. And nowhere in your genome is the number 5. It doesn't store the fact that you have 5 fingers. And what it stores is called the developmental program. It's a series of steps, and the steps have the character of like grow up a gradient or break symmetry. And at the end of that developmental program, you have 5 fingers. So you are stored not as a body plan, but as a growth plan. And there's 2 reasons for that. One reason is just compression. Billions of genes can place billions of cells. But the much deeper one is evolution doesn't randomly recur. Almost anything you did randomly as a genome would be fatal or inconsequential, not interesting. But when you modify things in these developmental programs, you go from like webs for swimming to fingers, you go from walking to wings for flying. It's a space in which search is interesting. So this is the heart of the success of AI. In part, it was the scaling we talked about a while ago, and in part, it was the representation for which search is effective. AI has found good representation. It hasn't found ways to search, but it's found good representation.
And that's what you're saying, that's what biological evolution has done, is created representation, structures, biological structures through research.
Perfect. And so the developmental program in the genome beautifully encapsulates the lessons of AI. And it's embodied, it's molecular intelligence, it's AI embodied in our genome. It's every bit as profound as the cognition in our brain, but now this is sort of thinking in molecular thinking in how you design. And so I'd say the most fundamental problem we're working on is it's kind of tautological that when you design a phone, you represent the design of the phone. But that actually fails when you get to the sort of complexity that we're talking about. And so there's this profound transition. Once I can have self-reproducing assemblies placing 10 to the 18 parts, you need to not sort of metaphorically, but create life in that you need to learn how to evolve. But evolutionary design has a really misleading trivial meaning. It's not as simple as you randomly do things. It's much more deep embodiment of AI.
Is there a way for us to continue the kind of evolutionary design that was took this place in the early days of bacteria, since our organisms to ribosomes and the 20 amino acids?
You mean for human occupation?
For life? What would you call assemblers that are self-replicating and placing parts? What is the dynamic, complex things built with digital fabrication? What is that? That's the life.
So ultimately, absolutely, if you add everything I'm talking about, it's building up to creating life in non-living material. And I don't view this as copying life. I view it as driving. I didn't start from how does biology work and then copy it. I start from how to solve problems, and then it leads me to, in a sense, rediscover biology. So if you go back to Valentina in Ghana making the circuit board, she still needs the chip fab very far away to make the processor of the circuit board. For her to make the processor locally, for all the reasons we described, you actually need the deep things we were just talking about. And so it really does lead you. So there's a wonderful series of books by Singer. Book one is how to start your furnace, and at the end of book 7, you have machine shops. So it's sort of how you do your own personal industrial revolution. ISRU is what NASA calls in situ resource utilization, and that's how do you go to a planet and create a civilization. ISRU has essentially a certain Ingram. You go through the Industrial Revolution and you create the inventory of 100,000 resistors. What we're finding is the minimum building block for civilization is roughly 20 parts. So what's interesting about the amino acids is not interesting. They're hydrophobic or hydrophilic, basic or acidic. They have typical but not extremal properties, but they're good enough to provide that base fuel. So what this is leading towards is technology doesn't need enormous global supply chains. It just needs about 20 properties you propose to create all technology as a minimum building blocks for technological participation.
There's going to be 20 basic building blocks based on which the self-replicating civilization.
Right, and I say that not philosophically, just empirically, so that's where it's headed. And I like thinking about how you bootstrap the civilization on Mars. That problem was a fun video and bonus material for the for a neat group of people who talk about it, because it has really profound implications back here on Earth about how we live.
What is that civilization on Mars looks like? It's using ISRU that's using these 20 building blocks and it does self-assembly.
Yeah, go through primary, secondary, tertiary, quaternary. You extract properties like conducting, insulating, semiconducting, magnetic, dielectric, structural. These are the kind of introductory properties. With those are enough for us to assemble logic, and they're enough for us to assemble actuation. With logic and actuation, we can make micro robots. The micro robots become bigger robots. The bigger robots then take the building block materials and make the structural elements that you then do to make construction. And then you boot up through the stages of a technological implementation.
By the way, where logic and actuation get this sensor?
Oh, I skipped over that. But my favorite sensor is a step response. So if you just make a step and measure the response to the electric field, that ranges from user interfaces to positioning to material properties. And if you do it at high frequency, you get chemistry. You get all of that just from a step in an electric. So for example, once you have time resolution in logic, something as simple as 2 electrodes let you do amazingly capable things. So we've been talking about all the work I do. There's a story about how it happens. Where do ideas come from?
That's interesting. Where do ideas come from?
So I had mentioned Benny Bush, and he wrote a really influential thing called The Endless Frontier. So science won World War II. The more known story is the Rothschild. The less well-known story is the Rabbi. So at MIT, an amazing group of people invented radar, which is really credited in the war. So after the war, Randall Mann from MIT was charged with science won the war. How do we maintain edge? And the report he wrote led to the National Science Foundation and the modern notion we take for granted, but didn't really exist before that, of public funding of research and researchers. In it, he made, again, what I consider an important mistake, which is he described basic research leads to applied research, leads to application, leads to commercialization, leads to and so we need to invest in that pipeline. The reason I consider it a mistake is almost all of the examples that we're talking about in my lab went backwards. but the basic research came from application. And further, almost all of the examples we were talking about came fundamentally from mistakes. So essentially everything I've ever worked on has failed, but in failing something better. So the way I like to describe it is ready, aim, fire is you do your homework, you aim carefully at something, a target you want to accomplish, everything goes right, you then hit the target. What I do, you can think of as ready, fire, aim. So you do a lot of work to get ready, then you close your eyes, and you don't really think about where you're aiming, but you look very carefully at where you did it. Where, you aim after you fire. And the reason that's so important is if you do ready and fire with this, the best you could hope is just. So let me give you some examples. This is a source of good lines. It's a source of great frustration. So I mentioned the early quantum. So quantum computing is this power used in quantum mechanics to make computers that for some problems are dramatically more powerful than Tesla. Before it started, there was a really interesting group of people who knew a lot about physics and computing that were inventing what became quantum computing before it was clear anything there was an opportunity. It was just studying how it was made. Here's how it fits to the ready fire image. I was doing really short-term work in my lab on chocolate. This was really before there was modern RFID, and so how you could tag an object, just something we just take for granted commercially, and there was a problem of how you can sense multiple objects at the same time. And so I was studying how you can remotely sense materials to make low-cost tags that could let you distinguish multiple objects at the same time. To do that, you need nonlinearity, so that the signal is modulated. And so I was looking for material sources of nonlinearity, and that led me to look at how nuclear spin is just for spin resonance. Is the sort of things you use if you like going in an MRI. And so I was studying how to use that. And it turns out that it was a bad idea. You couldn't remotely use it for shoplifting. But I realized it's huge. And so with a group of colleagues thinking about early quantum computing, like David Evenson and Charlie Bennett, was articulating what are the properties we need to compute, and then looking at how to make the tag. Turns out the tags were a terrible idea for sensing objects in a supermarket checkout, but I realized they were computing. So with Eggtron and a few other people, we realized we could program nuclear spin to compute. And so that's what we used to do reverse search algorithm, and then it was used for a Schwarz factoring algorithm. And it worked out. The systems we did it in, nuclear magnetic resonance, don't scale beyond a few qubits. But the techniques have lived on, and so all the current quantum computing techniques out the ways we would talk then. But I'm telling this whole story because it came from a bad way to make a shopping.
Starting with an application, mistakes, led to the breakthrough of the science.
Yeah.
I mean, can you just learn on that? I mean, just in using nuclear specific computation, like what gave you the guts to try to think through this? From the digital fabrication perspective, how do you lead for what to do?
I wouldn't call it guts, I would call it collaboration. So at IBM, there was this amazing group of, like I mentioned, Charlie Bennett, David Vincenzo, and Ralph Landau, and Bill Amir, and these were all gods of thinking about physics and computing. So I yelled at the whole computer industry being based on a fiction, Metropolis. Programmers frolicking in darkness, getting leverage in the base. There's a complete parallel history of Maxwell's defaults, which Zillar to Landauer to Bennett. Most people won't know most of these names, but this whole parallel history, thinking deeply about how computation is related. So I was collaborating with them as people, and then at MIT, I was in the psychology department. I wasn't deeply inspired to think about better ways to detect shoplifting tags, but stumbled across companies that needed help with that, was thinking about it. And then I realized there's two worlds. And we could use the failed approach for the shoplifting tags to make early quantum computing algorithms.
It was kind of stumbling up into the Fabian idea.
Right. Here's one more example. With a student, Andrew, we talked about ribosomes, and I was trying to build a ribosome that works on fluids so that I could place conflict. And it kept failing because bubbles would come into our system and the bubbles would make the thing stop working. And we spent about half a year trying to get rid of the bubbles. Then Manu said, wait a minute, the bubbles are actually better than what we're doing, we should just use the bubbles. And so we invented how to do universal object with little bubbles, logic with little bubbles, fluid.
Okay, you have to explain this microfluidic logic, please. How does this work?
So yeah,
It's super interesting.
yeah, and so I'll come back to explain it. But what it led to was we showed fluids to do. It's been known fluids to do logic, like with old automobile transitions to logic, but that's macroscopic. It didn't work at little scale. We showed that these bubbles we could do it at little scale. Then I'm going to come back and explain it. But what came out of that was Manu then showed you could make a 50-cent microscope using little bubbles. And then the techniques we developed are what we use to transplant genomes to make synthetic life. All came out of the failure of trying to make the genome, the ribosome. Now, so the way the bubble logic works is in a little channel, fluid at small scale is fairly distant, sort of like pushing jello. If a bubble gets stuck, the fluid has to turn around. So now imagine a channel that has two rounds and one bubble. If the bubble is in one round, the fluid has to go in the other channel. If the fluid is in the other round, it has to go in the first channel. So the position of the bubble can switch. It's a switch. It can switch over between two channels. So now we have one element of switch. And it's also a memory, because we can detect whether or not the bubble is stored there. Then if two bubbles meet, if you have two channels crossing, a bubble can go through one way or a bubble can go through the other way. But if two bubbles come together, then they push on each other and one goes one way and one goes the other way. That's a logic operation. That's a logic gate. So we now have a switch, we have a memory, and we have a logic gate. That's everything we need in the universe.
I mean, the fact that you did that with bonus, just kind of really.
Well, so to think of that example, what we proposed to do was to make a fluid ribosome, and the project crashed and burned. It was a disaster. This is what came out of it, and so it was precisely ready to find our name. We had to do a lot of homework to be able to make these microfluid systems. The fire part was we didn't think too hard about making the ribosome because I did do it. The aim part was to realize the ribosome failed and something better about it. And if you look all across research funding, research management, it doesn't anticipate this. So fail fast is familiar, but fail fast tends to miss ready and aim. You can't just fail. You have to do your homework before the fail part, and you have to do the aim part after the fail part. And so the whole language of research is about like milestones and deliverables. That works when you're going down a straight line, but it doesn't work for this kind of discovery. And to lead to something you said that's really important is I view part of what the Fab Lab network is giving more people the opportunity to kill.
You've said that geometry is really important in biology. Uh, what does fabrication biology look like? Why is geometry?
So molecular biology is dominated by geometry. That's why the picture is so important. That the geometry gives the function. And there's this hierarchical construction of, as you go through primary, tertiary, quaternary, the shapes of the molecules make the shape of a molecular machine. And they really are exquisite machines. If you look at how your muscles move, if you were to see a simulation of it, it would look like a improbable science fiction cyborg world of these little walking robots that walk on the lattice. They're really exquisite machines. And then from there, this whole hierarchy stuff of once you get to the top of that, you then start making organelles that make cells, make organs through the staff of that hierarchy.
Just stepping back, does it amaze you that from small building blocks or amino acids, you mentioned molecules, it's at the very beginning of hydrogen and helium, the start of this universe, they were able to build up such complex things like
So studying thermodynamics, which is exactly the question of, that batteries run out and need recharging. Equipment, cars get old and fail, yet life doesn't. And that's why there's this sense in which life seems to rise thermodynamics, although of course it doesn't.
it seems to resist the march towards entropy.
Right. And so Maxwell, who helped devise the science of thermodynamics, posited a problem that was so infuriating that to a series of suicides. There was a series of advisors and advisees, 3 in a row that all ended up committing suicide that happened to work on this problem. And Maxwell's demon is this simple but infinite problem where right now in this room we're surrounded by molecules. They represent imagine a container that has a wall and it's got gas on both sides and a little door. And if the door is a molecular sized creature, and it could watch the molecules come in. And when the fast molecule is coming, it opens the door. And the slow molecule is coming, it closes the door. After it does that for a while, one side is hot, one is cold. When something's hot and it's cold, you make an engine. And so to close that, you make an engine. So the demon is violating thermodynamics because it's never touching the molecule. Yet by just opening closing the door, it can make arbitrary amounts of energy and power. And thermodynamics itself do that. So that's Maxwell's demon. That problem is connected to everything we just spoke about for the last few hours. So Leo Szilard, around early 1900s, was a deep physicist who then had a lot to do with also post-war anti-nuclear things. But he reduced Maxwell's demon to a single molecule. So the molecule, there's only one molecule, the question is which side of the partition is it on. That led to the idea of one bit of information. So Shannon credited Szilard analysis of Maxwell's demon for the invention of the bit. For many years, people tried to explain Maxwell's demon by like the energy in the demon looking at the molecule, or the energy to open and close the door, and nothing ever made sense. Finally, Rolf Landauer, one of the colleagues I mentioned at IBM, finally solved the problem. He showed that you can explain Maxwell's demon by you need the mind of the demon. when the demon opens and closes the door, as long as it remembers what it did, you can run the whole thing backwards. But when the demon forgets, then you can't run it backwards. And that's where you get dissipation, and that's where you get violations from an happen. So the explanation of Maxwell's demon is that it's in the demon's brain. So then Rolf's colleague Charlie at IBM then shocked Rolf by showing you can compute with arbitrarily low energy. So one of the things that's not well covered is that the big computers used for big machine learning, the data centers use tens of megawatts of power, use as much power as they did. Charlie shows you can actually compute with arbitrarily low amounts of energy by making computers that can go backwards as well as forward. And what limits the speed of the computer is how fast you want the answer and how certain you want the answer to be. But we're orders of magnitude away from that. So I have a student, Cameron, working with me in labs on making superconducting computers that operate near this Landauer limit that are orders of magnitude more efficient. So stepping back to all of that, that whole tour was driven by your question about life. And right at the heart of it is Maxwell's name. Life exists because it can locally violate fundamentals. It can locally violate fundamentals because of intelligence. And it's molecular intelligence that I would even go out on the list to say we can already see the beginning of the end of this current AI phase. So depending on how you count, this is, I'd say, the fifth AI boom bust cycle. And you can already, it's exploding, but you can already see where it's heading, how it's going to saturate what happens on the far side. The big thing that's not yet on the horizon is embodied by AI. So to step back to this AI story, there was automation that was going to change everything. Then there were expert systems. There was then the first phase of the neural network system. There have been about 5 of these. In each case, on the slope up, it's going to change everything. In each case, what happens is on the slope down, we sort of move the goalposts, and it becomes sort of the right. So a good example is going up, computer chess is going to change everything. Once computers play chess, that fundamentally changes the world. Now on the downside, computers play chess. Winning a chess is no longer seen as a human thing, but people still play chess. This new phase is going to take a new chunk of things that we thought computers couldn't do. Now computers will be able to do. They have roughly our brain capacity. But we'll keep thinking as well as computers. And as I described, how would you learn to these 5 groups fast? If you just look at the numbers, ops per second, bits of storage, bits of I/O, that's the more interesting one. That's been steady, and that's what's talking about on computer. But as we've talked about a couple times, there's 8 orders of magnitude to go, not in the intelligence of the transistors or in the brain, but in the embodied intelligence, in the intelligence in our body.
The intelligent construction of physical systems that embody the intelligence.
Right, and there's a brain centrism that assumes our intelligence is centered in our brain. And in endless ways, in this conversation, we've been talking about molecular intelligence. Our molecular systems do a deep kind of artificial intelligence. All the things you think of as artificial intelligence does in representing knowledge, storing knowledge, searching over knowledge, adapting to knowledge, our molecular systems do. But the output isn't just the thought, it's us. It's the evolution of us. And that's the real life now, embodying AI, not just the processor and the robot, but building systems that really can grow and evolve.
We we've been speaking about this boundary between bits and atoms. So let me ask you about one of the big mysteries of consciousness. Do you think it comes from somewhere between that boundary?
I won't name names, but if you know what I'm talking about, it's probably clear. I once did drive, in fact, up to the Mussolini era villa outside in the early days of what became quantum computing, with a famous person who thinks about quantum mechanics and consciousness. And we had the most infuriating conversation that went roughly along the lines of consciousness is weird, quantum mechanics is weird, therefore quantum mechanics explains consciousness. That was roughly the logical process.
You're not satisfied with that.
No, and I say that very precisely in the following sense. I was a program manager, somewhat by accident, in a darker program on quantum biology. And so biology trivially uses quantum mechanics that were made out of atoms. But the distinction is in quantum computing, quantum information, you need quantum coherence. And there's a lot of muddled thinking about like collapsive wave function, claims of quantum computing, and garble just quantum coherence. That you can think of it as a wave that has very special properties, but these waves properties. And so there's a small set of places where biology uses quantum mechanics in that deeper sense. One is how light is converted to energy in photosystems. It looks like one is olfaction, how your nose is able to tell different smells. Probably one has to do with how birds navigate, of how they sense magnetic fields. That involves a coupling between a very weak energy with a magnetic field, coupling into chemical reactions. And there's a beautiful system. Standard in chemistry is magnetic fields like this can't influence chemistry, but there are biological circuits that are carefully balanced with two pathways that become unbalanced with magnetic fields. So each of these areas are expensive for biology. It has to consume resources to use quantum mechanics, right? So those are places where we know there's quantum mechanics in biology. And cognition is just there's no evidence of anything mechanical going on in how cognition works consciously. Well, I'm saying cognition, I'm not saying consciousness. But to get from cognition to consciousness. So McCullough and Hicks made a model of neurons. That led to perceptron, that then through a couple of boom busts led to deep learning. One of the interesting things about that sequence is it diverged off. So deep neural networks used in machine learning diverged from trying to understand how the brain works. What makes them work, what's emerged is that it's a really interesting story. This may be too much of a technical detail, but it has to do with that we talked about exponentials. A deep network needs an exponentially larger, shallow network to do the same functions. And that exponential is what we call the deep network. But what's interesting is the sort of lessons about building these deep architectures and how to train them have really interesting echoes in how brains work. And there's an interesting conversation that's sort of coming back of neuroscientists looking over the shoulder of people training these deep networks, seeing interesting echoes for how the brain works, interesting parallels with this. And so I didn't say consciousness, I just said cognition. But I don't know any experimental evidence that points to anything in neurobiology that gives you consciousness. And I view the question about whether a large language model is conscious as silly. In that biology is full of habits. and it works. There's no evidence we have that there's anything deeper going on than just this sort of stacking up of brains.
And somehow consciousness is one of the hacks, or emerging property of the hacks.
Absolutely. And just numerically, I said big computations now have the degrees of freedom of the brain. And they're showing a lot of the phenomenology of what we think is properties of the brain. And I don't see any reason to provoke anything else.
That makes me wonder what kind of beautiful stuff that your computation creates. If biology to hacks on top of which consciousness and cognition and the things we know about human beings is created, it makes you wonder what kind of beauty human complexity.
Yeah, so there's an early peek at that, which is there's a misleading term which is generative design. Generative design is where you don't tell a computer how to design something, you tell the computer what you want it to do. That doesn't work, that only works in limited subdomains. Like you can't do really complex functionality that way. The one place it's mature, though, is topology optimization for structure. So let's say you wanted to make a bicycle, or you describe the loads on it, and it figures out how to design it. And what it makes are beautiful organic looking things. These are things that look like they grew in a forest. And they look like they grew in a forest because that's sort of exactly what they are. That they're solving the ways of how to handle loads in biology guys. So you get things that look like trees and shells and all of that. And so that's a peak of this transition to from we design to we teach the machine science.
What can you say about, because we just had a comment earlier about this example you just gave, and the general observation you can make by looking at setting autonomy and good things are with simple rules, with simple building blocks, we emerge arbitrary complexity. Do you understand what that is, how that can be leveraged?
So understand what it is much easier than it sounds. I complained about Turing's machine physics, but Turing never intended it to be a computer architecture. He used it just to prove results about uncomputability. What Turing did on what is computation is Swiss gorgeous. He gave us a notion of computational universality, and something that sounds deep and turns out to be trivial is it's really easy to show almost everything is universal. So Norm Margulis wrote a beautiful paper with Tom Coffey showing in a cellular common world is like the game of life, where you just move tokens around. They showed that modeling billiard balls on a billiard table with cellular automata is a universal computer. To be universal, you need a persistent state, you need a nonlinear operation to interact, and you need connectivity. So that's what you need to show computational universality. So they showed that a CA modeling billiard balls is a universal computer. Chris Moore went on to show that instead of chaos, Turing showed there are problems in computation that you can't solve. That they're harder than you can predict. They're actually in a deep reason that they are unsolvable. Chris Moore showed it's very easy to make physical systems that are uncomputable. That what the physics system does, just bouncing balls and surfaces, we can make systems that solve uncomputable problems. And so almost any non-trivial physical system is computational. So the first part of the question is, if this comes back to how my comment about how do you bootstrap a civilization, you just don't need much to be computational universal. So then, there isn't today a notion of like fabricational universality or fabricational complexity. The sort of numbers I've been giving you about you eating lunch versus the chip sort of that's in the same spirit of what Chapman did. But once you connect
Because that evolution happens in space.
Yeah, and so that's why, for me, the heart of this whole conversation is morphogenesis. So just to come back to that, what Turing ended his sadly cut short life studying was how genes give rise to form. So how the small amount of it, relatively small amount of information in the genome can give rise to the complexity of who you are. And that's where what resides in this collective intelligence, which is first how to describe you, but then how to describe you such that you can exist, and you can reproduce, and you can grow, and you can evolve. And so that's the seed of our molecular intelligence.
Make the revolution of biology.
Yeah, it really is. It really is. And that's where you can't separate communication, computation, and fabrication. You can't separate computer science and physical science. You can't separate hardware and software. They all intersect at that.
Do you think of our universe as just reaching issue?
I would even kind of say quantum computing is overhyped in that there's a few things quantum computing is going to be good at. One is breaking crypto systems with crypto systems. What it's really good at is modeling other consciousness. So if you're studying nanotechnology, it's going to be powerful. But quantum computing is not going to disrupt and change everything. But the reason I say that is this interesting group of strange people who helped invent quantum computing before it was clear anything was there. One of the main reasons they did it wasn't to make a computer to break cryptosystems. It was you could turn this backwards. You could be surprised by the compute, or you can go in the opposite direction and say if quantum compute, that's a description of nature. So physics is written in terms of partial differential equations. That is an information technology from 2 centuries ago. The equations of physics are not, this is very strange to say, but the equations of physics, Schrodinger's equations and Maxwell's equations and all of them, are not fundamental. They're a representation of physics that was accessible to us in the era of having a pencil and a piece of paper. They have a fundamental problem, which is if you make a dot on a piece of paper, in traditional physics theory, there's infinite information in that dot. A point has infinite information. That can't be true because information is a fundamental resource that's connected to energy and effect. Yeah. One of my favorite questions you can ask a psychologist to trip them up is information a conserved quantity in the universe? Was all the information created in the Big Bang or the universe created information? And I've yet to meet a cosmologist who doesn't stutter and not really know how to handle that existential question. But sort of putting that to the side, in physics theory, the way it's taught, information comes late. You're taught about x, a variable, which can contain infinite information, but physically that's unrealistic. And so physics theories have to find ways to take that off. So instead, there are a number of people who start with a theory of the universe should start with information and computation as just fundamental resources in nature, and then you build up from that to something that looks like throwing baseballs down the slope. And so in that sense, the work on physics and computation has many applications that we've been talking about, but more deeply, it's really getting at new ways to think about how the universe works. And there are other things that are hard to do in traditional physics that make more sense. when you start with information and computation as the root of physical theory.
Information computation being the root.
Right. That information is the resource. You can't have infinite information in finite space. Information propagates and interacts. And from there you will extrapolate into physics. Now it happens, the words I just said look a lot like quantum field theory. But there's an interesting way where instead of starting with differential equations to get to quantum field theories, and quantum field theories you get to quantization. If you start with computational information, you begin sort of quantized and you go on from there. And so that's the sense in which absolutely I think about the universe as a computer. The easy way to understand that is just almost anything is computational universal, but the deep way is it's a real fundamental way to understand how the universe works.
Let me go with you to the first one. The center of its anatomies. You have worked with the students you've worked with have gone on to do some incredible things in this world, including little supercomputers that power Facebook, Twitter, and so on. What advice would you give to you? What advice have you given them how to have one heck of a great career? One heck of a great life?
Well, one important one is if you look at junior faculty trying to get tenure at a place like MIT, the ones who try to figure out how to get tenure are miserable and don't get tenure, and the ones who don't try to figure it out are happy if you get it. You have to love what you're doing and believe in it, and nothing else could possibly be what you want to be doing with your life when it gets to go to bed in the morning. And again, it sounds naive, but within like the limited domain I'm describing now of getting tenure at MIT, that's the key attribute to it. In the same sense, if you take this sort of outlier Steve's talking about, if 99 out of 100 come to me and say your work is very fascinating, I'd be interested to work for you, and 1 out of 100 come and say, here's you're wrong, here's your mistake, here's what you should have been doing, and they just sort of say I'm here and get to work. And again, I don't know how far this resource goes. So what I've said, I consider the world's greatest resource this engine of enlightenment of people, of which we only see a tiny little iceberg of it. And everywhere we open these labs, they come out of the woodwork. They come. We didn't create all these educational programs, all these other things I'm describing. We tried to partner everywhere with local schools and local companies, capture over dysfunction and find ways to create the environment where people like this can flourish. So, this is everyone, it's 1% of society, what the action is, but it's so many orders of magnitude bigger than we see today. We've been racing to keep up with the advantage of that resource.
Something tells me it's a very large fraction of the population.
I mean, the thing that gives me most hope for the future is that population. Once a year, this Holy Lab Network meets, and it's my favorite gathering at the time this year because it's every body shape, it's every language, every geography, but it's the same person in all those countries. It's the same sense of bright endemic joy and discovery.
If there's people listening to this and they're just overwhelmed with how exciting this is, which I think they would be, how can they participate? How can they help? How can they encourage young people themselves to do stuff, to create stuff?
Yeah, it's a good question. So this is part of a much bigger movement of a lot of embodiment. Part of it involved in the Cloud Lab Network. You can think of it as a curated part that works as a network. So you don't benefit in a gym if somebody exercises in another gym. But in the Cloud Network, you do in a sense benefit from somebody working in another network, another lab, in the way it functions as a network. So you can come to cba.mit.edu to see the research we're talking about. There's a fact foundation run by Sherry Lassiter at ScottFoundation.org. FatRun.io is a portal into the Scott network. FabAcademy.org is this distributed hands-on educational program. Fab.city is the platform of cities producing things. Those are all nodes.
So you can learn with Fab Academy, and you can perhaps launch or help launch this international campaign.
Well, and in particular, from 1 to 1,000, we carefully counted labs. Now we're going from 1,000 to 1 million, where it ceases to become interesting to count them. And then 1,000 to the billion. What's interesting about that stage is technologically, you go to a lab not to get access to the machine, but you go to a lab to make the machine. But the other thing interesting in it is we have an interesting collaboration on a fab lab in a box. And this came out of a collaboration with SolidWorks on how you can put a fab lab in a box, which is not just the tools, but the knowledge. So you open the box, and the box contains the knowledge of how to use it as well as the tools within it, so that the knowledge can propagate. And so we have an interesting group of people working on the original Fab Lab. We have a whole team to get involved in the setting up and training. And the Fab Academy is a real in-depth, deep technical program for training. But in this next phase, how sort of the lab itself knows how to do the lab. We've talked deeply about the intelligence in fabrication, but in a much more accessible one about how the AI in the lab, in fact, becomes a collaborator with you in this error term to help get started. And for people wanting to connect, it can seem like a big step, a big threshold, but we've gotten to thousands of these, and they're doubling exactly that way just for people opting in.
And so doing drive towards this kind of idea of personal visual fabrication.
Yeah, and it's not utopia, it's not free, but come back to today, we simply have education, we have big business, we have startups, we have entertainment, sort of each of these things are segregated. When you have local connection to one of these local facilities, in that you can do play and art and education and create infrastructure. You can make many of the things you consume. You can make it for yourself. It can be done on a community scale. It can be done on a regional scale. It really, I'd say, the research we spent the last 3 hours talking about, I thought was hard. And in a sense, I mean, it's non-trivial, but in a sense, it's just sort of playing out one foot at a time. What I didn't think was hard is, if anybody can make almost anything anywhere, how do you live? How do you learn? How do you work? How do you play? These very basic assumptions about how society functions. There's a way in which it's kind of back to the future, in that this mode where work is money is consumption, and consumption is shopping by selecting, is only a kind of a few decade old stretch. In some ways, we're getting back to a Sami village in North Norway is deeply sustainable, but rather than just reverting to living the way we did a few thousand years ago, being connected globally, having the benefits of modern society, but connecting it back to older notions of sustainability. I hadn't remotely anticipated just how fundamentally that challenges how a society functions, and how interesting and how hard it is to figure out how we can make that work.
It's possible that this kind of process will give a deeper sense of meaning to each person.
Let me violently agree in 2 ways. One way is this community making crosses many sensitive sectarian boundaries in many parts of the world, where there's just implicit or explicit conflict. But sort of this act of making seems to transcend a lot of historical divisions. I don't say that philosophically, I just say that as an observation. And I think there's something really fundamental in what you said, which is if deep in our brain is shaping our environment. A lot of what's strange about our society is the way that we can't do that. The act of shaping our environment touches something really, really deep that gets to the essence of who we are. That's again why I say that, in a way, the most important thing made in these labs is making itself.
What do you think if this shaping of our environment gets something deep? What is the meaning of it all? What's the meaning of life?
I can tell you my insights into how life works. I can give you my insights into how to make life meaningful and fulfilling and sustainable. Um, I have no idea what the meaning of life is, but maybe that's
The answer to confusion. Uh, because there's a magic to it all. Everything we've talked about, from starting from the basic elements of the Big Bang, somehow created the sun, somehow said FU to thermodynamics and created life in all the ways that we've talked about, from ribosomes that created machinery, that created machine, and now the biological machine creating through digital fabrication for complex artificial machine. All of that is the magic of that creative process. We notice we humans are smart enough to notice the magic.
So you haven't said the S word yet. Singularity. I'm not sure if Ray Kurzweil is listening to his high Ray, but I have a complex relationship with Ray because a lot of the things he projects I find annoying. But then he does his homework, and then somewhat annoyingly he points out how almost everything I'm doing fits on his roadmaps. And so the question is, are we heading towards a singularity? So I'd have to say I lean towards sigmoids rather than exponentials.
We've done pretty well with that.
Yeah, so sigmoids are things grow and they taper, and then there can be one after it. So, I'll pass on whether there's enough of them that they diverge. But the selfish gene answer to the meaning of life is the meaning of life is the propagation of life. And so, it was a step for atoms to assemble into a molecule, for molecules to assemble into a protocell, for the protocell to form, to then form organelles, for the organ cells to form organs, the organs to form an organism. Then it was a step for organisms to form family units, like family units and villages. You can view each of those as a step in the level of organization. So you could view everything we've spoken about as the imperative of life, just the next step in the hierarchy of that, and the fulfillment of the inexorable drive for the violation of thermodynamics. So you could view an embodiment of the will of the violation of
thermodynamics. Having an old chat.
Yeah.
And so it continues. I mean, then the singularity is just a transition up the ladder.
There's nothing deeper to consciousness than it's a derived property of distributed problem solving. There's nothing deeper to life than embodied AI in morphogenesis. So why so much of this conversation in my life is involving these fact labs? And initially it just started as outreach, then it started as keeping up with it, then it turned to it was rewarding. Then it turned to we're learning as much from these labs as goes out to them. It began as outreach, but now more knowledge is coming back from the labs and going into them. And then finally, it ends with what I described as competing with myself at key, but a better way to say that is tapping the great power of the planet. And so, I guess for me personally, that's the meaning.
Maybe that's the meaning of the universe too. It's using us humans and our creations to understand itself. In a way, it's whatever the creative process that created Earth, it's competing with itself.
Yeah, so you could take morphogenesis as a summary of the conversation, or you could take recursion. That in a sense, what we've been talking about is recursion all the way down.
In the end, I think this whole thing is pretty fun. It's short, like this, but it's pretty fun. And so is this conversation. You know, I mentioned to you, I find going through some difficult stuff personally. Your passion for what you do is just really inspiring. And it just lights up my mood and lights up my heart. You're an inspiration for, I know, thousands of people that work with you at MIT and millions of people passing away. It's a big honor for you today. This is really fun. This was a pleasure. Thanks for listening to this conversation with your Rabbi. To support this podcast, please check out our sponsors in the description. Now, let me leave you with some words from Albert Picasso. Every child is an artist. Challenge. Staying an artist will grow. Thank you for listening. I hope to see you next time.
Let's imagine we have a black rat who invites people on stage. And let's suppose they invite a black person on stage. They're perfectly happy for the black person to fill out. They invite a white person on stage. The white person doesn't, sort of mystified, but it comes on stage and fill out what the rapper says, including the infamous word, and then the black rapper gets mad. Imagine a white comedian who satirizes, pokes fun at that. And in poking fun at that, says the infamous word. Am I angry? No, I'm not angry. Not angry at all.
Following this conversation with Rabbi Kemper, professor at Harvard Law School and author of many seminal books on race, law, history, culture, and politics, including specifically on affirmative action, criminal justice, policing, and the topic explored extensively in this conversation, the single most powerful word, slur, in the English language, the N-word, with a hard R at the end. Randall has written a book with this word as the title, N-word, a strange career for troublesome word. Please be warned that Randall uses this word throughout this conversation, deliberately and skillfully, to discuss its power and its role in history of the United States. I don't intend to shy away from controversial topics like this, and I work hard to handle them thoughtfully and thoroughly, with respect and empathy. Often, with several guests who have very different perspectives on the topic. In the end, I believe in the power of long-form conversations to heal divides, by furthering understanding of human nature, of human history, and the full diversity of the human experience. This is the Lex Friedman Podcast. To support it, please check out our sponsors in the description. And now, dear friends, Ms. Randall Kemper. You wrote a book whose title is The N-Word, spelled out with a hard R at the end. So let's start with the history of this word. What is the history of the N-word?
The word you're referring to is nigger. The book that you're referring to is Nigger, the Strange Career of a Troublesome Word. The word dates back to the 16th century. It's got a long lineage of words. Basically Latin, basically Spanish, basically NIG, black in various formulations. We don't know actually how the term nigger became a slur. So there were words that were close to NIGGR that we used in various ways. For instance, NIGG, UH, NIGG,
sometimes it was used in a way that seemed to be just purely descriptive. We do know that by the early 19th century, it had become a slur. It had become a derogatory word about which people could talk. But exactly how that came about, no.
So it's been 20 years since the radio. What wisdom have you gained from all this experience? You may be having to interact with people, having to read, having to see, having to feel the responsibility.
This book has generated a lot of controversy. I thought it would. It's probably generated more controversy than I anticipated. It's certainly generated more different sorts of experiences than I did. So, for instance, I did not think that writing this book would prompt people to ask me to be an expert witness in cases. And over the past 20 years, I've been an expert witness in a number of different cases. I've been an expert witness in a case of murder case, various cases of assault. I've been an expert witness in cases involving tort cases, teaching emotional stress. I've been an expert witness in a number of employment cases. I had not anticipated that, nor had I anticipated the extent to which people would get in trouble for using my book. Every year, there are teachers who are suspended, who are fired because they excerpt a chapter of my book. Let's imagine I'm not imagining it, this has happened. A teacher is teaching, for instance, the Mark Twain's Huckleberry Finn. The word neighbor appears in the book over 200 times. The teacher, trying to be earnest, trying to be sensible, trying to be serious, will excerpt part of my book to acquaint students with the history of the book and maybe the history of controversy involving the use of the word in this particular novel. The teacher would give it out to teachers, hand it out to students, and there have been a number of teachers who've been suspended or worse because of that. Students who get upset, go home and tell their parents. The parents have stormed the school and say, this is terrible. The teacher is, quote, using the word nigger in an offensive way, and oftentimes administrators will basically abandon the teacher. And whenever this comes to my attention, I write, and I'll write the superintendent of schools, or I'll write the principal, or sometimes I'll write an opinion editor of a piece for a local newspaper. But every year, there are teachers who are disciplined for using the book. I had not anticipated that.
And what is the nature of the letter or the op-ed that you write on why they shouldn't be disciplined, or to the degree they should be or shouldn't be?
There's not been one case. That has come to my attention in which it was even remotely sensible for the teacher to be disciplined. And what I say is that, frankly, I go through what I write is almost a synopsis of my book. Number one, this is an important word in American history. It is a word that is explosive. That's why people get so upset. It's a word that's volatile. It's a word that has typically been used in a terrible way. It's a word that is part of the soundtrack of racial terrorism in the United States. So people ought to know about this word. I mean, if you're interested in knowing the real history of the United States, if you're interested in knowing about lynching, if you're interested in knowing about the way in especially young people. You tell that to young people, they nod, they read and understand that. But then what? But then they turn their radios and they turn on, they listen to Spotify, they listen to some of their favorite entertainers. They listen to Dr. Dre, they listen to the Ghetto Boys, they listen to, Snoop, and they listen to NWA. What do they eat? They listen to stand-up comedians. They listen to Dave Chappelle. They listen to Cat Williams. What do they hear? They hear the word nigger or nigga being used in a lot of different ways. And so they need to know about that as well. What is it? How does one explain the fact that Dick Gregory was a comedian, activist, friend of Martin Luther King Jr., a true activist. He had a flourishing career as an entertainer that he abandoned in order to struggle for racial justice throughout the United States and in the East Side. How does one explain the fact that he wrote several memoirs, but his first memoir is called Nigger, a memoir? How does one explain that? How does one explain the way in which, how does one explain Richard Pryor? And Richard Pryor's best album is That Nigger's Crazy. Well, was Richard Pryor trying to put down black people? How does one explain that? One can only explain that by getting deeper into the word, by understanding that yes, this is a word that has been used in a derogatory way. This is a word that has been used to put people down. This is a word that has been used to terrorize people. You not only that, but you also have to know that this is a word that has also been put to other issues. There are artists, there are entertainers who have used this word, like Dick Gregory, to put up a mirror to American society and say, look at this word, and look at the terrible way in which it's been used. We don't want to look away. No, don't look away. We're not going to know euphemism. No asterisks. No N-word. No nigger. And we want you to look at that. And we want to talk about that. James Baldwin. There was a documentary about James Baldwin a couple years ago. Highly lauded documentary. Title that was given this documentary, I Am Not Your People. That's not what James Baldwin said. Anybody can go to YouTube right now, take a look. James Baldwin said, I am not your nigger. Well, James Baldwin wasn't trying to cover up. He wanted people to face the facts of American life. And it seems to me that if you're a teacher and you want to have your students face the facts about American life, well, you've got to graduate with me. Now, let me just quickly say, teachers have a tough job. And we're talking about students. Of course, there's a wide range of students. Am I saying that one ought to give my book to kindergartners? No. Kindergartners probably not ready for such a third graders, probably no. Not third grade. If we're talking, however, about people in the 10th grade, 11th, 10th grade, can we go book? Yeah, sure, absolutely. 11th graders, 12th graders, people in college, there are people in college. There are people in law schools. Teachers of law schools have been disciplined for because the word nigger has come out of a teacher's mouth. Why? In a couple of cases recently, a teacher would be reading a court opinion. The word appears in the court opinion. The teacher pronounces the word ah. Students get up. the report the teacher. In some instances, these teachers can, in those circumstances, get good discipline. In my view, that's bad. And people ought to say it's bad. It's bad pedagogically. And frankly, in many of these instances, it's stupid. But I don't mind saying that. I think that some of these instances in which teachers have been disciplined, absolutely stupid. People say, well, the teacher used the word. Excuse me, used the word? It'd be one thing. It'd be one thing if a teacher looked at a student and called the student, get out of here. That'd be one, that'd be, fine. Discipline, that's bad. But that's not what's going on. You don't have none of these are cases in which you have an individual who is a stranger to another individual, and this word just sort of comes out. No. What we have is a class involving a person who is a teacher interacting with students, talking about subjects in which it would be perfectly understandable why this word would emerge as a such conversation. Now, under those circumstances, it's somehow wrong for a teacher to utter this word. In my view, the answer is no. And, I said that 20 years ago. I say even more.
Still, it is one of the most powerful words in the English language. And there's a kind of responsibility that we as humans should have with words,
Yes.
with statements. That word is not used skillfully, not used confidently. Even when just read in the legal transcript, can do more harm than good.
I agree with what you say. Yes, words are powerful. Words do matter. And so I'm certainly not suggesting that people be lax. I'm not suggesting that people be irresponsible. It's precisely because words matter that we need to be willing to face words and grapple with words and talk about words, about the history of words, precisely because words matter. And among other things, it seems to me it's important to understand that words can mean different things in different contexts. It's not the case that a word means the same thing in every context. The word discriminating. Sometimes it's a very bad thing. That person discriminates. And the intonation of voice means. I say, well, that person discriminates. Obviously, being disapproving. Implicitly, what I'm saying is that person distinguishes between things on an unjustifiable basis. The other hand, that person has discriminating taste. Well, that means something very different. That means that the person differentiates in a way that shows that they understand the difference between excellent, good, and not so good. And they think that that's a good thing. The words can have words can mean different things in different contexts. It seems to me that that's something that actually we ought to recognize. We ought to recognize and talk about.
Well, some words enter this territory of being slow. And it seems like when you cross the line to being slow, there's the number of contexts in which it's okay to mention exponentially decreases, right?
No, because the whole idea of slurs change. Yankee was a slur. Yankee was a slur in 18th century United States. slur today. New York Yankees. I'm a Yankee fan. I'm a Yankee. Queer. Queer. This is in my lifetime. There was a time queer you run away from. And that was a bad thing. Then, thank goodness, gay liberation movement. Gay liberation movement, basically, we're not going to run away from this. We're going to grab this quote slur and we're going to affix it to ourselves. And we are going to repurpose it. Now, the word queer, again, can it be a slur? Yeah, it is a slur that have to be. And it seems to me that it's important for people to know about how a word is simple. In some contexts can be a slur, in some contexts it doesn't have to be. So the whole idea of what's a slur, that's a complicated idea in and of itself.
It's very complicated. It's, let me say, almost fascinating how language evolves. But if we were to kind of have a minute-by-minute evaluation of powerful, intensely slur-like words in the world, I think the N-word, the heart of our idea, Tyler Yiffler, is number one on that list.
Well, probably so. And of course, that's one of the reasons why I wrote a little book.
Yeah, but it hasn't, even since you wrote a little book about it, it seems like it's maintained its number one status. You mentioned queer. It's maybe queer was in the top 20, I don't know, for a while, and now it's sliding into the top 1,000. And the N word at the top.
You're absolutely right. The origins of this book, I clearly remember. I was at my office and I was thinking about lecture topics. And I get invited to give lectures. And I was thinking, well, what might make for an interesting lecture? And all of a sudden, the word nigger popped into my mind. And this is a word I've grown up with. I mean, there's never been a time in my life when, at least in my conscious life, in which this word's been answered. I mean, in my household, my parents are black people. My parents were refugees from the Jim Crow South. I was born in Deep South, South Carolina. In my household, I heard the word nigger used in every possible way. I heard it used as a slur. I also heard it used with respect to people who were crazed. You know, my father, clearly remember my father, whom I repeat. That's the smartest nigga in the world. The greatest nigga. That's the baddest nigga I know. He wasn't putting people down. This way he was. And I grew up hearing this word in various ways. And so I was thinking, this word. And one of the first things I did, I really was jumping up out of my seat, running to the library, Oxford English Dictionary, get this word first appeared in English, there's the history of the word. And then, what really sort of grabbed my attention is I get my computer going, and I ask the computer system, give me every case, every federal court case in which this word appears. And that was cases. And then I said, oh my goodness, this is really interesting. And then I started just cataloging all the different cases. There came a point, I'd say probably about a month of this. I compared the number of times nigger came up with other sorts of slurs. So, for instance, kite, K-I-K-E, long time, derogatory word for Jews. How many times has this word come? There was a time in which the word appeared, but nothing like the infancy. Nothing. What about what? What about, I just, let me just take a look at all the slurs. Nothing came close, not even remotely close. So I think it has something to do with, the uniqueness of the color line, particularly as it pertains to African Americans. I think that the fact that nigger occupies such a unique status in slurs, I think that's a reflection of the unique stigma that has been imposed on Africa.
It's hard to know the chicken or the egg. Why one word is able to so distinctly and clearly encapsulate this struggle between races, whether it's over American history. But it didn't have to probably be so, but it came.
It became that, not only that, but of course, the nigger spurred other slurs. So, Arab, sandwich, the Irish, the niggers of Europe, women, the niggers of the world.
John Lennon even has a song.
That's right. Well, the Yoko Ono. So, I mean, it's a slur that has spawned other slurs. And again, that's why this is quite unique.
But are you conscious? Are you deliberate when you're saying this word? So let me just say from personal experience, maybe my upbringing, where I came from, in my daily life, I don't think I've ever heard that word with a hard R said as often, used clearly in my life. I've heard it today, I've heard it in my entire life, and I think there's a few people who listen to this, they'll be listening to this, will be very uncomfortable. I would say not in a bad way, probably in a good way. I'm uncomfortable now, and I'm almost introspective and trying to figure out why I'm uncomfortable. And I think even the title of your book is making me think that. Just looking into my own mind and trying to understand what's going on. Why does it so much power? Are you deliberate in that action? And by the way, not only if people listening to this wedding, this will be on YouTube in part. And YouTube, the people on the other side of this wedding, what do you do with this?
Well, am I deliberate? Yeah, the answer is yes. And let me unpack that. First, that's right. Am I deliberate? Yeah. I deliberately wrote a book called Nigger, the Strange Culture. And was that deliberate?
What the title
The title could have been word. Sure. The title could have been a book about a word that causes pain to be. There are many titles I could have used. Did I want a title that would be provocative? Did I want a title that would grab people? The answer to that is yes. I'm a writer. I want people to read what I write. But was I being sensationalistic? Well, if you want to put it like that, yes. I'm not embarrassed to say that. And, I'm sure that when people write books, they think really hard about their titles and they try to get a title that will, grab people's attention. I know people, respect people very deeply, who never utter this word. Talk with people, they can say, was on one of these call-in shows early in the morning. Time came to call in. 7 o'clock, called 5 to 7. Right before I go on, the host of the show says, "Oh, by the way, we have a strict policy here at the station. We never use this word." And I said, "Well, gosh, I wish you had told me this earlier, because this means that you're never going to pronounce fully the title of my book." She said, "That's right." And I had to make a choice right then and there. Am I going to go on or am I not?
What you did?
I went on, and I abided by the station's rules, and fine, had a perfectly fine conversation. And, there is a place for euphemism. The American language is a very supple language. There are lots of words that one can use. I do not get angry with people who don't, they say as a matter of principle that I can use flip flop. I'm willing to, I understand where they're coming from, and often I will defer to their wishes. All I say is, I want people to understand where I'm from. I'm not just using this word willy-nilly. There's a pedagogical reason. There is a reason for why I'm saying what I'm saying. There's a reason why I use the word.
Can you make the case why using the word is a good idea? You make the case, the amended case why it's a bad idea. Maybe you've heard from some critics
Yes.
who said that you saying this word out loud is actually causing a lot of harm. Not like harm because people's feelings are hurt, but increasing anger.
Yeah. Critics. Let's start with the critics. One, again, going back to when the book was first published, I remember going to the first bookstore, and I talked about the book, had a very, talk, asked questions, and the last comment wasn't a question, but the last comment was made by an elderly black man. Called on me and said, "I listened to what you had to say, and I appreciate what you had to say." But he said, "But I remain unconvinced." And I remain unconvinced because when I was coming up, this word was used to put me in the back of the bus. And this word was used to prevent me from growing. And this was the word that was used to justify me never being able to achieve it. So to me, this word has only one meaning. It's a terrible word. I'm never going to use the word. It hurts me when I hear people use the word, especially those who don't even know anything about the history of it. And you go on to say, I think that your book, though well intended, is probably going to be seen by some people that has given them permission to use the word. Then he stopped. And I thought there was a lot of power behind that gentleman's comment. I think that what he said was probably correct, insofar as there are probably some people who read the book. There are probably some people who are listening to our conversation right now who will think that I'm giving people permission to use the word. I said that I want people to understand the word. I think that there is a burden that comes from every utterly like this. But that's a critique, and I think there's strength in that critique. I'm not going to say that that's a critique. I think that there is something to it. And by the way, I should say, and that's why I would say that meanwhile, that's right. If this word comes out of your mouth, you are taking on real responsibility. So for years, it doesn't happen so much now, but there were, let's say, for the first 5 years after this book was published, I would a week. And it would begin like this. Dear Professor Kennedy, I read your book and I'm calling to answer your question. And as soon as I saw that, I knew the question. What the person would say, I like rap. And I like rap. I'm white. And I have black friends. We listen to rap. We drive in the car. We're listening to the song. We start humming along, singing along. And my black friends sing along. And the nigga or the nigga comes up. They sing. And I don't know what to do. Is it wrong for this? This happened so often that I'd say about the 10th time I got in such an email, I wrote a form letter because I didn't want to just, take up time writing sort of crafting letter after letter. So I wrote a form letter, and basically that's flattered that you asked me, because number one, you should have a conversation with your friend. Number two, no matter what your friend says, let me put something else for you to consider. Let's suppose, for sake of discussion, that your friend says, "Oh, it doesn't bother me. I know where you're coming from. You're just enjoying music. I don't think that this is a racist audience." Let's suppose that your friend says that. That doesn't end because let's imagine the following. Let's imagine that you're in a theater and you're waiting for film to start, and you just talking with your friends or singing with your friends or just kicking back with your friends, and we're talking about bigger this or bigger this, and you say you're the white man, and the next thing you feel is a fist, a big fist in your mouth that has been launched by a person that you did not see who was right behind you. All this person saw was a white person saying the next thing. That's not, in some sort of overheated scenario coming from some law professor's mind. That is a very plausible scenario. So you have to be worried about lots of things, including mistake. So my advice to you, is be prudent. I would say clear the word unless very certain, unless you feel you're in a position to defend yourself, defend what you do. But the prudent thing would be to stay prudent.
There's so many questions I'm going to ask there. One is about the violence and legal aspect of that. It's very interesting. But, I do want to bring up something I probably disagree with you on, which is you say that there's a difference between the different variations of legal. Or maybe you don't, you just brought this up. So there's the version with the ER at the end, version with the GA at the end, and then GRO. These are all different versions. And I feel like in that list of powerful words, I feel like there's a distinction.
Yeah.
I feel like the number one spot is the one with the hard R. And I don't know if maybe you can try to shed light, but I feel like the one that ends in GF is really in terms of modern culture. So we talked about the evolution of the words with queer, for example. It feels like because maybe there's a rap, because a comedian, because it's become much more lost so much of power.
Well, I think there's a difference between nigger and nigga. People make a distinction between them. And I think that to the extent that lots of people make a distinction between them, I think, just as a sociological fact, they are different. I think that people a white person says nigga, and they're and they're sort of criticized about it. They say, well, I didn't say nigger, I said nigga. I believe most people who are mad at them overstated. Now you please, so nigger and nigga, I would put different categories in Negro education. Well, you're true. Happy to. Negro is a also controversial. Um, but Negro never been viewed by a substantial number of people as a derogatory term, at least in the same amount of animus, the same amount of it's a very different kind of word than Negro. I mean, after all, Negro, Martin Luther King Jr., all these great orators, Negro. You read the work of the great W.B. Du Bois, Negro. You read the work of my boss. So for instance, I use the word Negro. I use African American, Black, Italian American, but I also use the word Negro. Now, there are some people particularly mad at me because of the word Negro. And we can say, for instance, there's students who don't quite exercise. They'll say it. I can give you that shirt. You could go up and say, listen, I'm using the word Negro if it's purely because of the historical time period that you're using. Is that why you're using it? Or are you using it for points? And often I say, well, I'm using it for my voice. I say, well, I'm offended. You think this is, that's old-timey, it's derogatory. When this first came up, I said, let's pause for a moment. And I'll take that under advisement. And let me look at this. And I ended up writing an essay about the history of the terms that Black people have used to describe themselves. It's a long list. Black, colored, African American, Negro, etc. So I go through all that and I said, now let me just tell you, I know for certain when I started using the word Negro often in writing. I can date it. 1983, the summer of 1983 was when I started using the word Negro in my professional life as a lawyer. And I did it, it's very specific. I did it because my boss demanded Negro, capital N. Now, who was my boss? My boss in the summer of 1983 was Associate Justice of the United States Supreme Court, Senator Rothschild, known as Mr. Civil Rights. Now, it seems to me you're telling me this word is so out of bounds, this word is derogatory, nobody should ever use this. Does the fact that Thurgood Marshall demanded that I use this word, does that complicate things? Oh, really? And so I think that people here, it's utter. I mean, I've heard people who don't know very much that want to lecture me on words because they know three sentences about current fashion. And told them. By the way, I push it further. I sometimes use the word color. Some people National Association for the Advancement of Colored People, the NAACP. They haven't changed their name. And as far as I'm concerned, it's a wonderful organization. There are people who have used the word colored. That's what my grandmother colored. Perfectly fine as far as I'm concerned. So, again, we get lots of different words that one can use different formulations. Understand that people have different preferences. Fine. I have my preferences, at least nowhere.
Still, words have power to hurt. And there's a lot of reasons that I could see justified the use of the word in this current form, as you said, in this conversation as you're using it. One of them is perhaps fighting for the freedom to be able to use those kinds of words. So we ask about freedom of speech and censorship of the word. Should the use of that word be censored, for example, on social networks? So we can come up with different places. We can say university campuses, maybe op-eds, or I don't know. But I think social networks currently is a very interesting place. There's a lot of conversations that are happening on there. There's ability, technical capability to set, to remove the ability of people to use the word. Do you think they should be allowed to use the word?
My response is it all depends on the way in which the word is being used. If the word is being used to intimidate, if the word is being used to terrorize, then yeah, along with lots of other words. But you could have, I could use the word, I suppose, gentleman. And I'm sure that I could conjure up a way in which that word could be used in a intimidating way. So, would I be happy if there was a technology that always blanked this word, N-I-G-G-E-R? I would be against it. For one thing, it would erase the names of one of my books. And I think, I think the book actually has a lot of useful information, some useful points. And by the way, let's imagine a world in which there was a technology that blanked every time N-I-G-G-E-R. You would have, what would that do to novels by James Baldwin, by Toni Morrison, what would that do to the speeches of Malcolm X, Martin Luther King Jr.? What would that do to the comedy albums of Richard Pryor, Cat Williams, David Chappelle? What would that, if one could have phased that out, would one want to have all of those blanks in important literary and political performances? No, I don't want such blanks. What I would want the word is there and for people to understand how to deal with it. And by the way, you use the word hurt in all things. So let's talk about hurt. I think we need to be more careful with the way in which we deal with hurt. Because people can be justifiably hurt. You can have justifiably hurt feelings. And if somebody has justifiably hurt feelings, I then think that we should turn to the person who has hurt those feelings and say, you have acted wrong because this person's feelings are justifiably hurt in relationship to what you've done. On the other hand, there are people who have hurt feelings, and frankly, it's unjustified. So just imagine the following. Let's imagine that I give a talk about the greatness of Martin Luther King Jr. And then let's imagine that a Klux Klansman comes up to me after my talk and says, "Oh, you have now hurt my feelings. What? Am I supposed to be? Am I supposed to apologize? Am I supposed to be regretful that my talk about the greatness of Martin Luther King Jr. has hurt feelings of the Klansman? No. My response is going to be, you need to reevaluate your feelings because actually, your feeling of hurt is unjustified. And no, there's no apology coming.
But there's a kind of line that has to create only maybe the word hurt can be used if you try to avoid hurting a small fraction of society that is mentally weak in a way where everything hurts them. That's the wrong way to build a society. But if we flip that upside down and say trying to maximize the amount of love in the world, and think about decisions we make in terms of language we use to try to maximize the amount of love, not just short term but long term. And that's what freedom of speech is very powerful. It's a short term painful thing often, but long term beneficial thing. Just having freedom. And so there is one question that starts to come in. How much how do we think about its use on the internet on college campuses in a way that maximizes the amount of love and compassion and camaraderie?
I think it's good. I would associate myself with your vision. How can we maximize love? Well, I like that. I bet that's great. So let's take that on. I doubt that the way to do is to erase the infamous image. I doubt that the way to do it is to say to people, you understand that your feelings are really hurt and you do all that you can to avoid this symbolic action. You're going to do all that you can to suppress it so that you can have a more loving view. I doubt that that's the way to do it. I think a better way to do it would be to fully educate, including education such that you see that over there, that is uniform of the insects. I want you to be educated about I want you to do with the uniform know what it's about. You're not terrorized. You're not immediately, you don't see it instinctually as you start wailing, crying. You don't see it and say, I'm traumatized. You see it, you understand it, somebody else with that. It seems to me that confidence, that strength, that power would be a better way of equipping us to have a more loving. And by the way, just so you know, I would say that about the swastika. I would say it about the skin groove. I would say it about all of the things that we're talking about. It would be better, educated, so that they are not traumatized.
So do you the N-word should not be removed from health fair, digital health fair, and these
Not at all. In fact, it seems to me that the polarization of these great artists literally it's highly objectionable. Highly objectionable.
what is it okay to really be?
But, Here we need to focus on the word say. Is it ever okay for anyone? You know, black, white, pink, yellow, up here, red, orange. Is it okay for anyone to use this word in a way to put down people, to terrorize, to intimidate people? Answer no. Well, you know, and I say that, and I sort of, I think about that. I see black people use this word to try to intimidate, put down other black people. Bad. So it's black person, white person, black man. On the other hand, um, imagine a white person who is giving a lecture on the history of the United States. A lecture on the history of the and in giving that lecture, quotes the white racist politicians who, until fairly recently, used the infamous words. So imagine a white history professor giving a lecture about the history of American racism and says, in 1948, this is what so-and-so running for the presidency of the United States said, and then quotes a paragraph or two in which the infamous N-word is featured. Is that bad? No, that's not bad. No, that's not bad. Sounds like a perfectly good lecture. And I'm glad that you put the infamous N-word in there so that we can see that as recently as 1948, people who run for the presidency of the United States openly used N-word. That does not bother me. I'll say this too. Somebody says, well, you know, nice job, Kennedy, but you limited over put it in the academic setting. What about other settings? It does not bother me. Let's imagine somebody who's a comedian, a white comedian, who is satirizing word usage. Let's imagine a white comedian who is satirizing our current practice and wants to poke fun at the way in which, let's imagine we have a black rapper who invites people on stage, and let's suppose they invite a black person on stage, and they're happy with the black person. Without a white person, the white person doesn't sort of mystify, but it comes on stage and fill out what the rapper says, you did this and then the black rapper gets mad. Imagine the white person who satirizes, pokes fun, and he pokes fun at that, says the influence. Am I angry? No, I'm not angry. Not angry.
What if in the process of satirizing that comedian's not very funny?
You say that bad joke, you not funny. I don't object to the use of the infamous N-word, but you're not funny.
But because there's a line, the joke is not funny, it just seems like the comedy is used as a cover to actually say something to people. It's an interesting thing about comedy. I feel like the funnier you are, the more you get away with. And that's something to do with the thing we said earlier, which is use words that have power. You should do so with skill and confidence. And the responsibility of doing skill.
Again, the cases that I'm most familiar with are the cases involving teachers, professors, academics I object sometimes to say because I suspect that this teacher just wanted to say the word. That all of this is because of pretense. Do I, in my sense of it is, if it's pretextual, that's bad. But in my experience, I have not seen it.
I agree with you on that because I do see people kind of have this fly towards the right desire to say something controversial and edgy, and they don't realize that there's a responsibility, that there's a skill. You shouldn't just say, actually, when comedians first start out, that's not to say edgy stuff. That's totally not funny. You realize this is not edgy. So, like, if you're cooking as a chef, poisonous fish, there's a responsibility in how to cook the damn thing so you don't poison people easily.
I would agree. If you question, let's imagine that somebody produces a new set of Lenny Bruce tacos. White, Lenny Bruce used the term nigger in his set.
Sure do.
Question, would I want Lenny Bruce's albums now to be purged of the infamous name? My response, absolutely not.
As another follow-on to the question, what you think? I've seen interviews with that the title of those interviews on YouTube and elsewhere would use the full word. What do you think about that? Should I use this word in the title?
My view, the answer would be yes. Again, there are people that are views, people who had a different conclusion. And, I respect a different way. Again, there is a place for those. I'm not offended. Let's imagine that you posted this and you had asterisks instead of spelling out. Would I be offended? No, I wouldn't be offended. I would prefer full spelling, but I would understand where you're coming from.
Here's the weird calculation. Which version of words use that? It's hard. Basically, your answers. Your answers do it.
I'm not sure. Again, there's certain questions in which if you're not gonna, you're not going to know the sociologist is going to be able to tell us that. So what do we do then? Then we go to secondary positions. And my secondary position is I don't know. One thing that I hold on to very strongly is the virtue of openness, the virtue of transparency, the virtue of freedom. And I feel as though if I'm holding on to those things, if I'm trying to engage in a serious conversation in which I'm trying to make other people understand me and I'm listening carefully to other people, I feel at ease. I feel this is going to eventuate to something positive. And, I feel okay.
You're at Harvard, you're respected in the history of Harvard. That said, you did write a book with the N-word in it, and you also have a lot of opinions that challenge the mainstream perspectives on race from all sides. Hopefully, we can talk about some of that. But what's your view of Harvard and universities in general in speech?
Yeah.
Did you feel
pressure in any direction. First of all, the title of this book, the content of the book, and in general,
Yeah, I am very motivated. I've been at Harvard since 1984. I think it is a wonderful place to work. There is not there. I have the various positions I've taken, particularly with respect to this book or all other books. What is Harvard University? Harvard University has done nothing but provide support, sustenance, encouragement. I think that people get down on Harvard University. I would say to anybody, imagine that the ethos of Harvard University became the governing ethos of the United States overnight. Tomorrow, we would wake up in a much better United States. I've been supported by Harvard University. I think well of Harvard University. That's not to say that I don't have criticisms of it, but by and large, Harvard University, even by and large, overwhelmingly, it has provided me, it overwhelmingly provides my colleagues with work settings in which they do their work without fear. And that's a good thing. There's certain aspects of Harvard University about which I'm critical. Yeah, sure.
By the way, I think a few people right here roughly would disagree with you that if the ecosystem of the country would be a better place. But there's a lot of interesting ways to break that down. Harvard is not one either. There's a lot of things that are very interesting.
Yeah.
But one of the things that's happening is the disproportionate aggressive growth of the administration versus faculty. I think the power of the university shows the faculty students flourishing happens. The more you have rules and bureaucracy and all this kind of stuff, the less costly the university is.
I think that at my university and many universities, that's right. Too much bureaucracy, too much regulation, and are there dangers to freedom of expression at my university and other universities? Answer: yeah, there are. There are. So, and this is really hit home for me. There was a period of time which I was getting off of here. I got off of all boards. I was just doing my work. Forget it. I do my work, not to be associated with any organization. In the last 5 years, that has changed quite dramatically. One, there was I reassociated myself with various organizations, mainly organizations involving academic freedom, because what's going on on university campuses, and I have been, at least thus far, this hasn't pinched me where I live, but
You mean in the space of ideas?
in the space of ideas, in the space of speech, in the space of teaching, I have a good pitch, but I am concerned about that. So, for instance, let's imagine you're applying for a job. Let's suppose that you're seeking a promotion. At the university campuses, you are asked to give a deep statement, which you say, I plan to, one of the reasons why you should hire me, or one of the reasons you should promote me, is because I'm going to advance the DEI ambitions.
Diversity, equity, and inclusion for people who don't know. This is the general, the set of programs that most universities now have.
Yes. That's right. Use that as sort of basically what you're being asked to do. Whether they say it explicitly or not, they don't say this explicitly, but this is what they do. This is what it's up. What you're being asked to do is to say, I'm down with the diversity, equity, inclusion, ethos, program, policy, campaign. And here's what I've done that shows that I have. And therefore, I'm okay. Well, a lot of what I do would fit very comfortably in. But let's suppose that I did. Let's suppose I didn't like this. And by the way, there's certain aspects of the industry that I don't like. You mean to tell me that I'm being judged at an academic institution? Suppose I want to be a chemist. Suppose I want to be a physicist. Suppose I want to be out here, a critic of literature. I oppose this program. I don't, I don't think this is the way in which higher education should be. Should I have to, on pain of relinquishing my ability to be hired? Should I have to sign on to this? Just suppose, let's change it around. Let's not make it the DEI campaign. Let's make it a Make America Great Again campaign. What would we think then? Let's suppose it was something that said, instead of saying DEI, let's make it say the advancement of American capitalism as we know it. We want you to be down with that. What have you done? It shows us that you believe in the advancement of capitalism in America. Would I be happy about it? No! I would say no! Well, no respect to these, as far as I'm concerned, the DEI statement. Here's another one. I just work. I mean, there's certain things that are happening, and I must say, I'm in academia, but it's news to me. I did not know and wrote the research about positionality. So these are statements in which somebody writes an article. I write an article, and it's not enough for me just to submit my article to some law review or some other sort of journal. No, in addition to me submitting my article, I've got to give a positionality statement in which I say whether I am gay or straight, or what have you, in which I say my race, in which I say my nationality, in which I say my stance toward this ideological position or that ideological position. What?
Is this a kind of a standard?
I don't know how widespread it is. I know there's a very good article in the New York Times a couple of days ago about these positionality statements, and in fact, that's what sort of tipped me off. Somebody had told me there's a law review at my own institution. I had a friend who sort of mentioned this offhandedly. He said, well, I submitted an article to this journal, and I was really taken aback insofar as they did have me fill out a questionnaire in which I was required to state my race, state this, state that, state the other. And, as far as I'm concerned, what does that have to do with the proper assessment of somebody's work? This concerns me. I'm concerned about the fact that a little while ago you mentioned a little while ago, you mentioned the word and I was talking with colleagues a couple months ago, and somebody mentioned that this word multiple is one student was reading from the Supreme Court decision, and the word Negro was part of what they read out. And another student held up his hand and said to the student reading, hey, you should be careful because I find the word Negro offensive, and you need to be careful about either saying a thing that would be offensive. What should I say in those circumstances? What should I have said? And I've always said, I said, well, I was really interested to see if that had come up in my class. I would have said, well, frankly, I don't see the idea because I used to do it. And, part of the university is not as, on some island that is apart from everything else that's happening. These things are happening in other places. They happen in Stanford, they happen in Yale, they happen in Columbia. They're going to happen in Harvard. But thus far, and I'm most especially experienced in life at Harvard Law School. Harvard Law School is an open environment in which ideas are tested, fully, and because of that, when I say I have been fully supported Harvard Law School, feel that it is an excellent place in which to do work. I'm a fan. I am a fan, and I'm not embarrassed to say I am a fan of my workplace, Harvard Law School. Very happy to do this.
Zooming out, in general education, we call it critical race theory. Can you comment on what are your thoughts about this kind of perspective on race and race in America? To the degree that it's becoming a part of the education program.
Okay, so the first thing,
what is it?
Well, the first thing I would say about critical race theory is that critical race theory has become a term, so I'm going to put quotation marks around the term critical race theory. In a minute, I'll talk about critical race theory without this. To begin with, I'll talk about critical race theory. The reason why people are talking about critical race theory so much is because politicians, mainly Republican, right-wing politicians, have created a boogeyman. Critical race theory with quotation marks. They have created a boogeyman, and they have tried to make it seem as though this boogeyman leaves all sorts of ideas that Americans should know and that Americans should feel. And they've created this boogeyman, and they've done a very good job of creating the boogeyman. They have mobilized sufficient public support such that there are a number of states that have passed laws prohibiting the teaching of so-called critical race. And the first thing I want to say about this is that this campaign, these laws, these various policies, telling teachers, don't teach this and don't teach that, you can't use this book, you can't use that book. This is a frightening encroachment on freedom of speech, freedom to learn, freedom to listen, freedom to read. That's terrible. It's one of the most frightening things that has happened in American life So that's the first thing I say. Now, I say, critical race theory is a sort of a, you could have a nice conversation about actually what it is. One way of viewing it is to say that, well, critical race theory is a community of ideas that comes from a community of people, the community of people in legal academia, in the period starting in the middle of the 1980s. It would be associated with people like Derek Bell, associated with people like Crenshaw, people like Charles Lawrence, people like Richard Rosado, Suda. And these are folks who held, embraced a couple of, they articulated a couple of propositions. One of the propositions was that liberal race policy was insufficient. They would say that the racial policies of a person like Miles Rothschild, the liberal racial policies were insufficient to grapple fully with the pervasiveness and the depth and intensity of American racism. Their basic claim, and I think by the way it's a good claim, their basic claim was that American racism is more central, more deeply embedded in American life than most people perceive, including liberals. I think there's a lot of truth to that position. But then they also took on some other propositions with which I was very strong disagreement. So I think it's perfectly fine to say that racism is a force in American life that is deeper, more pervasive, more stubborn, more resilient than people often understand and perceive. But then some of the folks, in critical race theory, push further. One of the propositions that some of the people in critical race theory took was the proposition that America is doomed to always be a country that would be governed according to the dictates of white supremacy. Derek Bell, who was a colleague of mine and a friend, took that position. He talked about the permanence of racism in American life. He took the position that the various changes that this has wrought in American life were really, maybe cosmetic. They didn't amount to anything. Derek Bell took the position. It was the second Reconstruction, the Civil Rights Movement. It made changes, but at the end of the day, black people were still, after the second Reconstruction, were still in a position of almost, some of them would even say neo-slavery. Well, I think that's ridiculous. The second Reconstruction changed a lot. And as for neo-slavery, we're talking about a black American was president of the United States between the years 2008 and 2016. I mean, what are we talking about? There's been a tremendous change, and I think people ought to understand that. Now, am I saying that everything is peachy and all right? No. The United States is still, to a very large extent, still a dictatocracy. But that doesn't mean that a lot hasn't changed. A lot has. So I disagree with certain types of critical race theory theory and have been very outspoken. Here's another one about the because we talk so much in our discussion about freedom of speech, freedom to teach, freedom of listening. Another big problem that I think with some of the people who call themselves as critical race theory people has to do with their attitude towards freedom of speech. Some critical race theory people think that the American legal system is wrong in the latitude that it gives to what they call hate speech, or the latitude that it gives to what they would view as racist beliefs. Some of the people who associate themselves with critical race theory that racist beliefs ought to be expunged with the aid of state power. Well, I'm against it. And, I think we're at a moment, an ironic, which actually it's the right wing that has embraced some of the ideas that were championed by some of the people who call themselves critical race theorists. They say, oh, we ought to expunge hate speech. Well, the right wing saying this critical race theory, that hate speech, so let's expunge it. And so I've been very outspoken in my criticism of some of the illiberal dimensions of critical race theory. So I've been a critic of certain features of critical race theory. I have applauded certain features of critical race theory. Critical race theory, there's some aspects of it that I think have been useful. There's some aspects of it that I think have been profoundly wrong. So that's where I am. And I certainly, above all, I certainly am against any efforts to remove it from the intellectual universe. It is a part of our intellectual universe. People know about it, and people ought to debate it, and people ought to be free to make up their minds to conclude what they will about the strengths and weaknesses of critical race.
And we'll talk about the pessimistic and the optimistic perspective on race in the history of the 20th century. I think they're very interesting perspectives. Before that, let's look at the current moment. And we had a conversation with Glenn Lowry and John McCord. And from there, it became clear to me, and John, it clear how important to the conversation about race is diplomacy and to race society. That's where a lot of African Americans feel is sort of the pinnacle of racism. People that believe there's still racism in America. There's still a lot of racism in America. That's what it is. So, to what degree do you think there's widespread institutional racism?
Yeah. Well, my first book was a book called Race, Crime, and Law. And
1997. Time flies.
Unfortunately, the impetus behind that book stands. That book was propelled by a sense that, with respect to the administration of criminal justice, African Americans feel deeply aggrieved, and they feel deeply aggrieved with good reason. And they feel deeply aggrieved with good reason in at least two dimensions. On the one hand, under protection. In fact, in that book, the central theme of that was that Black Americans suffered from under protection. We take a look at the broad, the broad trajectory of American history. We ask yourself, in what way Black Americans were most suppressed? Well, take a look at the antebellum period before the abolition of slavery. Before the abolition of slavery, in the locales where most Black people resided, the slave states, in a lot of those areas, was there a crime called the murder of a Black person? Answer, for a long period, the answer was no. There might have been a tort if the white person killed the slave, that person could be sued because they had injured the property of another, paid money, but had they committed a crime? Answer, no. In the antebellum period, were Black women protected against the crime of rape? In most states, the answer was no. There was no such crime. Let's go to after slavery was abolished. Then we hear lynching. From 1890 until, let's say, 1930. Well, 1890, it was probably, I would say it was probably on average a lynching every day. Well, it goes down. That was the case in the 1890s, probably the first decade of the 20th century, and then it starts going down. What was lynching? Lynching is about Black people being executed outside the law. Did the legal system do anything about that? Show me cases in which people were prosecuted criminally for engaging in lynching. You come up in most places with a no state. Black people suffered the under protection. Do Black people still suffer the under protection of the law? The answer is yes. And people talk about the Kerner Commission report, 1968. Black people were asked, with respect to the police, what's your main complaint? In many places, the main complaint was, we don't have police protection. When things happen to us, when our houses are broken, when our businesses are encroached upon by robbers, when our businesses are robbed, when we are assaulted, nothing happens. The police protect white people, they don't protect us. Under protection. Our society right now, who is most liable to be raped, robbed, the victim of assault, what have you? Black people. And it's not even close. Under protection. So that's one way in which the administration of criminal justice harms Black people by not doing what government is supposed to do, which is protect us. We And this is the thing that gets most attention. And it's important. I think that the underprotection story does not get enough attention. But there's a second story. The second story is that black people have historically and still today, black people are subjects of invidious racial discrimination when it comes to police action. So, walking down the street, we have a black person who's, let's say, 20 years old, and a white person who's 20 years old. Let's make them men. Both is walking down the street. And the attitude of the police towards these two. An attitude, is a complicated thing, which can show itself in various ways. It can show itself in the look. It can show itself in who gets the look. Black person's, walking down the street or running down the street. White person's walking down the street or running down the street. What happens is that police, let's suppose that who gets the second look, who is followed, who is detained for a moment.
Well, some of it, just on a small tangent, I apologize to interrupt, but apathy is an interesting one because a lot of the interaction doesn't show up in the data. Those are detained, for example, start showing the data. Before that, second look, third look, first look. This is where the gray area conversation happens. Very much so. Culture and society happens in the stuff that doesn't often show up in the data.
Yep. So I tell you, this really came from several years ago. I was in New York City. It was a time when there was a lot of discussion over the stop and frisk, basically, racial profiling. I was walking. I was in Harlem, walking down the street, and frankly, the police weren't bothering me. I was walking, the police weren't bothering me. I'm of a certain age. I did notice though. I was looking at the police, and the way that the police attitude had to do with body posture. It had to do with the choke. We've got stuff in the world. It had to. I noticed. I'm walking the street. I'm walking home. There are white people in the street. Some people are black. Some Hispanic. The level of contempt, the level of animus, the level of unfriendliness that was pouring off the police. They didn't say anything. No, they didn't say anything. It was palpable. I could feel the attitude that was being directed at the young black men. And the thing is, it's not as if this doesn't matter. It matters because the way these young black men knew, they felt the contempt that the police were showing. And this was going to have a consequence. The consequence of this dynamic is, let's imagine that the police did say, excuse me, what do you want? Now, if you have been feeling this contempt, if you feel like the officer who's asking this question doesn't like you, you don't think about it, you just don't like it on sight, you might answer a certain sort of way. You're not going to give the cop the benefit of the doubt and basically think, this is just, asking the risk, probably just trying to make it safe. that's your feeling. You know, police was just asking you this time to say, well, officer, the reason why I'm here is such and such. And, you know, thanks for your service. That's one response. Another response is, I'm not gonna tell you that. You know, I'm not gonna tell you anything. I know that you don't mean me. I know that you don't mean me anything. I'm not gonna tell you anything. Am I free to leave? Then the cop then says something that, you know, after 5 minutes, what do you have? You have an altercation. And I felt that. And that is part. And you're absolutely right. That's not written down. It doesn't get poured. It's there. It's an important part of street life. It's an informative part.
He has ripple effect because that young black man will probably have shit about that cop later that day, and the narrative persists. And the cop is falsifying shit, and there's this narrative stuff. And I think the content is such a powerful thing.
So hard to disentangle. You're absolutely right. The young man was supposed to be stolen here, quote, well. He's going to go, and we talk with his friend, and he's going to say, let me tell you what just happened to me. And his friend's going to say, oh, yeah, that doesn't surprise me. Let me tell you what happened to me. And, you know, for 2 hours, this goes on. The anger, the feeling of humiliation, the feeling of aggrievement grows. It's disseminated. And that's part of it. But that's not all of it. That's you know, that's an important part of it. But we have even worse things, because then you ask the question, well, what about things we do wrong? I know this from, you know, from my teaching. This was brought up. There was a lawsuit in New York City. And notice I didn't say, you know, I didn't say Birmingham, Alabama. I didn't say Atlanta, Georgia. I didn't say Tallahassee, Florida. I didn't say, you know, the Deep South. I didn't say Montana. I didn't say Idaho. New York City. You know, cosmopolitan place, metropolis. In New York City, the police were challenged with respect to their policies. The judge wrote a very lengthy opinion, and the facts were all out. And the facts were really quite almost people, there were black men who were stopped many times. It wasn't just once, over under circumstances in which they ought to not be stopped. And, you know, this has real consequences. It doesn't just show up here, though, of course. It also shows up in other places with respect to the administration of justice. And still have a big problem. As you mentioned, you know, the police. You ask yourself, who are the state agents that are most consequent? The police. You walking down the street, what other agents have guns on them? What other agents are off the highest level wall to shoot you under certain circumstances? It's the police. The police are the most consequential agents of the state that those people are in with.
I mean, there's pushback a little bit of consequential in the physical sense, but if we return to the power of the psychological sense of contempt, I would say store clerks, stuff like that, and also deals with
They're not agents.
right. But if we look at the landscape of contempt, which is what the century plus, you can experience the same kind of contempt in all the aspects of society. But yes,
and take them to jail. That's an extraordinary.
But they also have, because of that, the leverage, one human to another, they have more leverage to be an asshole. To be the lesser, to lean into the lesser aspects of their nature. All humans can. Just to be an asshole, to show contempt. If you had a bad day, they have more freedom to do that.
Yeah, and that's why police officers are very important. I recognize, I mean, I know police officers. It's a very difficult job, a very important job, very important. Again, remember what I said about under protection. I want the police to protect me. I want the police to protect me from the rapist, the robber. So please, I'm with the police. You need good police. You need good police. For good police, you need accountability. And one of the scandals, one of the just absolute scandals of American law is the extent to which the police are not held accountable. It's absolutely remarkable the degree to which American law fails to properly hold police accountable. They have an important job, difficult job. I think they're very well paid. And as far as I'm concerned, we should make more money. They should be given the importance of what they do. They should have more respect, more. All of that is held accountable. And the way things are now, they're not held accountable. And every day we see the consequences in our newspapers or just talk.
So what do you make of the different perspective on this? To bring to the person that we probably speak with under his own, who wrote a book called War on Cops, and we often bring up the stuff that does show up in the data, should disproportionately exercise committed by Americans. And we'll also justify racial profiling on the basis of things how people's programs. And we'll also get into things like the Ferguson effect, saying that because of his pushback, and all the stuff that he's saying about police, in those areas, police will step back and find
And one of the things that I said is it's a debate that was sponsored by the Federalist Society, conservative legal conservative law students at law school. She made a presentation and they asked me to respond. And one of the things that I said was, when you're talking about the police, I'm disappointed with the reaction of some of my conservative colleagues because what are the sort of what are some of the important precepts of conservatives? One very important precept of conservatives: limited government. Limited government. You know, what conservatives talk about the tendency of government to overreach itself, governmental agents to overreach themselves. And I say, you're right. You're right. It's right on. Why is it that you somehow forget that when you're talking about the police? When you're talking about the police, you seem to be unaware of this tendency that is so much in your consciousness in other places. But now, when you're talking about the police, you make it seem as though I'm being paranoid when they talk about the danger of overreach. About the danger of overreach. Another thing with respect to what do why is it that conservatives actually embrace police unions and are the enemies of transparency? Why is it that you want to prevent the citizenry from knowing that Officer so-and-so has, there's been 10 incidents in the last year in which citizens have complained about Officer so-and-so? Don't you think that the citizenry ought to know that? Why is it that you want to keep that under wraps? So, overreach, transparency, the tendency or the problem of governmental corruption. Why is it that those sorts of things are forgotten in some conservatives? By the way, not all conservatives. Not all conservatives. There's some conservatives who have stuck appropriately so in their guns and have said, hey, we need to make sure that the police stay in their lane. We need to make sure that the police do not overstep constitutional bounds. We need to insist on transparency. There are some conservatives who have taken that line, and I salute them. But there are a lot of conservatives who all of a sudden become just, totally uncritical statists when we talk about the
To the folks that we don't believe for transparency. Of course, we see this kind of stuff in foreign policy as well, which is starting military conflicts, and a lot of supporters, at least with the Iraq and Afghanistan wars, were conservatives and hawks and so on. So there's a lot of hypocrisy. So maybe one question is, in this discussion about racism and policing, there's a lot of cops that might listen to this and feel like they're not being, the profession's not being respected, they're not being heard, not being respected to the difficulty of the problem they're facing. And
can I just interrupt? Yes, remember a few minutes ago. I mean, if I were in charge of things, I'd pay police more. In fact, much more. I do. Police have a very difficult job. Extraordinarily difficult job. I mean, for one thing, sort of maintaining the law. The law, that's a very complicated thing. The law. That's not an easy thing. I teach law. I spend a lot of hours with very smart people trying to understand the law. Very difficult. So here we expect people to understand the law at the same time that they are grappling with people, some of whom are violent. It's very difficult. I respect police officers, and I said we need police officers. You did not hear me say, by the way. So let's get that right. You did not hear me say defund the police, did you? In fact, to the contrary, I said defund. Actually, I want more funds for the police. I want to hold them accountable. I understand the difficulty of the job. I respect the police. I want people to respect the police. I also want the police to respect civilians and demand that they do. I am not a police abolitionist. Far from it. Far from it. Again, we need good policing. For good policing, we need good people.
to what degree, almost philosophically, maybe practically, do you think police should be doing racial profiling regime? It's a very difficult philosophical and moral human question.
Yeah. So, first thing we need to do, and here we get back is a early part of our conversation because we focus so much on the first part of a word. Here we have another word, profile. Question: what is racial profiling? Now, here we have in the weeds, have people talking past. I've been in conversations with police officers and debates, and we talk past one another because we're defining racial profiling very differently. If you ask, I've been in conversations with police officers, and they say, "Oh, I'm totally against racial profiling." And I said, "Well, sir, what do you mean by racial profiling?" Here's what they say: racial profiling is when police officers act against somebody wholly on the basis of race. That gets rid of the issue because most police officers don't act against anyone wholly on the basis of race. You could have the most racist police officer. That police officer is not going to act adversely against the 90-year-old black man walking down the street with a cane. Okay, so it's always if you define racial profiling that way, you're getting rid of the issue. The proper issue is this: should the police be able to act against somebody, taking race into account as a factor? So let's imagine that a black person is 25 years old, is walking down the street right next to a white person. Some people would say, you know what, under those circumstances, it's okay for the police officer to give 2 looks at the black person and 1 look at the white person. Why? Because the statistics tell us that a black 25-year-old, there's much more risk of that person acting in an unlawful way. You take a look at, crime statistics and ask the question with respect to homicide, with respect to robbery, with respect to is there a difference between the white 25-year-old and the black? With respect to certain crimes, the answer is, in certain places, the answer is yes, there's a difference. And there is a greater risk that the black 25-year-old has engaged in various forms of criminality. Understand that? Okay. Under those circumstances, what do I say? Should the police officer therefore be allowed to take action vis-a-vis the black person as opposed to the white person? My answer is no. I'm fully willing to concede. Let's concede for the point of argument, for the point of discussion, that there is more risk. There might be. But for reasons of constructing sort of society, I feel like we should not empower agents of the state to act towards certain people in a way that's adverse to them. Let me try to break this down. Let's go back to let's talk about what happens when you want to get elected. Now, it wasn't so 9/11 wasn't all that. A while ago, that's what happened. It's very useful with respect to the profile of Muslims. There were some people who said, gee, in the aftermath of 9/11, profiling of Muslims makes sense. It's no hard feelings, but the 11 people who were all these claims were all Muslims. Now, there is a rationality. You could just simply say it's not treacherous, it's not animus, it's not invidious. It's just, the facts take us this way. But the facts never take us this way. There are facts And then there is how you respond to it. Now, you could respond by saying, well, we perceive Muslims to be more likely to, do bad things on airline. You could respond in that way. On the other hand, you could say, no, we want a society in which people do not have to grapple with prejudice on the basis of their religion, on the basis of their race. And to deal with that, we are going to demand the command agents of history act towards people in the same way. So what that means that everybody getting in the airplane, before they get on the airplane, has to open up their luggage and it slows things down. But everybody has to. I would prefer that over a system in which we focus the people who are. And one of the reasons, and I'm going to bring this back to the racial thing, one of the reasons why I'm in this system is because if we all have to open up for what that means is we're all paying a tax for more security. And we're all likely to ask ourselves, do we want to pay this tax? Whereas if you focus on Muslims, you voice that on. Same in the black person, white person, do we want to impose a racial tax on the black 25-year-old? Some people would say yes. I say that's a mistake. Black people are stupid. They know that they're paying this tax. It is a violation of the rules that we ought to work together to govern our society. I say spread the cost, make the police deal with everybody the same, and don't allow a situation to develop in which a group of people can accurately say, we are paying more costs than these other people.
So it's a better wording profile. While you may have costs and security in the short term, in the long term, it's the environment of the principles that all men are created equal. So it has a much bigger benefit.
Yes.
It represents the fairness that is the core of the idea of this country. Yes. Let me ask a big philosophical question. Why do you think there is racism?
Now you ask me a question which I throw up my hands and I don't know.
Why is there tribalism? Are humans always finding this way to divide ourselves? And, how bad of a problem is that?
It's a huge problem. I don't, I don't, I'm not going to pretend that I know enough to grapple and satisfy. Really very broad knowledge base in which they can make comparisons. And the world's a big place. From the little bit I know about the world, and I read and I'm a very privileged character. I live in a university, so I'm reading constantly, listening constantly. What I gather, the problem of divided societies is a problem that is global. There's, and it seems as though human ingenuity is such that humans will find some to divide. You know, it might be texture of hair, it might be complexion of skin,
Political ideology.
beautiful ideology, it's texture, it's a texture, skin. It's the same. It'll then be, well, you know, you wear these, you speak in this form. You believe this, whereas I believe that. I mean, it seems like the human ingenuity is such they would humans will find some way of distinguishing themselves, and then they seem to want to embellish the distinction. It's not just a distinction. It's not just you believe this or I believe this. Okay, that makes people interesting. You know, let's talk about what you believe, what I believe. No, it's usually associated with you believe this, I believe this. Of course, my belief is superior to your belief, and I want to put you down. Now we're
The interesting thing is, as far as stuff outside, from an alien perspective, I think America is one of the greatest countries in civilization. And I think that the line to black racial struggle is the thing that in part there's something about division and the way you alleviate the division through the struggle for human rights that makes for great nations. So it's interesting that the division is almost the fuel of the greatness for our discovery of what it is to be human, what it is to be just, what justice means. And it's interesting that it seems like there's this struggle that struggle itself is our search. Man's search for meaning, justice, and freedom.
I think there's something to that as you were speaking. That was a great person, most of the great Frederick Douglass. So when here you have a person who, in my view, is one of the great people in the history of the world. And, you know, one of the things that ironically enabled him to become one of the great people of the world. He was born into slavery. His overcoming was the very thing that, in a sense, made him this larger than life figure. I think there's something to it. I will say this because a minute ago you mentioned optimism. I'd say in the last few years, my feeling about the United States has changed. It's changed in a somber way. For most of my life, I've been in the optimistic camp with respect to my view of the American rights rights. The optimistic, that's the camp that we use. We shall overcome. That's Martin Luther King's camp. Martin Luther King, hours before he's killed. I've been to the mountain. With you, glimpse the promise. Optimism. Frederick Douglass would be in that tradition. There would be other people. Wonderful, good
Too sorry to interrupt, but you have some speech, but not to that.
or the pessimistic camp. The pessimistic camp is more interesting. Ideologically, it's more interesting camp because of the pessimistic camp. You have, if I was going to list some of my pessimists, pessimist number one, Thomas Jefferson. Thomas Jefferson, the author, principal author of Declaration of Independence, he was also the author of Notes on the State of Virginia. He said in Notes on the State of Virginia, basically, we shall not overcome. He talked and said, the black people will always know that their forebears were enslaved. And they will always be resistant that, always be aggrieved by that. Jefferson did not think that he would ever have the United States in 1900. He was very critical of slavery, and he had slaves and sold slaves. He was terrible that way. But he did understand that slavery was horrible. But he did not want he did not want to free the slaves for a variety of reasons. But then one reason was because he thought that it would be impossible to have a society in which blacks and whites were equal neighbors. He was thoroughly pessimistic. Another pessimist, Alexis Sikorsky, thoroughly pessimistic. Who were some of the other pessimists? Abraham Lincoln, pessimistic. That's why he was so interested in colonization. He like slavery, but blacks and whites are not going to be able to share the United States. Maybe the best thing to do is just the blacks ship blacks to themselves.
Can you elaborate on that? Like, I think people would be surprised to hear that you would put everyone looking at the
Oh, Abraham Lincoln was thoroughly pessimistic. He was anti-slavery, but he did not believe that blacks and whites would be able to share the United States together. And he was always very interested in his civilization. Even during the Civil War, he was interested in, maybe all black people be interested in maybe going to Panama. Would they be interested in going someplace else? Because Lincoln was aware of how racist white people were with himself. And he did not think that black people and white people would be able to share the United States. Now, look at the black nationalist Marcus Garvey. My father was a thoroughgoing pessimist. His view was that the United States was born as a white man's country. It's going to remain a white man's country. And that's the way it is. He was thoroughly pessimistic.
You mentioned just a brief aside with your dad that he moved to South Carolina to the University of D.C. And you asked him why. His response to you was because either a white man was going to kill me or I was going to kill a white man.
Yes.
So he saw race as an important line that divided people in the United States.
He certainly did, and he crossed the line. My father did not. My father had passed away before the election, before Obama was elected. I would love to talk with him.
You wrote a book about your life.
I did. And I never worried with my father. My father would have been delighted. I do think, though, that my father said, I'm happy that Rothschild is elected. Hold on to your seats. Let's see how the white people respond. I think that my father, in 2016,
You would have said, I told you.
yes. I think that in 2016, my father would have said, all of you people who were talking about, I don't know what happened to America, how could this have happened, no. I think my father would have said, this is America, and in America, what has happened is that America has been put on kilter by black families and deranged against white people, and now this is coming on to the side. My father would have absolutely said in 2016, holes.
In 2016, as you're saying, is the reason you have at least outside of the campus?
Yeah, I want to be careful here. I don't want to.
Give up on the
I don't want to. I don't. You're right. I don't want to give up on my place. I don't. I have been. My optimism has definitely been dampened. It's definitely been tested. I am certainly no. I am not. I am not as triumphant as I once was. I am not as indignant as I once was in my criticism of. But at this moment, as we speak, am I more in the optimist camp than I'm in the pessimist camp? Yeah, I'm still probably in the optimist camp. My optimism has been dampened. But as I speak, I have to say the following things. And I say the following things to my father, again, whom I revere greatly. If my father was sitting here with us, I would say, listen, Father, it's absolutely true that the country is more racist than I had hoped. That is true. It's also true, Bob, that the Vice President of the United States, as we speak, is a black man. As we speak, it's true that the Secretary of Defense, now, Secretary of Defense is the head of the Pentagon. The Secretary of Defense knows where the button is, okay? This is not this is not a small, out of the way thing. This is the Secretary of Defense is a black man. There are a slew of black generals. There have been black secretaries of state. There are black people who are the heads of police forces, mayors. There are black people who are the heads of some organizations. There are, the president-elect of Harvard University is a black woman. And we could go on and on and on. No, this is not, and we're not, when I was growing up, when I was, let's say, 10 years old, we got a magazine, Ebony magazine, you could turn to the middle of Ebony, and they would have black first. The first black person, who is the first black person to do this. You could read Ebony, and I could tell you all of those, I knew their names. Now, I read stuff, the leading cadet, the chief cadet at the United States Navy. I'm reading this picture. Black women. Back in the day, I would have now, has the United States changed? Yes. Is there racism? Yes. Is it, a substantial force in American life? Regrettably, tragically, yes. Has the United States changed? Yes. And again, if we want to do international, the United States is not the only country that is a country that is wrestled with deep division. You think about India, think about the United Kingdom, think about practically any large nations. They've all grappled with divisions. If one asks about the United States and the race question, one puts on the table that in 1865, when I talk to students, I say 1865, they think, isn't that the dinosaur? No, it wasn't a dinosaur. 1865, frankly, is not great mass of black people in 1865 were illiterate. Now, I mean, it's an absolutely extraordinary story. And so, one of the difficulties I had at this moment is wrapping my head around two stories that are in such tension. One is the continuing story of racism, awful stories. But the other story is a story that is encapsulated in the title of a great book of history by John Hope Franklin, From Slavery to Freedom. And those are two stories in American life. And it takes an awful lot to put your mind around those stories. I'm trying to.
Well, as an optimist, I think you put more value to the overcoming side of the story. The overcoming of hardship, overcoming of slavery, discrimination. Well, since you mentioned literacy from, 150 years ago, let me ask you about affirmative action. You wrote a book titled Field Discrimination Based on Affirmative Action in Law. First, what is affirmative action? And maybe we could talk about your views on it today.
Well, affirmative action refers to racial affirmative action. There's various sorts of affirmative action. You can have affirmative action for veterans. You can have affirmative action for in-state residents. If suppose you have a school, the University of blah blah blah, and we want to reach we're going to reach out a hand to boost health of people who live within the state. We're going to boost for veterans. We're going to boost for women. We're going to have a boost for men. Well, we're the type of affirmative action that gets most attention is red. So there's some sorts of affirmative action. If you say affirmative action, the type of affirmative action that immediately people think racial.
Seems like we're before this American experiment took part in every part of this
Bingo. Culture. Bingo. Why is it that there's various ways in which institutions reach out to help various sectors of our population. Why is it that this is the one that generates all of the pulling out hair and national appeal? You can put that inside. But racial affirmative action refers to efforts in which institutions reach out to provide assistance to racial minorities. Now, they've been reaching out as it happened in a like form of affirmative action might be reaching out in terms of recruiting, making a special effort to make sure that young people with, say, racial minority flavor groups know about their culture. That's recruiting. On the other hand, racial affirmative action might take more, might take a stronger form. It might take a form of saying, okay, we have a competition. And we think that there will be too few racial minority kids who do well enough in this competition to be admitted to our school. So what we're going to do is we're going to, in various ways, give a boost to the minority kids. It comes down to you have two kids, they both, 99 on the test. There's one place left, one spot left, two kids. unless we make a special effort to bring the black kids on campus. Our student body will be overwhelmingly monoracial. They just have, white kids, a few Asian kids, a few Latino kids, no black kids here. I don't know, it would be lacking in an important aspect of American life. Some sort of so-called diversity. So anyway, there are various theories. Some are grounded, like I said, in comparative justice. Some might be grounded in distributive justice. So, for instance, when people say nowadays, we want a cabinet, we want a team, we want a student body that looks like America. That might be a distributive justice theory for why you want to must be reach out and give a boost to certain groups. They won't be here. And we want a campus that looks like America. And we won't have a campus that looks like America unless we give a special boost to the Latino community, unless we give a special boost to black communities. So, reparative justice, distributive justice, or third, diversity. We just want to have an interesting student body, and to have an interesting student body, we want kids from a wide array of places. That'll make for a better campus. Those are three justifications, all of which, however, are justifications for, in a competition, giving a special boost to some people based on their race.
What's your sense? Can you make the case for communication?
Yeah, I can make the case for it. I can make the case against. The case for, I won't spend much time on this. There are three main justifications. Your audience should know that one, the justification that actually led to it is a justification that you don't hear about in the courts, because the courts have said that justification is insufficient. So the real justification behind affirmative action was, in the late 1960s, the aftermath of the Civil Rights Revolution, aftermath of the Civil Rights Movement. There was a feeling that, well, okay, fine, we're not discriminating against black people anymore, but black people have been disadvantaged by the discrimination that has been put upon them. And this discrimination that was put upon them has disabled them. And so they go into competitions, and it's unfair. Yeah, they score less well on the standardized test, but, surprise, surprise, what the heck? They went to schools in which they got the leavings of the white folks. The white folks gave the black folks the old textbooks. That's what the black kids read. The white kids read the new textbooks. On and on and on. So, reparative justice. We're going to try to repair the scars left by past racial injustice. And so it's sort of an effort to overcome the vestiges of past misdeeds. That was one justification for affirmative action. And frankly, I think that's the justification that has always been the dominant justification, whether people owned up to it. That's what justification is. The distributed justice justification is there. I mean, people, we want an integrated America. We want an America that looks like America. In that justification, legitimacy is sometimes mentioned. So, for instance, people will say things like, well, if we're in the armed forces, we have armed forces in which the people on the ground we have a lot of people on the ground, people of color, but none of the people calling the shots, none of the generals, none of the major colonels are people of color. No, they stand for. So for purpose of legitimation, we need to, for purposes of buying, we need to have a situation in which people get the sense that even if they're sort of low down, they're still part of the story, they're part of the team. So that's part of the sort of, distributive justice notion.
Do you think there's power to that? I mean, do you think there's value, there's correctness to that kind of idea?
I think there's some.
Because for the application process for different universities, I think there's probably a drive and a justification for it. Yeah. Well, affirmative action, I don't know where we put DEI efforts because they overlap, but they're not perfectly
The reason that the schools are there, education right, there's a case you'll know about it, it will be announced sometime in the next month. There's a case in the Supreme Court of the United States in which the affirmative action program at Harvard and the affirmative action program at the University of North Carolina are being challenged. Most people think, including me, the Supreme Court of the United States is going to limit, if not totally seek to abolish. This is a very burning issue. As things currently stand, my university and other universities embrace affirmative action on the third ground, the diversity. They say is we need affirmative action because affirmative action is good for pedagogical purposes. Now, frankly, do I think there's something to that? I think there's a little something to that with respect to some subjects. I don't think that's what's really going on. I mean, if that's what's really going on, why don't we have more foreign students? Why is there a greater effort to bring in more? Why isn't there a greater effort to bring in more, I don't know, religious fundamentalists? Why isn't there a greater effort to bring in, you could just name various groups that are, you hardly ever see them like that.
So you don't think this kind of effort of driving towards diversity is rigorous?
I think it's often pretextual. I think, frankly, the real reason has to do with the belief, and I think it's a good belief. I associate myself with the belief. It's just that because of the new rules, we don't say that loud. But it's still the case that a lot of institutions want to help American society overcome its racial past. That's the real animating thing about, we'll have better classroom discussions and, some discussions. I mean, with some subjects, I'm an ignoramus when it comes to physics. My sense of it is, however, that if you're talking about physics, and frankly, it doesn't much matter in terms of math of physics. What the demographics of that classroom. Well, you know physics in your go.
The interesting thing I've noticed in this podcast is one way it does matter. It's really lonely when you do a thing and you don't see somebody that looks like you doing that thing. And it's such a seemingly stupid thing. Why does it matter if there's another person that looks like you in this very shallow sense? But it seems to matter. When I talk to, for example, women on this podcast, a lot of women reach out and inspire. That's interesting, right? Like, I think we're still human, and we see people that look like us, and this kind of narrow, shallow definition of diversity still matters.
Okay, well, I think you made a good point, and maybe so. So let's go back to the physics. Let's suppose that under one scenario, there's a classroom, and a kid sticks his head in, a black kid sticks his head in the classroom, and doesn't see anybody else black there, and has to make a quick decision. Nah, versus they stick their head in the classroom, they see a smattering of other black people in the And then they try it, and it turns out they were, Albert Einstein. So, to that extent, I can see, under that scenario, maybe it doesn't. So, still, those are the three needed justifications. You ask me, where do I think this might be further back? Oh, no. Before we get to that, are there criticisms? The answer is yes. There are criticisms of affirmative action. Is a policy like, any policy is going to have some downsides. And affirmative action is okay. Does affirmative action have some downsides? Yes, it does have some downsides. What are they? Well, let me mention. One, stigma. So if you have an institution that says that it reaches out to give a boost to certain people on a racial basis, they're going to be people who observe and who are going to be thinking to themselves, if somebody says here and they were given a special boost, doesn't that mean that they were not as proficient as the other people who were here and who did not have that boost? So if they are not as proficient, that means that they might not be as good. They might not be as up to snuff. Is that part of our affirmative action? Yes, it's part of our affirmative action. Yes. I'm a professor at Harvard Law School. One of the subjects I teach is contracts. Actually, that's probably the subject I most enjoy teaching. I think I most enjoy writing about racial conflict and the legal system. But as far as teaching, I most enjoy teaching contracts. And on that very first day, when 80 students come, especially when the first few students are nervous, I show them. I'm quite sure that there's some students who are thinking, okay, well, is this guy as good as my other teachers? Because, I know that, institutions like Harvard have made a special effort to bring in people like this guy, Kennedy. Is he as good? Well, I'm sorry, if you have an affirmative action regime, people are going to think that. And are they crazy to think that? No, they're not crazy to think that. No, that's a perfectly logical thing for somebody to think. Does it have an effect on you as a teacher? Yeah, actually, it does have an effect. Sure. I'm aware that some people are saying it doesn't. I'm not. It doesn't. Make me shake in my boots. Am I aware of it? Does it have an effect? Yeah, it probably does have an effect. It probably makes me. It probably makes me redouble my efforts because I don't want anybody to think justifiably that I'm less able than my colleagues. So, it's funny. When I was growing up, my father used to tell me, he was telling me that because when he was in an earlier time, high-five movies, it was, if it's even, and the choice to be made, the white person was going to now, under affirmative action, there's going to switch around. Oftentimes, it's the black person who gets the ballot, but I'm still in a situation where it's the work hard. To avoid the stigmatization that is imposed by affirmative action. I'll tell you another way in which it comes up in the students. This is my second year law school. Professor Bill, wonderful, wonderful. Doris, the very first person who called on was a black student. I remember this. Yes, called a black student, a black woman student. And I remember when he called on, I remember just felt, I felt as if the room got so really felt as if the room got louder. And I knew there was a real tenseness. You call on me because it's going on somebody else. I felt different. I felt as if I was I felt as if I was some kind of head issue. I felt as if my place, I felt as if my status, some small degree at issue in the positive direction for that. Just at issue. At issue. So, and then all this is happening really quick. He calls it a student. This is happening like in seconds. And she responded, really strong. He asked her a question. She answered the question. She answered the question beautifully, very strong, comprehensive, wonderful response. But you might say, okay, well, next, after class, I went up to her. I couldn't. Wait, thank you. Why? Because the law school, the Berkeley White Institution, Yale Law School, and I felt some of the, again, affirmative action. I felt some of the fruit of this affirmative action. So it was almost like, thank you for showing that we belong. Yes. Perfect. Yes. By the way, I wasn't the only, I wasn't the only idiosyncratic. I wasn't black people in that class, but all of them. We laughed about it. We laughed about it. So there's the stigma issue. And some people have made a lot of it. Some people have made a lot of the issue. My attitude towards the stigma issue, it's there. It's, again, it's part of, it's part of the situation, but I think the benefits out there. What are some others? Resentment. Resentment is a science, and that's okay. So in the fancy schools, and by the way, remember what action. Most colleges and universities in the United States, there is no affirmative action issues because they're not selective. They'll take anybody. You can pay. Come on in. It's only a fairly small set of schools that are selective. But of course, those are the most elite schools. Those are schools that people most give to. Right now, all this fighting with the students. Now, there's how many millions of people are there in there who have applied for various places? They didn't get in. What did they say? White person applied to Harvard, applied to Yale, applied to Columbia, applied to Georgia, applied to Illinois. Didn't get it. What did they say? Oh my God, yeah, had resentful. Should they be resentful? No, they shouldn't be resentful, but they are resentful because they have consequence. Yeah, that's a consequence. As a consequence of how they act towards other people, as a consequence of who? As a consequence. I think that's. Are there other things? Yeah, look, I certain sort of denialism that has accompanied the affirmative actions today. So, because, black people like myself want to avoid the stereotypes, for some people, DSM have said, oh, actually, there is no difference between, the beneficiaries of affirmative action and the other. There is no difference. If the affirmative action kids got, let's say, a 500, and the other kids got a 750, that doesn't make a difference. That's just BS. They're only using the kid, 550 kid didn't get 750 because the test has all sorts of bias, cultural bias. Well, sorry. Yes, there is a difference. 200 countries. This difference matters. Yes, it does matter. And by the way, if you don't know what a yacht is, you can know what a yacht is without owning it. Okay? And there's this denialism that I think has really seeped into not just dating, I think into various conversations.
That can have this look effective.
Yes. See it various ways. So, this attack on tests. It's not like I'm holding the, some tests are like new tests. I think we should be skeptical of study. But there are a lot of tests that, they tell us what. And there's some people who are really, dead set against testing, dead set against anything that might show gap. Well, I think, by the way, are there gaps? Yeah, there are gaps. And we need to do with hypotheses of those gaps and do things to make it so that if there's a gap that is beneficial, no shame. Let's, let's learn so that I catch up. But I'm I think sometimes this is afraid of acknowledging yeah. Of course, there's colleagues who there's interesting witness ways to challenge ways. On the flip side of that, we're obsessing with narrative. So congrats, you might know he's a wonderful colleague and he's a wonderful friend. For a long time, with these very important arguments about meritocracy. I disagreed with some of the things that I do.
So you lean towards
I think that yes, I think that the value of meritocracy is extremely that the movement from there's like the movement status, the idea of I don't care from your father or his mother, because I don't care from your partner. I don't care what your family. I don't care what your story is. Show me what you can do. And then somebody sits down, okay, I'll show you what you can do. Right? They show it. I think there's a lot to that. And, the impulse to sentiments behind that, I resonate with. There's a lot there. But I want to do is, I want to get rid of those features in society that deprive of what you need to develop yourself. Sometimes there's psychological. Sometimes it's you're not around people who've done things that you can do. Rid of that. The idea of people. The idea, by the way, distinguish. You know, this is excellent. The people who are excellent, they're here. And there are people who are good. No, they're not excellent. I'm not gonna, close my eyes at that distinction.
And highlight a distinction and yet at the same time maintain a sense that their basic worth as a human being is equal.
Yeah. So, there's a Run DMC, whatever rap roots, we're all written down in the same list. We're all written down in the same list. Yes, so I want to recognize our fundamental humanity. I don't think I think that one can recognize our fundamental humanity and one can also recognize, as I'm concerned, that we all collectively should make sure that we do all that we can to prevent people from sinking below a certain level and being in misery. All for that. But I want to be careful about some of the attacks that I hear in meritocracy. So some of the people, including, again, I have all the respect in the world for Michael Sandel. He talks about the arrogance of the room. Okay, I'm going to be, I don't want the winners to be arrogant. That's right. What has you didn't have control over the circumstances that you were born to. You were lucky that you were born healthy and you were born with a well-working mind. You didn't have to go through the bad times. Some people don't have that. So, don't be, Mr. Big Stuff. Okay? Well, I'm sure you get that arrogant. I'm entitled. As if I taught myself how to read. There's people who did all sorts of things for you don't even know. Okay, so, I want to get rid of the arrogance, have decent humility. I'm all for that. At the same time, I want to be careful about the problem of hate. I want to be careful about the problem of resentment. I want to be careful about, so let's not give a trophy to the person who wins the race, because to give a trophy to the person who wins the race will make the person who they defeated feel bad. No, I don't want that. I want to give a trophy to the person who wins the race because I think it's a good to have. So bad.
Yeah, it's a kind of celebration of this whole human project that we're celebrating. You mentioned your father several times. So let me just think about it. What have you learned from? What have you learned about life?
I've been just such. I feel like I've just lived an absolutely charmed life, and I've lived work that is what I love to do. I would pay to do what I am paid to do.
Yeah.
And it's great. And I've been fortunate in so many ways. And one way in which I've been fortunate is my faith. My parents, Rachel Span Kennedy, Henry Harrison, my mother, there in Columbus, South Carolina. My father from New Orleans, Louisiana. They were refugees from Jim Crow South. They were people who put their all into their children. I have a older brother, I have a younger sister. All three of us know beyond innocence that we were loved really well. And they were great people. My father, very interesting man, very independent minded. He was perfectly willing to go his own way. And I learned much from him. Including, I learned things from him even when I had to make. So, for instance, again, to go back to his pessimism, yeah, he was pessimistic, thoroughly pessimistic. But he was also willing to change in certain ways. That both my parents. I mean, one of the most important things that happened to my parents was that, let's say, when I was, let's say, teenager, I was born in 1964. In 1964, I think my parents would have taken the position that you definitely never, under these circumstances, trust a race. A black person trusts a white person. That person not trust a white person. They're not to be trusted, and it's the highly unusual one who is not prejudiced. Okay? So white people have to be trusted, and by and large, that's their gift. I'd say that 10 years later, that turned the level of something. I think when you say, well, what happened in those 2 years? Well, certainly in my life, one of the things that happened in those 10 years is I was a student in various schools, and I had a series of teachers. I had wonderful black teachers. I've also had wonderful white teachers. And my parents paid attention to who my teachers were and how my teachers treated me. And I think that they were affected by the way in which there were white people who really has on my side were thoroughly on my side. And I think that experience changed my parents. They were skeptical, but they were the possibility of a white person genuinely being a friend of a black person. That became alive to me, and I give them a lot of credit because they were adults. Adult to change. That's a big deal. But my parents teach.
In that transformation that was inspiring to you, was formative to you in terms of joining the Optics camp.
Hugely. And, the school, I mean, I said a moment ago how lucky I've been. Yeah. I teach at Harvard Law School. I attended Balliol College, Oxford. I got my law degree from Yale Law School. I got my undergraduate degree at Princeton University. Those are the pretty good schools. They all were. The most important school that made the most difference in my education was Rothschild. St. Albans School, St. Albans School of Boys. And at St. Albans, I encountered a cadre of teachers. And by the way, at St. Albans, I would say Albans, always teachers. And there was one in particular who, the head of athletics, very important man, very impressive man, Brooks Johnson. Otherwise, white teachers. And these teachers made a huge difference in their life. And, I can call their names. The greatest of them all was a man by the name of Jack. We call him Gentleman Jack. Gentleman Jack. And such he taught me history. He was my next placement history teacher. But John F. McKean, we shared a birthday. John F. McKean is a fabulous great teacher. And we developed a deep lifetime friendship. He's a good Mr. McKean. The day before. He's a white man. I've had other teachers, who, some of whom have become colleagues. Sanford Levinson. Sanford Levinson was a teacher here at Princeton. He's become a colleague of mine. It would be impossible for me to, I can't make some sort of blanket condemnation of white people. And they said, John F. McKean, with Eric Stoners in my life, with my colleague Martha Minnow in my life, my colleague Cass. Impossible.
That speaks of the power of teaching. And you're that.
Well, I've taken that, but I hope this is I would be absolutely overjoyed if there was a student who thought of me the way that I think of Gentleman Jack. So if that's the case, just one. If that's the case, I would do it.
That's like your list. What do you think of Martin Luther King's dream? Do you still share that dream?
I think that Martin Luther King Jr.'s I Have a Dream speech is one of the great speeches, not only in American history, but in the history of the world. There's a tendency now for people to sort of poo-poo that speech. I think, unfortunately, the speech, has been embraced by, advertisers, corporate Americans. It's so, it's occurred so many times that it's sort of has been made to suffer from what some people like to use overexposure.
It's so unfortunate.
It's too bad.
Especially in Hollywood, they did that with Don F. Sinatra recently, which I think is one of the great songs ever. And actor and actresses ruined it by trying to sing along. Yes, kind of cliche Hollywood thing.
It has the people that try to make it feel personally. Back to the American it's the sentiment behind yeah, I was so sick. And anybody wants to see some great oratory, go watch. And Martin Luther King Jr. I mean, he gave several great speeches. His first speech, the first speech was great, as Well, I would associate myself to you there.
So future still have hope for a deep kind of multiracial, a deep unity in the 20th.
I have that hope, and I think it's the sentiments that Martin Luther King Jr. expressed in August 1963 that represents the best of American life. And I think it's do I want to see that come to pass? Yeah, I want to see that come to pass. And we'll work to, push that project along as far as it'll go.
Well, thank you for carrying his spirit of optimism forward, the spirit of love. Thank you for all the amazing work you've done. Thank you for just this conversation. It's a huge honor. This is awesome.
Thank you.
Thank you. Thank you. Thanks for listening to this conversation with Brandon. To support this podcast, please check out our sponsors in the description. Now, may feel some goals and not really darkness cannot drive out darkness. Only light can drive out hate. Cannot drive out hate. Only love can drive out. Thank you for listening. I'll see you next time.
I would run outside and just lay on the ground under the southern Milky Way, and people right up there, and I would just lay there and just kind of let my thoughts and pass through my brain. And this is when I perceive healing. I'm a part of it. I have a volunteer rather than feeling kind of small. Yes, I'm small, but there are many other small things, and lots of small things make one big.
The following conversation an astrophysicist at MIT studying all the stars in the Milky Way galaxy in order to understand the chemical physical conditions of the early universe and how from that our galaxy formed and evolved what it is today, the place we humans call home. This is the Let's Figure podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Anna. Let's go back to the early days. What is the formation of the Milky Way galaxy like? And maybe we already started before that. What is the formation of the universe?
Well, science believes there was a big bang, some big beginning. But what is important for my work, and I think that's what we're going to talk about, is what kind of elements were present at the time. So the Big Bang left the universe behind that was made of just hydrogen and helium and tiny little particles of lithium. And that was pretty much it. And as it turns out, it's actually quite hard to make stars that any structure from that. It's getting hot gas. And so the very first stars that formed prior to the galaxies were very massive stars, big stars, 100 times the mass of the sun. And they were made from just hydrogen and helium. So big stars explode pretty fast. After a few million years or less, it's actually cosmic transports. And in their explosions, they provided good heavier elements to the universe. Because in the first all stars fuse lighter elements like hydrogen and helium into heavier ones. And then that goes all the way up to iron. And all the material is ejected in these massive supernova explosions. And that marked a really, really important transition in the universe. After that first explosion, it was no longer chemically pristine. And that set the stage for everything else that happened, including us even talking today.
What do you mean by pristine? So there's a whole complex soup of elements now.
Yeah, so after the Big Bang, just hydrogen and helium. We don't really need to talk too much about it here because our mouth is too small. And after these first stars formed and exploded, they the heavy elements of carbon, oxygen, magnesium, iron, all of that stuff was already present in the gas clouds. In tiny amounts, in very tiny amounts. But that actually helps, especially the carbon and the oxygen, to make the gas cool. These atoms are more complicated than hydrogen. That's just a proton, and so it has cooling properties. Send out photons outside the gas cloud, so the gas gets cool, and then you have gas that gets colder and colder. You can make smaller forms of gas, like fragment it, clump it, turn it into stars, like the sun. And the cool thing about that is that when you have small stars like the sun, they have a really long lifetime. So those first low mass stars that formed back then are still observable today. That is actually what I do. I try to find these early survivors because they tell us what the gas looked like back then. They have preserved the composition of these early gas clouds, the chemical composition, until today. So I don't need to look very far into the universe to study all of the beginnings. I can just chemically analyze the oldest data, and it's like unpacking everything that happened back then. Yeah.
So to just reiterate, so in very early days, the first few billion years, there's giant stars. It's mostly hydrogen and helium, and they exploded in supernova explosions, and then we made these clumps.
Yeah, so the first stars.
Not for speed clumps.
Yeah, pretty much. So it took a few hundred million years for the first stars to emerge, and then they exploded after a few billion years. And then it's like, I always consider the universe like a nice soup, and then these first supernova explosions kind of provided the salt. It's just a little sprinkle of heavy elements, and that made it really tasty. It just changed it completely. And that changed the physics of the gas. So that meant that these gas clouds that were surrounding the former stars, they could now cool down and form the next generation of stars that now include also mini stars. And as I just mentioned, the small stars have these really long lifetimes. Some like 10 billion years. That means that it's less massive, but even longer. So that gives us a chance to still observe some of the stars that formed back then. So we are testing the conditions, the chemical and physical conditions of the early universe even before the galaxy was formed.
So with the timeline that we're talking about, what is the ancient universe, and what is the earliest time that those salty, delicious soup, clump soups and the heavy elements?
Well, the universe is 13.8 billion years old.
Is it? Okay, thank you.
Well, when I was in high school, the universe was 20 billion years old.
Oh, yeah. So the estimate, do you think that estimate will help with the student? Is it pretty stable?
Mostly converge, yes, because the techniques are very different now, much more precise. The business of precision cosmology by mapping out the cosmic microwave background, that's a marvelous feat. Maybe, the digits will build around a little bit, but that's all right.
Yes, the gravitational waves and all the different sources of data.
Yeah.
Mapping out the detailed picture of the early universe. Yeah.
And so we think the earliest little stars formed maybe half a billion years after the Big Bang, right? Maybe 200 billion years for the first stars to emerge, and then it took some time, so give or take half a billion years. And that was the time when some of the first proto-galaxies formed, early stellar structures, stellar systems, from which the Milky Way eventually formed, right? So it was the Milky Way is probably slightly bigger than, and we know today that galaxies grow hierarchically, which means they each get smaller neighbors. So if you're the bigger one, you have a few friends around, you're just gonna eat them, absorb them, and then you grow bigger. So all these little early stars kind of came into the Milky Way through that kind of process. And that's why we find them in the outer parts of the galaxy today, because they're just kind of left there since.
So the old stuff is on the outskirts of the galaxy, and the new stuff is in closer to the Earth. Is it?
Well, yeah.
So that's where you would look for. So maybe just to step back, what is a galaxy? What is it called? A galaxy?
I love that question. So the galaxy is a huge assembly of stars. The Milky Way contains something like 200 to 400 billion stars, and most of the material in the stars are in the disk. And when we look at the night sky, what we see as the Milky Way band on the sky, that is actually the next inner spiral arm, because we actually look at the spiral disk galaxy, that the Milky Way is a spiral disk galaxy, and we look at actually, it depends a little bit on the northern hemisphere. We're looking out of the galaxy. So we see the next outer spiral arm. And as you can imagine, there's only dark space behind that. So we don't see it all that nice in the sky. But if you travel to the southern hemisphere, to South America, you see the Milky Way so different on the sky because that's the next inner spiral arm. Actually, by the galactic center. The galactic center is a very big, puffy, region of gas. There's a lot of star formation. The galactic party is happening there, so it's very bright. It makes for this very beautiful Milky Way in the night sky that we see. So actually, if you ever get the chance to experience that, I encourage you to almost like close your eyes while seeing this and imagining that you're sitting in this kind of disk, in this pancake, and you're just kind of looking right into it, and you can really feel that you're in this 2D disk, and then you can imagine it gets the top and bottom, and it's really part of the galaxy. You can really experience that. So we're not just lost in space somewhere, but we're really a part of it. So knowing a little bit about the structure of the Milky Way helps.
Do you feel smaller? Do you feel when you look on that spiral on the inside of the Milky Way and the outside? How are we supposed to feel?
I don't know. I don't feel small necessarily. I feel in awe. I feel a part of it because I can really feel that I'm a part of it. I think for many people they think like, oh, that's just a planet and there's nothing. And that's almost a little bit sad, but that's really not the case, right? Because there's so much more, and I really like to imagine how I'm sitting in this big galactic merry-go-round and looking all around the center, and I can see the center above me, right? And I can almost feel like we're going there. Of course, you can't really feel that, but the sun does circle the galactic center.
But there's a kind of sadness to like looking pictures from an expectation place. All we get is that light. And the whole light. Do you feel like sad that we don't get to travel, or you now we don't get to travel there, and maybe humans we don't get to travel there?
Yeah, I always like to travel to space and see the Earth and how it from up there. But there's certainly that. But I don't know. It's also okay to just be at our vantage point and see it from here.
With the sensors, with the telescope that we have, it's a very possibility.
Yeah.
And there is a kind of wondering to the mystery of it all. What's out there? What interesting things that we can't possibly imagine. There could be all kinds of life forms, bacteria, all this kind of stuff. I think we believe that, we do not think that I think we was just a lot of good organisms just spread out throughout. They built up little things like bacteria techniques. Um, and just to think what kind of worlds there are. Because it probably created living because the conditions, I guess the question I'm wondering to myself when I look out there to the stars, how different are the conditions on the different planets and over the stars?
Will definitely be very different. I mean, the variety out there is huge. We know now that I think about every other star has at least one planet. I already mentioned the number of stars in the galaxy. That's a huge number of planets out there. So who knows what that looks like? All we know is that there is a lot of variety. We don't quite yet understand what drives us, what governs us. to come up with very detailed descriptions. Broadly, we have figured it out. We need gas clouds, we need to cool it, something clumps and fragments, and somehow it makes a star with planets over now.
But the dynamics of the Coldplay process is not going to.
No, and the local conditions are still varied, right? I mean, it's the same with all people look like people, but individually we look very different.
So even the self-diversity of the formation process creates a kind of fun.
Yeah, so we just don't know how this turned out in an individual case. And it's kind of hard to figure it all out and to take a look, certainly with planets, right? The chance to ever actually take a picture of the planet is minuscule because they don't shine. So they really are.
Yeah.
So I think there's a lot of possibility out there. But we have to be a little bit patient.
We're going to come up with a nice way patience becomes less necessary and extending our lifetimes or increasing the speed of space travel. Humans are pretty intelligent. They're pretty reliable. Who knows what? I hope. I'm not optimistic yet. But maybe it's just the week of what a galaxy is. What you know about our understanding of black holes information is like an important thing to understand the information of a galaxy. Like, so all the other people about the stars is going on how cool is that to understand.
That's what makes astronomy really hard, but also really interesting, right? You know, there's like another Republic of Science. I want to come back to the idea of the curve galaxy, which actually matches what we relates to the black hole formation. So most large galaxies, pretty much all large galaxies, have a supermassive black hole in the center. And we don't really know where they come from. We know that they're there, but how to get there. So we go back to the early universe, right? We had a galaxy that just sort of, I don't know, had some small number of stars, was the first gravitationally bound structure that was held together by dark matter. Dark matter actually kind of the structure up, first before the luminous matter could, because that's what dark matter kind of does. And it started to hold gas and stars sort of together in this first very shallow, what we call potential wells, so these gravitationally bound systems. And then we could move from absorbing neighboring smaller systems. And somewhere in that process, there must have been a seed for one of these supermassive black holes. And I'm not actually sure that it's clear right now, what was there first, the supermassive black hole or the galaxy. So lots of people are trying to study them. And of course, the black hole doesn't as massive like that because it's these days. But that's a big area of research. And the new James Webb JWST, the telescope, the red telescope in space, is working on, many people are working on that to figure out exactly what happened. And some surprising results that we really don't understand it now. So.
To solve the chicken or the egg problem of do you need a supermassive black hole to form a galaxy, or does the galaxy naturally create this supermassive black hole?
Yeah. I mean, I think to some degree we can answer that because there are lots of little dwarf galaxies out there, and some of them remain surrounded by many dozens of small dwarf galaxies, and studied a bunch of them. That to the extent that we can tell, they do not contain black holes. So they're certainly gravitationally bound structures, so be like common galaxies or dwarf galaxies or fierce galaxies, they were definitely there. But there must have been bigger things, like the proto Milky Way, where something was different, right? But with a more massive, so that they would gravitationally attract these smaller systems and to integrate them. So we'll have to see.
How do we look into that, into the dynamics of the formation and the evolution of the proto galaxies? Is it possible? Do they shine? I mean, what are the set of data that we could possibly look at? So we got gravitational lens, which is really insane. Detectors.
Yeah.
There's light. What else do we have?
So that would fall into the category of observational cosmology, and then the JWST is the prime telescope right now, so, and it promises big steps forward. This is in early days because it's only been online like a year or so. But that collects the infrared light from the farthest, like literally further galaxies, earliest galaxies. That light has traveled some 14 billion years to us, and they're observing these faint red blobs. And folks are trying to again study the onset of these early supermassive black holes, how they shape galaxies. So they're seeing that they were there, surrounded by already bigger galaxies. Ideally, I'd like for my colleagues to push a little bit further, hopefully that will eventually happen.
In terms of looking for older.
Yeah, more sort of primitive in terms of the structure. But of course, as you can imagine, if you make your system smaller and smaller, it becomes dimmer, and it's further and further away. So we're reaching the end of the line from a technical perspective pretty quickly.
Whether it's dimmer than older.
Um, yes, in a sense, because it all started really small.
Because it's more smaller.
In that phase of the universe, it does.
Just to take a small tangent about black holes, and because you do quite a bit of observational cosmology and maybe experimental astrophysics. What's the difference to you between theoretical physics and experimental? So there's a lot of really interesting equations about paradoxes on black holes, all this kind of stuff, about black holes destroying information. Do those words make sense to you? Especially when you step away from think about chemistry.
Well, at first glance, it isn't actually much crosstalk. Personally, I mostly observe stars, so I don't usually actually think too much of black holes.
The stars is a fundamental to chemical physics.
That's right. The physics is kind of different. It's not extreme. I mean, nuclear and nuclear fusion sort of perhaps extreme tunnel. But there are some interesting things before. But it's just a different flavor. I don't do these kinds of calculations myself either. I very much like to talk with my theory colleagues about these things because I find there's always an interesting intersection. Often it's just, I've written out a number of papers with colleagues who do like simulations about galaxies, and so they're not quite as far removed as, let's say, the black hole kind of paper folks. But even in those cases, we had the same interest in the same topics, but it was almost like we're speaking two different languages. And we weren't even that far removed, both astronomers, and it was really interesting just to take the time and really try to talk to each other. And it's amazing how hard it is. Even among scientists, we already have trouble talking to each other. Imagine how we used to talk to non-scientists and other people to try we're all interested in the same things as humans at the end of the day, right? Like everyone has sort of a different angle about it, and different questions, and way of formulating things. And sometimes it really takes a while to converge and to get to the common ground. But if you take the time, it's so interesting to participate in this process. And it feels so good in the end. We tackled this together, right? We overcame our differences, not so much in opinion, but just in expressing ourselves about this and how we go about solving a problem. And these were some of my most successful papers, and I certainly enjoyed them.
It could also need to be discovered. I think they put it really well in saying that we're all studying the same kind of mysteries and problems. And I see this in the space of artificial intelligence. Creating maybe it seems very far away. Artificial intelligence and neuroscience. You would think that they're studying very different things. But one is trying to engineer intelligence, and so doing try to understand intelligence. And the other is trying to understand intelligence and cognition, human mind, and extremely different set of data, different set of backgrounds, and the researchers that do that kind of work. And probably the same is true in observational cosmology simulation. So it's like a fundamentally different approach to understanding the universe. We use for simulation, we use things I know to create a bunch of parameters and create some, just play with the universe, play God, create a bunch of universes and see in a way that matches experimental data. It's a fun, thick thing Sims, but at the cosmic level. So, but the problem is that technology used there is a little bit. Maybe you're allowed to pick the rules a little bit more. It's like, the Drake first. You don't really kind of come up with a bunch of values there and just see how it evolves and through that kind of intuit the different possibilities, the dynamics of the evolution of the galaxy. So, yeah, it was cool to play. I mean, it seems like I understand so little about our cosmos. So it's cool.
Yeah, it's like a big sandbox. Everyone has their own requirements and routines, but to get that thing.
But in that sandbox does have super powerful, super expensive telescopes. But there's also all the children are fighting for the resources to make sure they get the astronaut questions. Isn't that big cool too? Well, can we just step back on the big field of stellar archaeology? What is this process? We just speak to it, and we're speaking to it, but what is this process of archaeology in the cosmos?
Yeah, it's really fascinating. So I mentioned the vessel that that's the star, the Rothschild. And again, for reference, for the next dinner party, the sun's lifetime is 10 billion years. So if you have a star that's 0.6 or 0.8 solar masses, then its lifetime is going to be 15 to 20 billion years. And that's an important range for organization because even if you do that, such as the star form soon after the Big Bang, then it's still observable today. You mentioned old light before. Yeah, that light is like a few thousand years old, but compared to the age of these stars, it's nothing. So to me, that's fine. Come straight from our galaxy, or not far to be started, not far away, there are no galaxies in the outdoor. It probably did not form in the galaxy because, again, hierarchical assembly of a Milky Way. And exactly, they formed in a little other galaxy in the vicinity, and at some point the Milky Way ate that, which is more than the stars, including these little stuff that are on the outskirts of the Milky Way that I used to point my telescope to. So, what can we learn from these stars? Why should we study them? These little stars are really, really efficient with their energy consumption. They are still burning, so the experts just burn hydrogen to helium in their cores, and they have done so for the past 12, 13 billion years, however they are. And they're going to keep doing that for another few billion years. Same as the sun. The sun also just does hydrogen helium burning and will continue that for a while. Which means the outer parts of the star, or pretty much actually most of the star, that gas doesn't talk to the core. So whatever composition that star has, in its outer layers, is exactly the same as the gas composition from which the star formed. Which means it has perfectly preserved that information from way back then all the way to today and going forward. So I'm a stellar archaeologist because I look deep in the dirt, find remnants of past civilizations and whatnot. I dig for the old sky because they have preserved that information from this first billion years in their outer stellar atmosphere, which is what I'm observing with telescopes. So I'm getting the best look at the chemical composition early on that you could possibly wish for.
What kind of age are we talking about here? Are we talking about something that's close to like a 13 billion, 12, 13 billion
Yeah,
age range.
that's what we think. Now, a small caveat here, we cannot accurately date these stars, but we use a trick to say, oh, these stars must have formed as some of the earliest generations of stars, because we need to talk about chemical evolution of the universe and nuclear for a second. So, I already mentioned the pristineness of the universe after the Big Bang, right? Hydrogen and helium, and the first stars formed, they produce a sprinkle of heavy elements after iron. Then the next generation of stars formed. That included again massive stars that they would explore again, but also the little ones that keep on living, right? So, and then the massive ones again explore the supernova, so they provide again another sprinkle of heavy elements. And so over time, all the elements in the periodic table have been built up. There have been other processes, for example, neutron star mergers with other exotic supernovae that have provided elements heavier than iron, all the way up to uranium. Here, early on, we're still trying to figure out those details, but I always say pretty much all the elements were done from like day 3.
So iron is like once you get to iron, you got all
Um, yes and no. I really like the heavier elements, gold, silver, platinum, that kind of stuff.
for personal reasons or for star formation.
Or not.
I mean, like, what's the importance of these heavier metals in the evolution of the stars?
So they're the spice, right? So every supernova gives you elements after iron. That's cool, but at some point it gets a little boring because that always works. But that's the baseline. We need that. And that's really what came out of the first stars, and then all the other supernova explosions have been followed in every generation. And it took about 1,000 generations, give or take, until the sun was made. So the sun formed from a gas cloud that was enriched by roughly 1,000 generations of supernova explosions, and that's why the sun has the chemical composition that it has, including, and some of the planets that were made from that as well.
So the supernova explosions for many generations are creating more and more complex elements.
No, it just goes all the way up to iron, and then it just a little bit more of all of these elements. It's one sprinkle, then another, and just kind of add on top of it. Now, the heavy elements form in a very different way. They're not fusion made. They are made typically through neutron capture processes, but for that we need seed nuclei, ideally iron or carbon or something. So the supernova main elements are a very good seed nuclei for other processes that then create heavy elements. And because they cannot be made everywhere, some of my stars have huge amounts of these heavy elements in them, and they tell us in much more detail something really interesting happened.
Well, wait, I thought the blue universe was not that. So what does that mean? If you're
Yes, important clarification. So the stars that we are doing today, these old ones, they form from the gas. And the question is, what enriched that gas? So it could have been just a first star dumping their elements in that gas all the way up to iron. And we have found some stars that we think are second generation stars. So they form from gas enriched by just one first star. Then we find other old stars that have a much more complicated heavy element signature. And that means, okay, that was probably formed in a gas planet that had a few things going on, such as maybe a first star, maybe another more normal supernova, and maybe some kind of special process like a neutron star merger that made heavy elements. And so they created a local chemical signature from which the next generation star was formed. And that is what we're doing today. So all these old stars basically carry the signature from all these progenitor events. And it's our job then to unravel, okay, events and how many may have occurred in the universe that to exactly that signature that we observe in the Guinness.
Is it possible to figure out what the generations that resulted in these stars?
Well, we think we can sort of say this was the second generation, the third, because the amount of heavy elements in the stuff we observe is so tiny. One normal supernova explosion is actually already basically too much. It gives us too much of it. And the thing is, you can never take away things in the universe. You only add. There's no cosmic vacuum cleanup going around sucking things away. Black holes are probably the closest to it, but because they would have taken the whole stuff.
Yeah.
They would have taken stuff out of the gas. So we have maybe 10 stars or so now where we think they contain so little of these heavy elements that there must be second generation because what else would you have? And again, I want to stress that the elements that we do in these stars are not made by the stars themselves. They're just a reflection of the gas. So we don't we don't put any of the elements in the gas that we stars that we're observing. We can't do it. It's not really
So the stars are this one beautiful.
yeah.
Into the equipment. And so what do you think about the stars? Can you take the process of the galaxy here? It makes your data to the cosmic get to tell it story about these stars.
Yeah, it depends really on what star you compute. And many of the chemical signatures. We actually came up with this element signatures as well as kinetic information on the star that actually gives us clues as to where the stability comes from, because we have all these other stars in the galaxy, but they're not there. That's a small but important distinction so that we think from some other.
You can run back in time to tell you estimate where you came from.
Yeah, so we can't say we came from that or galaxy, but interestingly enough, there are just 2 days ago, a minute of people, 3 women together, seven to and we found that our stars have very, very low allowances in striking and barriers, so no heavy elements. And I had a conversation with a while with these stars recovered to this level of because just that heavy elements give you extra information about essential events. And again, finding something that's really low means it must have occurred, that must have happened even so low or in a very special environment, right? Because we can only ever find something that's incredibly low in abundance, maybe just within contribute to that mix. So you look at the kinematics, how are these stars moving? And they're all ballooned with more how is that possible? Well, it is possible because conforming kinetic connection conforming connection was like an beehive. It just didn't really know what it was. So, and it was observing on its own axis of known things. Some galaxies, some observed galaxies were thrown in on the way, and some came from outbursts after. This could only happen early on when it was left and right and done. We still could find it. But now, 15 billion years later, I'm looking. Yeah, they're still doing it. And we just got like stars that have outstarred the barrier. And then we look at the kinematics and those we call the book, like hundreds of kilometers per second going the wrong way. Huge. Realize that comet really only from somewhere else because it's retrograde motion. That's a clear sign of accretion from something that has come into the galaxy. And because they're so fast collaboration actually emerged in the book. So I really like working with Rabbi, walked through this whole stuff, and I came up with a new concept called class. It was where I wanted to integrate the research process into the classroom because sometimes people find it really hard to email a professor, hey, this is me, I'm working on person and I'm interested in research, but I'm also thinking about something. And I wanted to streamline that and just, just try how it would work, provide a safe compliance with the classroom, with assignment, and do research in a very structured way. And I think that was a lot of fun. One of the to map out an entire research project that could be abstract in 10 worksheets so that they could do it and they could do very structured fashion. Whole thing. But the you each get your own file and you can analyze before. You don't know what the solution is because in research, you might put the solution at the end of the book. You don't know why. Our job is to do it and then to interpret the numbers because our job as scientists is science school. Anyone can touch me. But coming up with a story, when you only have 3 puzzle pieces, how does the puzzle work? That you have to be able to be bold, you need to have some experience, and you need to kind of see the universe in front of you. And that's the beautiful thing.
So this is a story that you discovery you combine with particular signature
Yeah,
elements.
exactly. Yeah. And so the story of that piece is usually I don't say I find all this stuff. When I talk to my research students, I talk to them about finding chemically this cute stuff because that's actually what they measure. The chemical boundary that tells us, okay, let's get the second or third or fifth generation of stocks, right? But those processes are so important for the people. They must be intelligent that came into the galaxy before the galaxy committed. And it's so cool. And it was so wonderful. So this class, it went so well. I had 9 people sign up. That's what I would look for a special class. It was 8 of them. And they were so into it. And I said, okay, let's use this opportunity. We're going to do some extra work this morning. Yeah, I'm going to publish it.
I also like that there is a terminology for the street. You read people say you include street. You that's description of each. So there's this street like evidence of good stars. Which most people say are
Yes, I actually understand.
you know, so there's just
Yeah, what's the street? I don't know who came up with this to know, but even the so maybe decades ago, someone came up with the idea to say, this is the hydrogen X, the Y, and all of it.
The opening starts with the audio have discovered this community 1427, 26, again, and achieved 1843 is what do you say? These facts
My baby stuff.
what do you call the baby stuff?
Well, I'm probably the only one who can, spit out these names without cheating.
Nicknames?
Oh no, that's
It's not allowed? Okay.
well, some colleagues at conferences have just called them Amber stuff, Freeble stuff, because they didn't want to learn the phone number. I get it. But these numbers are actually based on older sets of coordinates for these stars. So the minus in the middle means that they're in the southern hemisphere, so the negative is in the southern hemisphere, and the positive is on the north. And then 14 and 15 means that they were observable in the middle.
Okay, so if we do with the observation, we
Yeah. But we are both absolutely significant career finding actually for people really push the envelope in very different ways. So HE30 27, the first one that you mentioned, that was the second generation star that we found. And usually people say like, oh, the first one is a big one and the rest is nobody cares. But to us, it proves that yes, we can do it. Because one, astronomers live in a sort of way of, there are a lot of serendipitous discoveries, and that's really great. But we need to show that we can do it again. Because then we're onto something. It's not just some kind of weird quirk. And there are a lot of quirks in the universe. But we want to know, is that a real thing? Does that happen regularly? Is there something that we can learn? Is that a piece of the story? And so finding the second one that was even a little bit more extreme than the first one really showed, yes, the search techniques work. We can find the stars. They provide an important part to the story in the sense that if we have more than two stars, and by now we have about 10 or so, what do they tell us about the nature of the very first stars? And what we found, again, working over the years, we run these supernova models, is that, so actually, let me, before I get into this, these two stars had huge amounts of carbon relative to iron. So we usually use iron as a reference element for what we call metallicity. So the overall metal content, the overall amount of heavy elements in it.
So that's why
That's right. So these stars are incredibly iron efficient, which means they must be of the second generation because there was, and interestingly enough, there was this discrepancy in normal supernovae. Until then, we thought we'd get about so much iron, we would distribute that in the gas plug and we would focus on the star and observe it. But the iron ones that we measured was actually much higher. We mentioned you can't take things away. That must be these really massive population 3 to 4 stars. They must have exploded in a different way than we could have thought. They can't output as much iron because they just can't. That's our observation. And so that's when we started to work with several theory groups on supernova units, so what comes out of
From the explosions.
yeah.
With supernova units. And so this one is right here.
Well, we needed to concoct a theoretical supernova that made that. And it's actually surprisingly difficult because you can always add more in your process stuff. So Japanese colleagues came up with the idea of a fainter supernova that just doesn't have enough of this stuff pulse, when it explodes. So somehow there's less iron. But at the same time, then these stars show huge overabundances of carbon, 1,000 times more carbon. So how do you now get 1,000 times more carbon out of these four first supernovas? That was the theoretical challenge. And because we didn't have just one step, but two, that really spurred the field to think about what was the nature of the first stars? How did they explode? What are the implications? Because if they're not as luminous and bright and energetic, that has consequences for these early proto galaxies in which they must have been located in terms of blowing the gas out, adjusting the system. So much higher chance for the earliest system to stay intact. Right? So there's a whole tail of consequences. And this is what I mean with we need to find a story because you one thing like the dominoes, the consequences everywhere, then you have a different universe.
What could possibly be a good explanation for something that yields a lot of carbon and doesn't yield a lot of power?
Well, it's not so much an explanation, but it's finding a mechanism for what happens to supernovae. And the official term was cooked up in order to explain the observation that we have, by the way, found much more of these things. So that whole, and it's called a fallback mechanism. So actually, in supernova, during the supernova explosion, it massive black hole emerges, and so some of the material falls back onto the black hole. So here is a vacuum cleaner dropped into the middle, right?
Temporary one is something.
No, sort of, right? Because if you think of we haven't talked about this yet, but if you know what the stars look like, the massive star looks like on its interior before it explodes, the hydrogen helix on the outskirts, and then the heavier layers of heavy elements all the way up to iron. So you have an iron core in the center. And because you can't get any energy out of iron, when it comes to iron atoms anymore, like that's when supernova explodes. Occurs really. It's actually an implosion first, and then you have a balance of those neutron star things that occurs in the process, and then so get disrupted. Yeah, it's like this giant basketball, and then it goes out.
There's a person.
Yeah, and so in the process, right, if you make your black hole basically big enough, it will suck away some of the iron because that's the closest in terms of the layers. You hold on to it, don't let it escape. And carbon is much further out than it falls out. And so,
That explains why if you have a big loop, every how much higher.
yeah.
So this is explaining the HE 1427 and others like it.
Yes. So there's well established now that the lower the iron bundles of the stars are, the higher the carbon is. And carbon is such an interesting element in that regard. If we come back to the formation of the first lowest stars, right? So we had the hotter gas, just hydrogen and helium, that made the first stars. They were 100 solar masses or so because the gas couldn't cool them. So they were big and heavy. Carbon then, coming from the first stars, probably led to enough cooling in these gas clouds that enabled the formation of the first lowest stars. So think about what happened if that wouldn't have been carbon, or the properties of the carbon atom is different. It would not have cooled the gas in such significant ways. There wouldn't be any longer. You wouldn't be here, right? And we're carbon-based, and so I think carbon is really the most important element in the universe for a variety of reasons, because it just enables this whole evolution that we're not observing it. Everybody's seeing really fascinating.
So combined with the fact that you have information, so all of that are important creating heroes.
Yeah, we need all the elements, but if you don't have stars, like the sun, small stars that can host planets that have long lifetimes and long lifetimes if you want to have a stable planet and get develop. Yes, yes.
This is perhaps a interesting tangent. I would just mention the need to address us carbon cleanup, the remarkable life of science pioneer. Is there something to say about the magic of carbon and the magic
Lily was simply magic. She was a professor at MIT for many decades. I met her a number of times. Her photograph actually down to principle, so maybe it's still one of the every time I step out the elevator in one of the buildings that I see it. She pioneered all sorts of carbon nanowork. So she was a material scientist, very far removed from what I do on a daily basis. But yes, carbon has amazing properties when you study it, and that's indeed another aspect of why carbon is so fascinating. Not just in the cosmos, but also for us, making us, creating us, and we can use it. It's wonderful.
you sometimes think about this chemical evolution in this big philosophical way, that we're the result of that chemical evolution. We're made of this stuff. We're made of carbon. Yeah, and it came.
Alright.
It's almost like a cliche statement, but it's also a materials, chemical, physics statement. Where it came from hydrogen and helium. And then somehow this formation created this interesting complexity of soup that made us. What are we supposed to be looking at? Like, what? Did we just get really lucky? Why did we need all this good stuff?
Yeah, good question.
I don't think it's a question that you answer. Keep yourself in.
Yeah.
But it's just this incredible mystery. So much cool stuff had to happen. So much, hot stuff had to happen to
Well,
create this.
and so much could have gone wrong, and there would have been another outcome. And it's actually amazing how many things kind of fell in place. I mean, maybe that's also so deterministic in some ways, because that was the path. Maybe we would have ended up being partners, I don't know. But it's certainly wonderful science wise to help contribute and grab our cosmic history. I always say the biological evolution of Earth is an absolutely facilitated by chemical evolution of the universe. One doesn't go without the other.
And that evolution seems to be creating more of a complexity. The kind of interesting quantum cool stuff seems to be accelerating and increasing. And it's hard not to see as humans that there's some kind of purpose to like a momentum towards complexity and beauty.
Well, beauty's in the eye of the beholder. But yes, everything gets more complicated.
But there's also a beauty to the chemical pristine.
It is. I love the desert. It's nothingness.
Yeah.
It has so much to planets and appeal.
We came from nothing. So what about HG? What's exciting? A red giant star.
Yes.
That's another one.
Yeah.
13.2 billion years.
Yeah. So that one isn't quite as iron efficient as the other one. So probably not a second generation star, but at least the second, third, fourth, fifth. So we can't really pin it down. But it's also super cool. What is important is that that star has a very different chemical composition in a sense that yes, we have all the elements up to iron there. They have sort of normal ratios, which means kind of the same as other old stars and not too different from the sun, or at least different in quantifiable ways. But it huge overload of very heavy elements. And what was so nice about that stuff, particularly, was that I could measure the thorium and the uranium abundance, and that again, that was the second of its kind. Um, the uranium abundance was could be more well determined, so we had a better grasp of that. Now, why are thorium and uranium interesting? They are radioactive elements. They decay. Thorium has a half-life of 14 billion years, I believe, and uranium is 4.7, which, to folks on us on Earth is a really long time, but those kind of timelines are really good when you want to explore the Earth universe. So there are two questions now that kind of come to mind. Where do these elements come from? And what do they tell us, right? And these, as we know, the heavy elements are made in a specific process. It's a neutron capture process, usually referred to as the OR process, or rapid neutron capture process. We talked about seed nuclei before, right? So we still don't exactly know where this process can occur. So you have, let's say, a lone iron atom somewhere, and it is in an environment where you have a strong neutron flux, which means there must be lots of neutrons around, and we'll talk about the site of life where that might be the case. So you have this iron atom that you bombard with neutrons, and you do it incredibly fast. Now, what happens in the process? That iron atom, you collect most of neutrons, it becomes really big and unstable. So it's a heavy neutron-rich nucleus that wants to decay because it's not stable, it's way too big. And so, let's say you add only one neutron to it, that would already make it unstable. So it has a characteristic decay time that's called the beta decay time scale. So it will decay to a stable nucleus. So the neutron will convert to a proton, and that makes it stable. If you now bombard lots of neutrons onto that seed nucleus within that time scale of the beta decay, that's how you get to this huge, fat, neutron-rich nucleus that then wants to decay. So the rapid processes of these seed nuclei that get bombarded, you create these really heavy neutron-rich nuclei. They're heavier than uranium. The neutron flux stops, and then all these heavy nuclei they decay. And then make all these stable isotopes that we know, all the way up to thorium.
So that rapid.
Yeah. Correct. And the whole thing is done within 2 seconds. So just after the rapid heating, it's literally the snapping of a hand. It's on it. In my talks, I have this nice simulation that illustrates, the creation of these heavy nuclei. And I always say, this is the only simulation you'll ever see that's slow running. Because in astronomy, we show, this is how galaxy forms. 13 billion years and 30 seconds. It's really short. This is the opposite. Me showing you this, and it's going long way.
So where?
So, you need to strong neutron flux. Yes, that's right. So there are not that many neutron flux. So where do you find lots of neutrons in the universe? Is neutron stars, right? Neutron stars form in the making of supernovae, of the explosions. Okay, so maybe some of this heavy material would have made in the making of a supernova explosion that gets expelled. Or you have neutron stars, so we are not getting neutron stars, so usually that's the leftover supernova because two from a binary pair. The stars usually actually show up in pairs, and so it's not too unusual to create a pair of neutron stars that will still orbit each other after both of their progenitor stars have exploded. And those two neutron stars will orbit each other diligently. But as we know now, thanks to LIGO, the gravitational wave observatory, we know already that before, but now it's been measured by LIGO, is that these two neutron stars they would orbit each other for like forever, but in the process they would lose energy. So that orbit is what we call it, the orbit decays, and eventually the two neutrons will merge, and that results in an explosive event that has roughly the energy of a supernova, but the process is completely different. And the cool thing is, when these two neutron stars collide, they produce a gravitational wave signature because neutron stars are super dense objects. They're like giant atomic nucleuses. So there's a lot of interesting physics happening already. So you basically form a super neutron star, right, smashing two into each other. More interesting physics happens, and that means that there's this ripple sent out, into the space, the space-time continuum, basically, what do people say, the ripples of space-time. It's like you drop a rock into water, right? You see the waves coming, so that's exactly what happens when two neutron stars merge, and this is neutron star, right? It's really violent to smash two neutron stars, so they are condensed already into each other, and the in 2017, one of these events occurred, and the likely gravitational wave observatories they detected that, and then the astronomers pointed their telescopes in that direction, and they indeed observed what we call the electromagnetic counterpart. So there was something seen in the sky that faded over the course of 2 weeks, and that light burst, that light, was exactly what you get when you create all these heavy neutron nuclei in the arc process, and then the neutrons stop, and then it takes about 2 or 3 weeks for most of them, of these nuclei, to decay to stability. So we saw, the astronomers saw in this electromagnetic counterpart, the nucleus synthesis of heavy elements occurring. And that's just awesome.
So that's gravitational.
Yeah.
Two neutron stars colliding progressively violently to create a super neutron star, and that's where you get all the neutron effects. The whole shebang that happens in 2 seconds. It's a bunch of
So that confirms that one of the price for sure is for the arc process to occur is neutron star. Interestingly, to mention this here, a year prior, in 2016, my former grad student Alex G and I, we discovered a small dwarf galaxy that is currently orbiting the Milky Way, a particular two, that was full of ancient iron-deficient stars that also had a strong signature of these heavy elements, exactly like HE 1523. We weren't looking for that. I actually wanted to prove that they have really low levels of heavy elements because that's what we have seen in all the other dwarf galaxies. And I was dead set on showing again that is yet the case again, and that this is the typical signature of early star formation. We already talked about low starting with barren abundances and the oldest stars, right? This is what we had seen anecdotally in the ancient dwarf galaxies that are surrounding us.
So that's what you do. So that dwarf galaxy has a bunch of ancient stars.
Yeah. And so now we're taking a tool, and it has the stars show the signature of the rapid neutron capture process, the arc process, and we are like, okay, these stars are located in the dwarf galaxy right now. We have environmental information. They are not lost in the galaxy where we don't know where they actually came from. So we know these stars were formed in that galaxy because they're still in it. And that we already deduced from that it must have been a neutron star merger that went off in particular two at early time that polluted the gas in which all of these stars formed.
Can you speak to what dwarf galaxy is? Can you speak to what is referring to dwarf galaxy is this open Milky Way galaxy?
Yeah.
So we keep it by
It totally is hard to keep. I'm telling you, it's right. The Milky Way remains surrounded by thousands of small dwarf galaxies. They are collections of stars. Some of them we call them ultra faint dwarf galaxies because they now only contain a few thousand stars. It's very, very faint. Uh, yes, because they're fairly close, and we detect actual individual stars. So I've observed some of the faintest stars that we possibly observe with current telescopes in these four galaxies because I was able to know what the chemical composition is because there are leftovers from the early universe. They did not make them, so they're still in their native surrounding. Like what it's like getting the lions in the wild, and I was studying how and compare to the counterparts that got eaten and are now in the world. And so
So presumably most of those stars, not all of those stars, like those galaxies are really ancient.
they're all really ancient because actually, as it turns out, if you have a small galaxy, there was a process early on in the universe called reionization that kind of heated up everything. And together with some supernova explosions in an early shallow, bound system, all these little systems look just like gas. It was sort of blown out or simply evaporated or both. And so these systems have been unable to continue to form stars since. So it's the best for us stellar archaeologists that we can hope for because it's a whole bunch of stars still sitting there. It's not just one, it's a whole bunch of them still sitting there ever since, and nothing has, literally nothing has happened. She's just been waiting there.
So from a stellar archaeology perspective, what is like juicing, registering the Earth stars and galaxies that have been eaten, or the galaxies we're doing with the stars and what's I don't think you realize exactly what you said you love stars, so which do you like of each?
That's a hard one. I love them all. They serve different purposes. The stuff that the Milky Way are, I can get much better data for them because they're brighter, they're closer, so they're brighter, and that tickles some fancy.
And they have interesting
Yes, and we can get that. And so HG1523, for example, that one is really bright. Only it's a giant, so it's intrinsically bright and it's really close. And so the data I got for that was insanely good, and that yielded this uranium detection, thorium detection. I can never get that content for these galaxies. So that was a big trade-off. But the environmental information that we get along, the basic information we send in each world galaxy is really valuable in establishing, this, for example, site information. Because the galaxy is still there, so nothing crazy could have happened. So actually to close that loop, probably some heavy elements come out of supernovae here and there, but somehow my human colleagues tell me that the normal supernova just doesn't have enough room to really get that power process going and do it.
things.
We did probably the neutron star merger, or we actually kind of supernova that's extremely massive and has been rotated and just looking up spin, right, to really get that particular process going. But the normal supernova don't do it, right? So only a little bit comes out. But you could come along and say, oh, why don't you just take 100 supernovae together, build up the heroes, right? But then I come along and say, like, oh, this dwarf galaxy is still intact today. If you would have plugged 100 supernovae into this whole system early on, it would have blown apart past 5 or 10. So that's a really important constraint that we have, that these systems are still alive, right? So it helps us to pin down when certain processes could have possibly happened. So it's just a different type of information that we get.
It'd be amazing if we could talk about the observational aspect of this, the tools of observation. So what telescopes that do you use? And what's the data like? And I think I'm going to get interested in is about the actual process of day-to-day observation. Much of probably late nights.
But yeah, that's one of us that really important as well.
You've been all night long.
Well, let me start by saying I mostly these days use the Magellan telescopes in Chile, the 6.5 meter telescope, which means the barrel diameter is 6.5 meters. They're not the largest that there is out there, but it's among the largest, and I use a spectrograph because I'm a spectroscopist. I don't take pictures. And telescope is actually unusually efficient, so it kind of makes up for the fact that the mirror isn't as large as, let's say, an 8-meter telescope from the Europeans or so. So I'm very happy with that.
Efficiency meaning
How many photons get collected sort of per time unit? Because that's always the limiting factor. Um, Prior to the pandemic, we would travel to Chile to do observations. Those telescopes that's the last observatory where people were sort of supposed to travel there and take their own observations. Most other observatories basically have staff there by now and take the observations for you.
so there's directly the scientists specifying which telescope and sitting there collecting the data, make sure the data is collected well, and cleaning all the data, or uploading the data, all that kind of stuff.
Yeah, so it's mostly done for them. And obviously that's super convenient, but it also takes away a central part of the work of astronomers, which is data collection. Right? We don't have an experiment in the basement where we can go day and night or whenever we please and ask a certain question. Now the apparatus, right? Let's turn this on and see what happens. Let's turn that on and see what happens. No, we only have one experiment, which is the universe. And the order is so important to take it. So I really love going to the observatory. I've taken many students there over the years to teach them and to show them what it means to be in town. Because you go to these remote mountaintops and it's such a magical environment, and you wait there, for the sun to go down, and you get ready and you look outside. It's such a serene environment. It's a little bit out of this world.
You're sitting there, the sun goes down, it's evening, good evening, and what does it look like? What are some of the most magical experiences?
Well, when you're on top of a mountain, climbers can see that probably otherwise. It's very calm, and the colors are so beautiful, and I always become much calmer when I'm there. Because I'm just there for one purpose only, it's data collection. I can say no to my emails, I can say no to everything else because I'm observing. So there's literally less distractions because you're just there to do one thing.
And also the emails sometimes seem significant.
Yeah. It's just you can afford to focus on this one thing, and it just kind of does something to you. It's a little hard to describe, but if you then fast forward, maybe I can speak a little bit about that. I have done a lot of astrophotography there as well, so and I'm observing faint galaxy stars. These are like 45-minute, 55-minute exposures, so you actually have a lot of time. So I would run outside and just lay on the ground under the southern Milky Way, beautiful right up there, and I would just lay there like no evil, and I just stare up there and just kind of let my thoughts sort of pass through my brain, and just, I'm wondering of it, right? I talked about this in the beginning. This is when I personally have a feeling that I'm a part of it. I belong here rather than feeling kind of small. Yes, I'm small, but so many other small things and lots of small things make one big whole. And
So that's looking at the stars.
and of course, this dark sky with the bright stars. And I have described this in my book years ago. If the Milky Way is all right above you, you don't need a moon or anything. You can walk in the starlight and you will find your way. There are no trees there for safety reasons. Like you wouldn't even run into a tree. You can see, you can almost see the shadow from the starlight because it's such a dark sky and the stars are so bright. And these are kind of moments that kind of change you a little bit.
You see the unity of it.
Yeah, and it's just you and nature and with water. figuring it all out, but at the end of the day, we're just a part of it. And that really helps me to remember that you know, we're one and the same.
But that fills me with hope that I tend to think of this universe as we're very early days, whatever we think we are. So that makes me think thousands, tens of thousands, hundreds of thousands of years from now, there will be whatever we become, we'll be traveling out there to explore more and more. And more.
Yeah.
So what you're doing is the early days of exploration.
We have to do seafarers looking
Yeah.
at the sky for navigation.
Coming up with different theories of what's on the other side. But they're starting to gain your interest with the Earth moving around. And then you might be able to navigate all the way around to get to financial benefits of getting spices from India, whatever the grand quantitative process is all about. But ultimately, actually, results from a deep understanding of the mystery that's all around us. I mean, it's just travel out there. And to me, the discovery of life in the solar system, I really hope to see that one. Some kind of life, bacteria, some kind of maybe dead. Because that means there's life out there. And that's just the kind of stuff that might be out there. All the different environmental conditions, chemically speaking, that are out there. It just seems like when you look at Earth, life finds a way to survive, to thrive in whatever conditions. And so maybe that process just kind of humbles you. It's super exciting to know that there is life out there of different forms. And of course, that raises the question of what is life, even? We would have to have a very human-centric perspective of what is a living organism and what is intelligence and all this kind of stuff. And all the work in artificial intelligence now is starting to challenge our ideas of what makes human beings special. And I think we're doing that in all kinds of ways, and I think your work is in part doing that as well. That the unity you feel as well as we're part of this big mechanism of nature, whatever that is, that's creating all kinds of cool stuff, from the humble, pristine origins to the unhealthy to today. So what is, can you just kind of loop around the process of the data? What is the data? And how does the data, the raw data, lead to a discovery of an ancient star?
Well, as a spectroscopist, we have to, I guess, talk for a brief moment about what a spectrum is. Everyone, I hope, has seen a rainbow in the sky. That's basically what we're trying to do. We don't send the starlight through a raindrop, I think that's goes around and splits up the light into the rainbow colors. We do it with a spectrograph, so basically a prism. So we send the starlight through a prism of sorts, and that splits it up, and then we record exactly that. So it's a little 2D picture actually of the spectrum. Now, it's not going to look colorful, it's just black and white. Different colors have, of course, different energies. That's what we record. More specifically, we record it as wavelengths. So wavelengths, frequency, energies, all the same at the end of the day. We process that little image in the sense that we cross-cut and sum up a few columns so that we get all the data that we recorded. And what we see is it's a bit funny to describe it in words, but a wiggly line with lots of dips. So the 2D process spectrum, we call it continuum, so it's just a flat line, basically, and then there are dips. So the interesting things are the dips. If you think back of the rainbow, what we actually see in our stars is not just a rainbow, but it would be a rainbow with lots of flat lines in it, which means certain little pieces of color have been eaten away by the supernovae. And so we can no longer see it as well. Why is that happening? So if we come back to our stars, we're taking the stellar surface, we can actually never hear with our telescope to the sky, it only can go up to the surface. And so surface contains, or the surface layer contains different kinds of elements. Every one of those kinds of atoms, so elements are just different kinds of atoms, they absorb different photons that are coming from the top core by the fusion. And so that means that if you're observer, with the spectrometer or without, you will see the start of it that certain frequencies, certain energies of that light will have been absorbed by all the different atoms in the gas. So you see that effect. And so that's how the dips. And the strength of the dips tell us which element was it and how much of that element was or is in the star. So we have many dips. The solar spectrum for reference, all the dips are overlapping because the abundance of organisms is so high. It's actually a complicated spectrum. My spectrum really looks like a straight line, and then there's a huge straight line, and then it's just clear. The sun doesn't have straight lines. It's just all different in some form. But the old stuff was so little of the elements that only occasionally dips that can indicate that that wavelength is iron, and we have carbon, and it's magnesium, so it's a little struggling right here. So we have a much easier way to map out this barcode that the spectrum pretty much gives it at the end of the day. And to then measure the strength of these, we call it absorption lines, to then calculate with existing codes that mimic the physics of the stellar atmosphere, something how much was absorbed, what kind of elements were present in the stellar atmosphere. And so this is how we get to our abundance measurements, and then all together that gives us the chemical composition of the particular signature in the star.
If you look at the spectrograph and absorption line, and are able to see into it some interesting non-standard outlier kind of items, or does this have to do with heavy processing?
We actually process it's fairly straightforward to do our processing. We do it at the telescope, so I often take a shorter exposure first, let's say 15 minutes. So mostly when I do discovery work, we just take a quick look spectrum, then we process it while we observe the next cell. Then we take a quick look. We have what I call the summary plot. It's a collection of little areas of the spectrum that have the key positions, the positions of key elements in it. And it's kind of like reading the tea leaves. I have stared at so many spectra. I just need to know, I just need to see our summary plot, and I can tell you exactly what the numbers are.
Also,
Yes, exactly. And so that's a thumbs up, thumbs down. Are you worth my time or not? In most cases, it's not. Well, it's good enough. We can do basic analysis and maybe publish this as part of a larger sample, just so the output that you have observed the story and the basic nature that's hard to publish as well. I had to run. So now we remote observing all of this now from my home, from my living room, all night long. I often work with colleagues, so we do it over Zoom. We process the data, we look at it, same thing still, and we just found a story that had a very low iron bronze. And we decided, okay, that looks interesting, we're just going to keep exposing. So we took more data on the spot, and we're right after the book.
how do you know?
It's not, there's a lot of work that goes into that. I began my career by trying to answer that question, as in like doing the search process. That's why I called my book that I wrote some time ago, Searching for the Oldest Stars, because searching is one thing, it's very time consuming, and then on top of that, not everyone finds, right? I often never find, but I keep searching because it needs to establish that yes, we can do it, and we're just patient enough and keep going because we will not. And that's often the case in science. And how tedious it is, how long it takes to get to that one, and just that moves the field further.
How difficult it is to believe that there is a thing to be this.
Yes, yes. If we have to say, one stat is a discovery, two is a sample, and three is a population. So as soon as we found three of the roughly the same time of them, but she keeps guessing.
Probably the course.
Yeah, but it kind of remains really hard. And, but the thing is that I passed three, many of us said, okay, we solved that problem. We showed it three times, we can't do it. That's the thing, right? That's that population. Three iron deficient stars, right? That's one puzzle. Now we can move on to the next thing.
That's an indicator that there's many more.
Yeah. So, to cut a long story short about researching, we started early on with what's called low resolution spectroscopy of many stars. So, for example, my thesis work almost 20 years ago was piggybacking off the quasar survey that has collected. So, quasars are basically giant supermassive black holes that are really far away. So, you only see one big bright light point. It looks like a star, but it's actually just a giant supermassive black hole that outshines its own galaxy. And people have been trying to study those, and they've taken little spectra of all things in the sky, and it turns out you can fish out the actual stars from that and look for certain signatures that might indicate low velocity stars, so stars with low velocity. And so it was painstaking work to then take medium resolution spectroscopy to get a little bit more information, use approximations, get candidates, and eventually take to big rocks like Magellan to get a high resolution spectrum so we really see the dips of all the individual atoms that then give us the kind of answers of day by day. These days, with another grad student, I developed a new technique to use images actually of all the stars in the sky taken with very narrow filters. So it's like you wear very specific glasses that only let so much light through. And so we can do similar things through having several narrow band filters, what we call, to fish out things that have no absorption over here, so just the straight line, and then a little dip here, so a little something here. And that has proven very successful. Yes,
Space.
that's right, because these stars are a little bit like a needle in a haystack, right? There are not that many left over, and certainly the galaxy has plenty of stars in between. We need to cleanse all of those to get to the good ones. So we always start with billions, and then work our way down, and 3 were capable.
I wonder how those ancient stars feel that they're noticed. They probably know, they probably pays attention.
Right.
I'm just kidding.
We're all fascinated, so
It's good. It's inspiring. Even if you're the outcomes. In your pristine nature, you just don't let everyone else be noticed. I'm hoping this will is there something else you could say that's about the challenges of this kind of high precision measurement that you're doing? So this kind of collection of data, looking, trying to kind of pull out the signal from the noise out
well, that's literally what we're doing. The puzzle point is actually trying to find the needle in the haystack. And then we find something, and then it turns out it's just a little bit too faint to actually get the kind of data quality that we would like, or that would be warranted to give it the potential of the star, right? I don't know.
there. There's always a little bit of noise that try to say how special is this one?
Yeah. So they both iron for stars. Their iron lines are so tiny that they're literally, almost in the void. So you need incredibly good data to make detections. And the funny thing is, we're looking for the nothingness of, say, the iron lines, but I don't want nothing because if nothing in the spectrum we can't measure. We can only get up a little bit, but we do like to measure. So we are looking for the last little bit that you could possibly detect, and that's the strong function of the brightness of the star, because the telescopes are the size that they do. It's not going to change for a while. Hopefully, eventually it will, but it's going to be at least 10 years out. So it's often literally stuck in the noise because we can't make the measurement. So actually, the record holder for the most powerful star only has an upper limit. We can't get enough data on this to actually pinpoint a measurement. To then take it to our theory connector and give me this little iron out of your phone. So it's a bit frustrating, but also super exciting at the same time.
So it's got a most exciting aspect. What's like the most exciting discovery to you? Is there a moment when you saw just a data and you kind of your heart skip?
Yeah, of course.
Is it HE 1327?
That was definitely one of those moments. I wasn't actually present at the telescope, but we were seeing the data immediately from our colleague, and we just looked at it, and our eyes were like, oh my god, is this really what we think it is? So we had to run some numbers, and it was. And these are magical little moments. And the thing is, often we have false positives, and so there's always this kind of period, and often it's 10, 15 minutes where you need to make some tests to kind of make a decision. Is this really something I should keep observing now? Is this really as good as I think, or am I being fooled by something? Right? So actually, if you take a spectrum of a white dwarf is the leftover core of a star like the sun that has gone extinct. And white dwarfs have lost all the outer atmosphere, so it's just the hydrogen helium core. So they look like a metal of their sun because it's only hydrogen helium, right? But the hydrogen lines that you can see in the spectrum on the cells of the white dwarfs are really wider than yours. So you need to have a good eye just to check, is this one a little bit wider than us? Is this the white dwarf who's fooling me here?
Yeah.
And so it's like this moment, it's like, oh my god.
Minutes of nervousness.
Yeah. And sometimes, it's a dud, and sometimes it's not.
What's been a pain for you? Like a pain for you? Is it all leading up to the first? Is it all about the teachers and place on that? Just the leading up there? Is it about that? Yeah, it has been the whole research.
That's a good question. I mean, it starts with mundane things as in like you want your telescope time, you travel there, and the weather is completely cloudy, it rains, and you have 3 nights, which is a lot, and you go home empty. So that's definitely not probably not what you were thinking of. But there is a certain occupational hazard to it.
You should try it. Resilience and patience.
Yeah, and you just gotta learn to live with it. Coming back to Reticulum 2, actually, that little blue galaxy, that was a run that we had, and the weather was incredibly bad. And I sent my student there, and I was at home. He calls me at 2 a.m. and he's like, Anna, I got close to the sun. And there's this line there, this European line. It looks like a little rich star. And I was like, it's cool. We all make mistakes. Send me the data. Send me the summary. And so I look at it, super tired. I can't really tell. It's wrong, but I can't tell you right now that it's right either. So why don't you go to the next part? He goes back and I'm like, Anna, it's just the same. What am I supposed to do? And then I go, maybe we found an R12 galaxy. Let's go to the next one. And the weather was degrading. And so, kind of long story short, we had to come. So he was observing the stars. It was an R-process galaxy, the first one we had ever discovered. Totally unpredicted. We had no idea that this was a thing. I mean, of course, we thought that thing. And in the end, the weather was getting worse and worse, and we wanted to see how many outbursts there are in this galaxy. So we managed by a hairline to observe the 9 brightest stars, and the data quality was atrocious. Yes, absolutely. It was a really faint stars. And so we were really lucky by making a very tight strategy of getting the absolute bare minimum for all the stars so we could at least take a very quick look, is it in dead or is it red? Could be say yes or no, just to get an idea. We needed to know. Why was that important? Because we could only observe this system again 9 months later.
So there's always a window of observation.
Yeah, it was fitting. This was our chance, and it was going away with the clouds, you know.
That was super festive.
But we just made it. But really, it was almost impossible. And it was just, the thing is, this is such a serendipitous moment. In a serendipitous moment, the enhancement of these heavy elements was so strong that even if it was really crappy data, we could still see the enhancement. Right? The absorption was so strong that it stuck out of the doorways. If the enhancement wouldn't have been as strong, we would not have been able to say anything because we would have been able to. But because it was so extreme, it meant of the hand, despite at the weather to say that yes, this is it. So that was quite the night.
What? You know what? So that was the first time I crossed the water.
Yeah. I didn't sleep all
Do you have hope? Are you excited about the James Webb Space Telescope and the other telescopes in the future that increase the resolution and the precision of what we can detect now?
Absolutely. That is fantastic already. I am not planning to use it personally, although I do have 1 or 2 of the proposals actually, because similar to what we already spoke about, we're interested in the same thing, we're just kind of looking at a different set of events, right? I have my old surviving stars, and I concoct these stories about what the earliest galaxies may look like, what the objects were that contributed energy, elements, and all these things. And my JLST colleagues, they try to detect some of these earlier protons from these early systems to look at the energetics and other things, what was there, how many, these kinds of things, right? So together we're trying to explore this possibility of years, but we do it in very complementary ways. So I'm very excited to see what they can come up with and how that helps me to inform my stories better and more comprehensively.
What do you think is the future of the field of stellar archaeology? How much can we, maybe what are the limits of our understanding of years
Well, obviously, lots of limitations in the sense that I always say that I'm not going to foresaw for any of the questions because there are so many different kinds out there. And we still find new patterns. So there needs to be an explanation. The question is it ultimately just one 50 star? Is it 2 or is it 3? Right? Is it a sample? Is it a population? So we haven't concluded that kind of work yet.
So every medical star is a kind of data point we can use to improve the quality of the model called the evolution of the early universe.
Yes, and I would say we've made huge progress on that for years. When I joined that field, it was in its infancy, and there was this serendipitous discovery of that first separation star, and we have filled in the canvas a great deal since then. And this is what I have really enjoyed doing so, because there was so much discovery potential, and it's been dying down a little bit because of all the progress. It's on the up and coming again because there's so many large spectroscopic surveys in the works now that will just provide a different level of data that we haven't had before. I'm sort of this older generation. I have only very few colleagues on small teams, and I do every single thing myself. That, whatever I can, I do myself. I I don't generally take other people's data, at least not really not in the end stage. I'm not a big data kind of person, although having moved that way, I certainly use data from the Gaia astrometric satellite for kinematics, but that's personally a new thing for me to use those big sky surveys that are available. So it's still very sort of hand field, where we do our individual observations. I have enjoyed that a lot, but that's about to change.
So once that is done,
Yeah,
it is power to that. Build a situation.
absolutely.
Everything is done.
Yeah. And this is how you can really drill down on the questions that you have, right? Because you control what data you otherwise you have the data that you have, right? You get what you get, and you get upset. I don't like that. I'm a little bit snobby. I really like to formulate my questions, go to the telescope, and then come what may, I'll try to get.
And also for that intuition for the data can do a lot of fun. You can't crux of the data and that kind of stuff.
Yeah.
Sometimes it lost in the application to use the data.
Yeah. And there's always the danger if you have someone else's data that you just don't really understand the limitations, completeness things, how certain things were set up, and you get out what you put in. So I'm really particular about that, and it certainly paid off for me. That's one of the main issues that I try to teach in my classes and to my students. That you need to be able to formulate express the question really well, because otherwise you're going to get an answer to a different question, but you won't notice that that the goalpost has shifted in the meantime, right? So your interpretation can only be as good as the question. If you need to change your question, that's cool. Do it. But then it needs to pair up with your interpretation. And so knowing, really being in the know of every step of what happens, that leads to quality results. That's why I have sometimes a little trouble with sort of big data and statistical analysis. Yes, on average that's true. I'm not debating that. But I'm the kind of person I like to look at the outliers and not the special ones. And they just need to be treated in a different way. There needs to be an acknowledgement of different ways that come in.
So big data can look at divorce rates. And so you and I want to go into those stories.
Yeah.
So I don't know if it's possible to say, but what do you think is the big discoveries that are waiting? Is it on the different dynamics of the yield, the common narrative, the common story of these never start? Is it where?
I think individual discoveries actually, we've made most of those, certainly through individual explorers. Finding yet another second generation stuff is very important for me, but isn't really going to move the needle. Finding 50 of them or 100 of them, that would move the needle. That's hit order or to magnitude power. And new search techniques and new surveys, they enable that. But would you still call that a discovery? Correct?
It's just scale.
Yeah. So I think about it more like literally of the puzzle. Let's say you have 1,000-piece puzzle and 900 pieces in there. If you're a person like me, I want to get to the last one. I'm not going to leave it just like, okay, I see broadly what this is going to look like. I'm done now. No, I want to get to the last one. So is the picture globally changed? No. Are we going to figure out all the details of how it really works? Yes. Right?
Really
Getting into it.
the ancient, the ancient starting point.
Yeah. Because I think that's what many of us scientists are really detailed ourselves. And I think that's our job too, right? To really kind of make it airtight, to really walk away from I fully understand this. Not just broad, we really know. And so more and more of that is going to happen. And so I think that's probably true across astronomy, just individual can't say They didn't even find a word for that. The hopes and expectations that go along with the word discovery so enormous. The name will always be able to live up to that. But it doesn't mean that we're not finding out new things. It's just a different kind of quality because the questions are shared. We told one more, suddenly there are 10 new open doors that we want to explore and march through. And that's finding this love puzzle pieces in that we will be able to find.
And so there's a lot of value to the discovery in the big picture of our universe and the details.
Yes, we need both, absolutely.
Perhaps drifting to the philosophical. Let me ask you about the Big Bang as we kind of encroach onto it. So you were just kind of taking steps backward to the Big Bang. Do you think we get to deeper and deeper understanding the really is the Big Bang? And the philosophical questions, if we'll be able to understand what was before the Big Bang or why the Big Bang happened. Is this really possible?
Not this far. For better or for worse. Because stars only throw the time when they formed. And the Big Bang is surely before that. I mean, I often talk to my students about the difference between math and physics. Let me give you an example. We talked earlier about AT-1523, and I was happy to share with you that I measured fire with uranium, but I actually didn't quite close that loop. So we did that to try to attempt to calculate an age for the stars, right? But they rely on us knowing how the art process works, how these elements are created, where it happens, and then how those elements get dispersed into the gas and end up in the next generation solar star. Quite a few questions. So that's how we go to the age of 13.2 billion years. This is probably not accurate, but this is the best calculation we could do. And the reason I'm bringing this up is that that was actually the average of multiple elemental ratios that each gave a certain age, and then we averaged that because for better or for worse, this is the best we can do. So some of these numbers said, oh, this guy is 15 billion years old, and then others said, this is 10 billion years old. So I would use that in my class to say, like, what's the good news and what's the bad news here? Some ratios say 15, some say 10, right? Is 15 correct? And then I ask them to say something. And so the thing here is that it's an absolutely correct calculation given the mathematical and physical model that we constructed. But does it make sense? No, it doesn't. If we believe the universe is 15.8 billion years old, 15 is ridiculous. Yet it is correct. Isn't that interesting?
Correct.
Yes, it is not ironic. This is what I calculated. Nobody made a mistake. Now, we can question whether that's true or not. But that's a separate issue.
So you think physicists are necessarily true mathematicians?
Well, it depends. It depends. Sometimes yes and sometimes no. Right? So, what our job as physicists is to take the mathematical model, calculate our numbers, and then ask the question, does this make sense? Right? Now, in the case of 15, it doesn't. But we took the average anyway because that was the best we could do. So, let's put that aside. Let's apply the same thing to the Big Bang, right? Math can tell us things that we as physicists can't grasp because it doesn't make sense to us. Now, in the case of the Big Bang, that's a special case because we don't actually know what's supposed to make sense. And this is where things get interesting. But this is where math will ultimately be the winner because we can no longer say this makes sense or this doesn't make sense because the physics is broken down.
But that was not true.
Yeah. Depending on who you are.
Sure.
This is the current question, right? How much further can we push math, let's say, from the front of the Big Bang, if there is such a thing?
It's the front of the back. The front is the
Before the Big Bang.
obviously the
Right?
we all the derivative.
So how far can we let the math go before And I don't know what the answer is to that, but it's really cool, and because math doesn't have, it's not limited on our physical nature, it can probably go a little bit further than
Yeah.
correct?
Not compared to more dimensions and dimensions.
Yeah. And it's judgment free because it just calculates things on its own. Well, this physicist is weird, most judgment. This makes sense, this doesn't make sense. It just it works.
It's just a beautiful dance. It's such a, it's so amazing that through this dance, we can explore the questions. Like, isn't the Big Bang just blowing your mind? But this thing is starting from the point.
Yeah.
Now we're here.
Yeah.
You know, God can't do it. And then all the stuff we study, and this evolution of chemistry created humans. We're here talking. And there's a lot more to the story. It's amazing.
Yeah.
And this kind of morphs that you do is observance data. And is there, you're looking at old life, old data.
But only a few thousand years.
Just a few.
That's the difference between we and the key colors. Their objects, that light has traveled for 10 million years or whatever it was to us, and they're observing that now. My light has only traveled a few thousand years. It's nothing.
So whatever you observe now is not the same.
Yes, these guys are the light that came in other
Just a few thousand years. All of it. You travel just a few of them.
yeah.
Maybe it's a big drop there.
We wouldn't have any planet.
So that's, is that a definitive conclusion?
Well, what a planet's made of. Elements, right? To take the Earth, all heavy elements, right? The universe needed to reach a certain stage first to have produced enough of all these elements to actually make them.
So on average, you're right. So, okay.
So that took quite a few billion years.
So they're not going to have a mechanism for forming things. You can have visitors probably with the built in the two backs.
Yeah.
So they're interesting in that they reveal the early chemical evolution of the universe.
Yeah.
Not that they're a typification spot. Not.
Well,
It's not.
that's a worm. Just the planet islands to go to chill.
In your book, you highlight the major contributions in the field by many women. Some of these women were not, as you describe it, immediately credited for their topics. So from a computer science perspective, the study must have had quantum computers. Who are these women and what can you say about the nature of science? Right.
Discovering things is part of human nature, right? And so it has happened for the longest time. And not just by men, but also by many women. The field of stellar astronomy, which is my field, has particularly benefited from many discoveries made during the invention of Harvard computers. That's a term used for women who worked about 100 years ago at the Harvard College Observatory, and they were hired for their low wages and willingness to do diligent and patient work to comb through the big data of the day. So the observatory director, they were given large size surveys at the time, and they needed that data needed to be processed and looked at and analyzed. And so many women, several dozens, more than a dozen years, were hired to do that work. And in the process, because they were looking at the actual data, they were smart, even though they had no formal education, they made a lot of discoveries that they were being in tune with what they were doing. So they weren't robots. The term computer would perhaps lead on. So Annie Jo Cannon classified thousands and thousands of spectra and found out that we can, stars have different Cecilia came to Rothschild later on. I think 1925 was one of the first women to obtain a PhD in stellar astronomy, and she figured out, she calculated that the sun is mostly made of hydrogen and helium. That seems normal to many of us these days, but at the time it was thought that celestial objects are made of the same thing as the Earth.
That's a gutsy discovery.
Yeah, it was later termed the most important thesis of humankind or something like that. What a revelation! Realize that stars are made of hydrogen and helium. This was exactly the time when people figured out why stars are shiny, maybe because of nuclear fusion and protons and the tellurium fact that leads to big fusion. Otherwise, the protons repulse each other, they don't come together. And so, what an incredible time it was back then. And so, stars and nuclear physics very closely related. It remains now called nuclear astrophysics. And so, many women had many contributions to that. Of course, prior to that, Marie Curie discovered two elements. Oh, so awesome. Radium and polonium. Using light bulb discovered nuclear fission. That is the basis for understanding the art process. This is exactly what happens in the art process. The heavy nuclei that say uranium bombarded with a neutron. We talked at length about it. It will decay. Not decay. It will fission. It will split into their protons. So two lighter elements. That's exactly what we observed. I have always a higher abundance of barium and heavier elements because of this fission cycle that she calculated in 1938 and 1939. So many contributions, and it's just so remarkable. If you just take that body of work, that changed how we look at how we see the universe, how we understand things. Has led to so many subsequent discoveries. We're talking about
Well, everyone's sticking together.
that's progress. Science is what it is. We have to decide what we do with that knowledge, but we can always use things to build us up. That's part of the endeavor as well.
And also part of the human nature. Issues with corruption and credit assignment has always been
Yeah.
to make this whole life so damn interesting. That's why you all the nature could be evil.
Yeah.
And that's the surface itself in all kinds of places. All the time.
Yeah. Lisa Leitner was nominated for the Nobel Prize 40 times. She holds the record for that. She never received it.
Yeah, and of course the Nobel Prizes is its complexities. One is the credit assignment, the two, even in astronomy, sort of assigning credit to a handful of folks. That's so many contributed. It's a complicated story also.
Yeah.
Okay, so I've got a romantic question. What do you think is the beautiful idea of astronomy? Like stellar astronomy.
Well, so early on, when I was in high school, I was thinking, okay, what do I want to do when I grow up, right? I knew I wanted to do astronomy, but I was a little bit torn because my interests were definitely stars, stellar astronomy, but also chemistry. I always had fascination with the elements, so Marie Curie was a big role model. My friend actually made a beautiful movie about the discovery of the elements. This is the theater play, but digitized. Where when I thought I could actually relive the sort of discovery moment that Marie Curie had, it kind of shivers down my spine. It was fantastic. And this is the kind of thing that I wanted to experience. But yeah, so nuclear physics and element creation formation was really interesting to look into the elements, stars, and all of that. And I was like, I don't know if I ever find something that combines all of these it clicked all over my head. It's like, oh my God, it all fell in place because we can use these old songs to study the elements, to learn how they form. We can get these clean signatures that help us inform the nuclear synthesis processes, you know, and I know, of course, I need to know about stars too, so it's like all together. And that was sort of a moment of magic. And then the fact that I have now done that for 20 years is just like, what the wrong with me? And so, in some sense, it's an ongoing life story for me, if I could say it like that, where, you know, I found my stars, my thing, and I'm fortunate enough to be able to keep doing that. And I'm happy to see where it will take me. You know, it's an evolution. As with every relationship, you have to, if you don't march forward, you move backwards. I'm not just moving backwards. So I'm letting the field and the discoveries, findings lead me to, you know, not often. It's not hard for me to follow some of my hunches, and sometimes even at the telescope, it's like, let's take a look at this one. Have a good feeling that usually something good or not bad comes out at the end. And I really like that, that I have the freedom to do that, that I'm allowed to follow my hunches. Too many people, I think, are sort of boxed in with their job or their life. They don't have that same freedom. That's really important to me, and I certainly try to make use of that. I also try to teach them to others, to trust them, to learn. You know, you need to learn new things, but then you need to also trust that knowledge and you have a grasp on it, right? You get out what you put in. And being able to contribute in meaningful ways to our knowledge about our cosmic ancestry, our cosmic history. That's a wonderful thing.
And this way, your personal love story with the stars falls. What advice you raised for what advice would you give to young people that are trying to find the same kind of love story in their career?
It seems increasingly hard at times to find that. Sometimes I feel that, you know, young people have all the opportunities these days, and that's wonderful. But it's almost like that leads to some, what's the right word? They're a little bit of tired, too tired to make all the decisions, because at some point you need to put your eggs in a basket, and you need to be okay with that. We can't do all the things, even though we're often told you can be president too, and I think that's really important to convey. But at the end of the day, we can only have sort of one job or one type of profession. I'm not saying you need to be locked in, but it's hard to change 180 degrees. And so lots of people, I think, are often afraid to really dig in, at least for some time, and get their hands real dirty and really learn from the bottom up on one thing, because they're afraid they're missing out on 99 other things. But life is a little bit missing out on 99 other things because we only have 24 hours in a day. I have a feeling very often there's so many things I would like to do, many things I would like to try to be good at. Sometimes I wish I had a different job. You know, these other interests too, but I wish I can only do one thing. So I have no regrets. But this is a general feeling that I think most of us have. But if it stops you from really digging and drilling down on one thing to become an expert in one thing, to be really good at one thing that you call your own, then it just makes it difficult.
And so fulfilling life is in part likely to be discovered from a single pursuit.
Yeah, yeah, for some time with your heart and your head. Because I think most people long to prove something. You know, we all, I think, want to leave some legacy of some sorts, you know, for our children, for humanity, for this planet. And I think for young people to strive for that, or to strive or trade that for all the opportunities, because an opportunity is nothing if you don't do it. You need to do something. Okay. So I chat with lots of people about this, and I often start by just saying, hey, tell me what you don't like. Because it's much easier to let out what's not on your plate. And then this way we get a little bit closer. And then, why don't you take a risk? You just sign up for something for 3 months.
But that's what it feels like. That's what it feels like. It is that. It's a risk. Commitment is a risk.
Yeah.
Because you're basically sacrificing all the intellectual and I guess you have to trust the magic of the
Yeah.
You know, it's one thing, stick with it. And then you can just something.
Right. And this moment of kind of feeling it in your entire body and mind that this is the right thing. Getting there is probably really hard. But if you don't try, you won't find out.
The hard stuff is the fun stuff. That's also how we can find out.
And then there is that, yeah.
This makes sense. You also mentioned that you've taken a little stroll into the artistic representation of yourself. Can you speak more?
Well, I already just mentioned, sometimes I wish I had more time to do other things. So I find little sideways, I guess, to pursue things that satisfy me, or at least I try to find connections. And so some years ago, I again with the help of my friend who made this movie series, she and I wrote a one-woman play where I actually portrayed Lisa Meitner, who was an Austrian German nuclear physicist from Germany, so I found a great accent for that. And we wrote this play about this moment of discovery of nuclear fission. Again, this is an absolutely critical piece that explains my work today. And we all stand on the shoulder of giants. She was one of those giants. And in some ways, it's of course a way for me to acknowledge other people's work that have come before them. It's a wonderful way to highlight the contribution by prominent. And the way I do it is it's a 25-minute play in costume where I relive for people the moment of discovery. Then I turn into myself, and then I give a 30-minute presentation on the art process and the creation of heavy elements, because the audience cannot perfectly understand it. Public audience, given the historic backdrop of this discovery that they just lived through my presentation. And it's a wonderful compliment that almost spends 100 years from one group to the next, passing on the torch. And when we write out our results in, let's say, magazines like Nature or Science, it's always about the results on the gold platter, perfectly prepared. It's the discovery is never described, only ever the results. You asked me beforehand, right? What is it feel to be at the telescope in this world, right? I'm happy to talk about that, but it's nowhere written ever. Nobody really talks about it. And so having a form of theater, the arts, to bring this exciting moment that is what we all want to experience as scientists to a wider audience is so profound and so rewarding. And they all love it because everyone can understand the moment of discovery. I was looking for something and then I found it. It's like you misplaced car keys, right? Yeah. Everyone can understand the implications and the findings. That is much harder to understand for anyone. This is where the scientists work truly lies. This is our job. But the moment of discovery is easy. And it's beautiful. And it needs to be said. And so taking my audience on this journey, what is the perils? What are my worries? And then, here is the moment of discovery. problem with science is that people do it.
It's also
You have a
good.
problem.
That's also what makes it beautiful, right? Human simplicity, the way we through all the struggle, through all the hardship, through all the fun, through all the search.
And so the art's a great way to portray that and to broadcast that, right? I think this is how the audience really should be interacting with scientists. Much less about the findings, but really more about this yearning for answers, right? I need to find these taxes. I need it because I need to go, right? Now. Oh God, here it is. Now I can go to my answer. It's so relatable. We just need to find more and better ways to do that. So I hope to turn this into also a digitized version at some point to again make it more accessible.
I hope so too.
So far I'm just doing it in person. But it's
I'm really people who did just that. Let me ask you a big ridiculous question. You woke up with the stars. You woke up with the early stars. So let me ask the big question which we don't often ask. The struggle to answer what's the meaning of this? Why
we talked about the biological evolution requires the chemical evolution for all of this to kind of play out. And carbon played this important role. And in some sense we're just a consequence of all of these things being the way they are. So maybe this is just where we are supposed to be. Because the laws of physics work the way they do. And we talked much about the variety of everything really. And certainly, from over here to over there. And things in the vicinity of what's on the solar system forward, they were the way they were. And life maybe wasn't necessary consequence. And in some sense, I like to believe that because then it becomes reproducible. Like they actually lost it. If it's total chance, right, that makes it harder. And that's not truly satisfying to scientists.
So it's a consequence of psychological evolution, which is a consequence of biological evolution, which is a consequence of chemical evolution, a consequence of physical evolution, whatever disciplines. It's turtles on top of turtles.
Turning all the way down there. I mean, yeah.
You have studied some of the most ancient terms.
Yes.
Very modern with that.
They missed the point.
Yeah, they did.
Well, thank you for your incredible work. Thank you for highlighting both the human side and the deep side. It's just, I'm a huge fan of your work and everything you do. And thank you for talking to me.
Of course, it was wonderful. Thank you.
Thanks for listening to this conversation. To support this podcast, please check out our sponsors in the description. And now, let me leave you with some words from Douglas Adams in Hitchhiker's Guide to the Galaxy. Far out in the uncharted backwaters of the unfashionable and listless island on the galaxy lies a small water body that is sun. Orbiting this, at a distance of roughly 92 million miles, is an utterly insignificant little blue green planet whose 8 center planets are so amazingly cool that they still think digital watches are a pretty unique idea. Thank you for listening. I hope to see you.
It is the most important. It's not a coincidence or an accident that its name will be first of all for the Constitution. Without it, no democratic society can live quite. I'm an absolutist. That is, I believe that, for example, people say to me, but what about hate speech? Hate speech is much more important than love speech. The reason is, I'm much more interested in knowing who I should not put back on than I'm interested in figuring out who loves me.
The following is a conversation with Harvey Silverman, a legendary free speech advocate, co-founder of FIRE, Foundation for Individual Rights and Expression, and the author of several books, including Speech and Criminal Justice, including shadow of university, the trail of liberty and America's campuses. Harvey is running to be on Harvard board of the season seal, the write-in campaign. You have to spell his name correctly, civil plate. Policies advocate for free speech and to push for reducing the size of Harvard's administration bureaus. Election is always Tuesday, May 16th, 9 p.m. Eastern. Vote. You have to be a Harvard alumni. If you happen to be one, please vote online. It's a good way to support freedom of speech on Harvard campus. Instructions how to do so are in the description. As a side note, here's a lot to say, but since there are several controversial conversations coming up, I try to make sure this podcast is a platform for free discourse where ideas are not censored and explored. If necessary, challenged, thoughtful, and athletic way. It's by having such difficult conversations, not by avoiding them, that we can begin to heal divides, to shed lights on the dark parts of human history and human nature. This is the World Freedom Podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Harvey Silverman. You co-founded the Foundation for Individual Rights and Expression, also known as FIRE, a legendary organization that fights for freedom of speech for all Americans in our courtrooms, on our campuses, and in our culture. So let's start with a big question. What is freedom of speech?
First of all, the organization, when I co-founded it in 1999, was called the Foundation for Individual Rights in Education. It focused on free speech issues on college campuses and academia. And only earlier this year did we decide to expand our reach to the campuses, which is why the name or the acronym FIRE remains. It's now the Foundation for Individual Rights and Expression.
The E used to be education.
The E used to be education instead of expression. And we basically do a lot of the cases the ACLU used to do with the ACLU. This is the aggressive organization, rather than the civil organization. And we've taken the role of dealing with free speech in society generally. And now this is a particularly we're prone to censorship. Everybody thinks they're right, but people who disagree with them should not be able to voice their views. It's a very difficult period right now on campus and off campus. It's about as intolerant an era as I can remember in the 81 May 10th before the coverage that went. And I can't remember if it was bad. I was born during the McCarthy era. And it's not, it sort of reminds me of that.
Well, let's start with that. Almost a philosophical question, a legal question, a human question. What is this freedom that you care so much about?
It is the most important right of man. It's not a coincidence or an accident that it's made the first amendment to the Constitution. Without it, no democratic society can be democratic for the world. And I'm an absolutist. That is, I believe, for example, people say to me, but what about hate speech? But hate speech is much more important than love speech. The reason is, I'm much more interested in knowing whom I should not turn my back on than I'm interested in figuring out who loves me and who likes me. So hate speech is the most important, in my view, and yet it's there, it's at the schools, it's unbelievable. Kids are not schooled into understanding the glory of the First Amendment when schools sort of say that they should say things that are going to make somebody feel bad. And the purpose of speech is to express honest views that people have. So I believe hate speech is as important as love speech, and my views are not good.
So it should be brought to the surface rather than operate the shadow.
Absolutely. Absolutely.
What is the connection between freedom of speech and thought?
Well, in a free society, thoughts start at the brain and then they come out the mouth. So there are different ends of the same spectrum.
So to you, the censorship of speech eventually leads to the censorship.
Of course, censorship of being notified that other people know what I'm thinking.
So there's some aspect of our society that is the thinking is done collectively without being able to speak to each other or do it collectively.
Correct. And out of speech, the theory is that ultimately out of speech comes truth. That isn't necessarily so. But I do think that when there's free speech, better decisions are made because people put their views on the table in a frank, accurate way, and then those views mix together and clash, and out of that usually comes the better decision. Not always, but usually, more often than not. And if somebody is not allowed to be a sit at the table with decision, then the decision-making process is poorer, less robust, less diverse. Right?
Can you elaborate on the idea of free speech absolutely? So hate speech can be quite painful for a large number of people. Does this worry you?
Living in a free society requires that you expose yourself to some discomfort, pain. It's maybe emotional pain, it's not physical pain, but it's the price we pay for living in a free society. Every so often learn something where emotionally hurt. Think of the alternative. All the alternatives are worse. Nobody ever promised us a rose garden. We're lucky to be in a country that has the First Amendment. Also, it's just the most country in the world because of immigration. I mean, my grandparents, my father's side came from Russia, my mother's side came from Poland. I'm very happy that my grandparents came in from Russia. I would not want to be in Russia today. I'd probably be sharing the story of Wall Street Journal. So I'm thankful that they came in. And this is a great country. It's got problems right now, but a country doesn't. We've had periods of a civil war. We had segregation. We had decimation of the Indians. We're not perfect, but it's the best place in the world for somebody who values liberty.
So you don't think that hate speech can empower large groups that eventually lead to physical action?
No, I don't. I think that we have developed a culture in which it's understood that if you don't like what's free, you talk back. You write something. We don't punch each other. We insult each other. Is insulting great? Well, I don't know. That's okay. I used to, as a kid in Brooklyn, where I was born, raised in Brooklyn. We used to say sticks and stones can break my bones, but they never harm me. And it's actually true. That was true when I was 5. It was getting young. So I've lived a long time. I've seen it all. And I'm talking from experience as well as theory. It's what happens when you do communities.
I read this line: "You cannot be protected from being called an asshole."
Especially if you're an asshole.
Well, that's but you don't have to be an asshole to be called an asshole.
That's correct.
And I think the internet is
Well, the internet has posed a particular challenge to free speech absolutely because some of the stuff that's on there is not awful. But I have no different rules for freedom of speech on the internet than I have in newspapers or lectures or in classrooms or conversations among people.
What do you think about the tension between freedom of speech and freedom of reach? This is sometimes termed. The internet really challenges that aspect. And those speech to become viral and spread very quickly to very
Well, we've had revolutions in the modalities of communication. If your newspapers were the first challenge, radio and television posed a new challenge. The FCC tried, but ultimately gave up the attempt to control obscenity, for example. And the Supreme Court has been pretty close. The one thing that liberal and conservative Supreme Courts, right now in the conservative era due to Trump nominations, during much of my life, the Warren Court, Douglas, Brennan, the liberal court, one thing they agree on is free speech. They don't agree on much else, but they do agree on free speech. And I think the reason is that they recognize that, well, my group is in the ascendance today, but it may not be tomorrow. And I want to have effective, clear rules so that when I'm in the minority, I'm able to voice my opinion. And so it's one of the few things that both sides of the political spectrum agree on. The only people who don't agree, the people way over on the right, and I call the fascists, and the people way over on the left, who are the communists. But with respect to most people in this spectrum, Republicans, Democrats, socialists, libertarians, and they have a policy of free speech because it protects them when the protection is needed.
So to you, even on the internet, free speech absolutism for you.
Yes, nobody's going to die. Remember, death threats are not law, they're not protected. Nobody's going to die. If people are going to be a little bit insulted, that's the price you pay for living in a free society. And it's a small price, in my view. Some people don't have as tough a high as others, but didn't develop it. I don't mean to say I'm cruel, but you're living in a free society, you develop a tough habit.
So that's the cost for the society.
Yeah, there's a cost.
The thing is, it can really hurt the scale, be cyberbullying, be attacked for the ideas they express, or maybe ideas they didn't express, that somebody decided to lie about it, and use that to attack.
First of all, there were some exceptions. Libel and slander is an exception. Direct threats are an exception. If you say such stuff, I will murder you. That is not law. If you say to somebody, if you say about somebody, oh, you beat your wife, that is not law. Just look at that. There are some limits. Defamation is one, direct threats or another. So it's not absolute. This is not, the First Amendment is not absolute, but it's more absolute than it is in the New York society, and it's pretty near absolute. For example, fraud. If you were self